Hello, hello, everybody. Good morning. Who's excited to be here today? Please make some noise if you're excited to be here. Awesome. I love the energy. My name is Israel, and we are going to be having lots of fun today. We have all these activities lined up. We have good panel session. We do have, speakers coming up later on today, and we have a morning and afternoon session. So when you finish this morning session, please do all to come back in the afternoon session because it is going to be energetic in here. We're going to learn a whole lot, and the purpose of this ZK Hub is just to bring all the ZK community under one canopy, under one roof. Sometimes it feels like we're a big community, but we're still growing. I mean, ZK is still new to the community of blockchain, and we're still trying to get the best out of it. So if you're here and you're live streaming this, please join us so you can learn from all the experts we have in the building today, all the amazing people we have. And, coming up very soon would be a panelist session. And trust me, there's so much to learn from this panelist session. There's so much to gain. There's so much to get from everybody coming up on the stage today. So ensure you stay glued to your screens. Ensure you stay glued here in the hall. If you're outside, please come inside because it is going to be super, super amazing. Please, a round of applause for yourself if you're already in the building today. Thank you. So, without further ado, we would just listen to the music a little bit, then get started on the first panelist session. When next I come here, I'll be introducing the people, and we can get started. So for now, enjoy good music. Okay, okay. So we are ready to get started. And we have the first panelist session about to go live right now, and we will be calling on some of the most amazing people. I'll be calling on Jody from Polygon. Please, a round of applause for Jody. Please, thank you, thank you. Okay. Then also we'll be calling on Adam. Adam. Okay, amazing. Thank you. We'll be calling on Ratan from Succinct. Okay, amazing. Then we'll be calling on Dr. Martins Baker. Awesome, awesome. Then the moderator for this panel session will be no other person but Evan. Please a round of applause for Evan. Thank you. Let's go.
GM, everyone, thank you so much for joining us in the Z Cave today to talk about our favorite things. Big appreciation to our hosts here today at the ZK Hub. Really appreciate you guys holding space for these important discussions. So to get us kicked off, I'm going to invite our esteemed panelists to say a quick hello, remind us of the role that you have, and tell us what was the last ZK application or service that you used?
All right, so pleasure to be here. My name is Martin. I am a technical co-founder at Zirkit. We built a zero-knowledge rollup, and this is the last ZK application that I have used. It's Zirkit.
Hey, I'm Ratan. I'm a founding engineer at Synced. A lot of fun to be here. And I have to go with a similar answer. The last thing I use is SP1. Yeah.
Hello, I'm Adam Domrad, a staff engineer at Aztec, and the last ZK application that wasn't just our rollup would have to be the in-progress ZK email verification software that's being built on Aztec.
Hello, I'm Jordi Bailina. I've been developing the ZK VM and been in Polygon for last years, doing a lot of ZK stuff. And the last ZK application that probably is going to be some rollup, but yeah, the one that I'm more proud of is Tornado Cache. I think that we cannot forget that, and that's still a good application to use, and we need privacy, so yeah, I want to mention that.
I'm Porter from Matter Labs, one of the teams building ZK Sync, and yeah, I think besides ZK Sync, the last ZK app I used was ZK Email.
Awesome. And GM, guys, my name is Evan McMullen. I'm the co-founder and chief strategy officer at Bravado ID, your host today, and I also used ZK Email most recently. So thank you guys so much for reminding us, and you definitely want to encourage everyone in the audience to try out those platforms. So for a little context setting today, obviously we are all acutely aware that L2s have become a norm in scaling blockchains like Ethereum and even our friends over in the Bitcoin ecosystem. While optimistic rollups have, of course, played a major role in this evolution, ZK rollups are increasingly becoming sort of seen as the future due to their inherent advantages in terms of security, finality, and efficiency. So today we're going to discuss what the role of that evolving space looks like with respect to optimistic rollups, to ZK technology, and how they may or may not play well together in the future. So to start off, let's talk about the disparity between these two technologies and get a little base definition here. I also want to encourage our panelists for some healthy disagreement. There's nothing worse than 6 people hanging on a stage and all telling each other how cool they are. So this is a comfortable and welcoming space for a little bit of friction, and I invite us to try to find one thing to disagree with a little bit from the person who spoke before us. So to get us kicked off, ZK rollups are often described as being inherently more secure and efficient than optimistic rollups. Can we start the discussion by identifying some key advantages that ZK rollups have over optimistic rollups, so we all kind of start with that shared understanding? Want to kick us off?
Sure, sounds good. So the primary difference between ZK rollups and optimistic rollups is that in ZK rollups, in theory, nobody should have the chance to cheat, right? You have your ZK EVM, you have some circuits that produce zero-knowledge proofs that make sure that the EVM transitions were executed properly, and as soon as the proof is ready, you know that nobody cheated, right? This has very strong impact when people are withdrawing their assets. What we are doing in zero-knowledge rollups, we let them burn or lock their Ether or whatever asset we are talking about. Then as soon as the rollup produces a proof that this has really happened, that proof can be provided on the L1, and then as soon as it is verified, the person can finish exit with their assets, right? This is not the story of the optimistic rollups. In optimistic rollups, everything happens optimistically, then you have to wait for the challenge period, and when the challenge period elapses, regardless of whether somebody cheated or not, you are allowed to finish your exit, right? Because nobody challenged you, nobody actually proved that there was some cheating that happened. So this is what revolves around security and why people say that ZK rollups are more secure. I disagree in here that ZK rollups are always inherently more efficient. This efficiency, it actually does come in this realm of exits, but it's sort of difficult to find it all throughout the stack of the rollup.
Yeah, I think I would agree that ZK rollups are not inherently more efficient. In fact, you're paying the proving overhead, so they're inherently always going to be less efficient than running an optimistic rollup. But I think it's really in the context of having many different rollups where I think ZK shines, right? Like people have talked about having great interoperability solutions between optimistic rollups, and often a lot of the designs are not that elegant. You end up having to run, if you have n chains that you want to have interop between, you have to run n different nodes, which is just not scalable in the long run. With ZK, clearly the design there is better. I think that to me is one of the biggest places where it's not just the self-verifiability, but interop just becomes so much easier for a team to build. And I'm sure, at ZK Sync and at Polygon, you guys have seen this a lot too. And it's something that we're really excited about as well. So yeah, I think fast finality, interop.
All right, so I'm going to try to add something different here, which is, there's a difference between validity rollups that use ZK technology and what I would consider a ZK rollup, like what Aztec's doing. And the main thing there to point out is that optimistic rollups do not really provide a way to do privacy. You'd have to use another privacy technology, while ZK allows people to do client-side proving and add privacy, which I think is a feature greatly lacking from most blockchains.
I'm going to be here a little bit disappointed somehow, because ZK is a great technology. I would say if you want to do the things in the right way. If you are interested in decentralization, if you are interested in doing things that that nobody controls, that are human, common goods that belong to the human, and then you need the ZK. I think that that's the way to go. But if you don't care, if you just want to build a kind of a bank that we are not, I would say that most of the rollups today, they are not even ZK rollups or optimistic rollups. They are multi-sig rollups at the best. So, and it works. People like it, and people care about other things. It's just a kind of, we are seeing the space, mainly it's gambling, DeFi gambling, just people just playing poker between whales playing there. You can run that in a centralized server. Maybe centralized server is too risky from legal issues, so let's just build some multi-sig or something, and that works, and that's great. But, that's not what I really want to build. I want to build things that, that are decentralized. Bitcoin, it's like this idea that's behind. And for that, you need the tech. You mentioned before, if you want to communicate trustless, not with a bridge that somebody has some keys again, but if you want to communicate between that, you are gonna need some sort of proofs, and of course, ZK proof gives you this immediate validation, and you don't need to wait for this gaming there, and this is much superior. But again, if users don't care about decentralization, privacy, I fully agree. That's the next step, and I think that this is you are in advance here in the space. If we don't care about that, then really we don't really need ZK. Definitely.
Yeah, I think the story so far has been ZK is better because of the faster finality, because you can withdraw after the proof is complete in a couple hours instead of waiting a full week. But turns out a lot of users don't care that much about that. It's not a big differentiator. I think, it's these trust assumptions, and today when there's only maybe 5 or 10 optimistic rollups that have a lot of volume, I'm pretty convinced there's going to be like enough people there to like generate a fraud proof if I need them. But if we imagine a future where there's like closer to like 1,000 rollups, I'm much less convinced that every single one of them is going to have like enough people for a fraud proof. And I'd way rather depend on ZK for the trust assumption.
Yeah, one of the things of the optimistic, of the optimistic world is that it implies, so in order to be optimistic, that means that you need to follow the chain. I mean, you need to check the chain, and that means that you need to run the chain. And this is, it's very much the problem why the things do not scale in consensus, because there is a lot of people that needs to follow the chain. So an optimistic is very much the same. So if you want security, you mean you need to have a lot of people that needs to be connected and follow the chain. And I mean, if you compare that on, you don't have to follow a chain. Maybe somebody just built a ZK and gives you a proof that this chain is correct. Verification is much, much, much easier. So this is, I mean, this concept is why one of the reasons why ZK is so superior to optimistic.
So it sounds like we have a new phrase here. I like the multi-sig rollup as a descriptor. But if we were to think about, what can the bull case look like for an optimistic rollup, understanding that it's going to require some amount of observation effort, understanding that there are certain trade-offs, especially with respect to user experience. But now that we've heard all of the benefits of ZK, let's try to make the bull case for what use cases might benefit from optimistic approaches, understanding that, of course, as Jordi noted, some of those are likely to embrace centralization and discard consent. But what do those look like? Just to challenge our initial set of views.
So there is one thing that I consider a clear advantage of optimistic rollups, and it's the ease of understanding. If you imagine a ZK rollup and proof system that is broken, it's, for example, not sound, right? So you can have actually two proofs or like a falsified proof that proves some transition, some kind of a fact. If you imagine that you go to your friend who is absolutely not technical and try to explain to them what went wrong and why their $10 million just like disappeared because there was not sound proof, they will not understand what the sound proof is. They will ask you whether snark is a swear word. You will stand zero chance of actually making them understand. When you take it optimistically, you will say, okay, well, the rollup is supposed to go from here to here, and it did not. Here is a proof. You cheated right here, right? This is actually pretty transparent. So in some way, the optimistic rollups, they're actually conceptually much simpler than the ZK rollups, and that can be a benefit in many cases.
I'm gonna disagree with you here. I think it's, at least for me personally, I think it's much harder to reason about the complexity at the rollup design level when you have to design a fault-proof game. I spent a lot of time looking at Optimism's fault-proof stack. I don't know if you've ever taken a look at it, but not only is the dispute game complex, but the contracts themselves are quite complex too. In contrast, for a ZK rollup, let's imagine that you can take, let's say, a ZK VM as a foundational layer. We abstract away, we're there exists some censorship-resistant layer that is being run all around the world. This allows us to build DeFi, right? I think similarly, people are no longer going to think as much about, oh, this ZK system has all these nuances and complexities. They'll take a ZK VM for granted. It'll become foundational. And then things like securing your rollup become much easier to reason about. I'm hey, we have a cryptographic method for showing that our rollup is secure. It works, it can prove any arbitrary program, and it's been audited by the community over the course of many years. The same way that blockchain node software, if you tried to reason about it every single time you built an application, you would go crazy. So I think here, I find that ZK is much easier to reason about, but we're in an interesting transitory period where we used to have to worry about the nuances about how each proof system is designed, but when there's consolidation, I think we have to worry less. So, but to your original point, why are optimistic rollups better? I think my kind of take on this is that until you have real-time proving of ZK rollups, there's going to be some delay before you have finality with ZK. And so you need some optimistic either bonding system to get that immediate interop liquidity. And I think that's where optimistic will dominate, which is in contrast to today where like, the windows are, multiple days. Like now I think you'll see like liquidity-based systems. I don't know if I'd classify that as optimistic, but that are not ZK that allow you to do interop faster. So yeah.
All right, so yeah, I definitely agree with most of the points already said. I would take the stance definitely that overall for mere mortals, the inner workings of an optimistic rollup are, well, they don't require the domain knowledge of ZK, which is pretty much a particular topic in itself. And definitely, I do agree for sure that the kind of bugs that come out of ZK can be very hard to explain to a layperson, with the flip side being that verification is a lot easier in the ZK space. You don't have to follow the chain to be convinced it's correct. And I guess the point I'll make is that the basic economic game behind optimistic rollups is always a consideration. So I think there's a tool set for rollups. And if you consider the optimistic approach to ZK, you get stuff like naysayer proofs, where if you want to, most of the time, not actually verify proofs, only if somebody challenges it, then you get a little bit of optimism in ZK. So I think, as always, it's a set of tools.
To mention various things here. The first is that ZK, I agree that if you are trying to get inside the ZK box, it may be complex, but it's also a lot of difficulty if you are trying to check a signature, how it works, and it's a black box. So if you accept that ZK is a black box, a complex black box, but it's a black box, I think that ZK rollups, they are much easily conceptually than optimistic rollups. Optimistic rollups, I mean, they are based in the assumption that the blockchain is a real-time thing, and it's not a real time. And the way to convert something that's not real time with real time is just by delaying things. But it's not. So there is a lot of complexity. So I agree that there is a lot of complexity in the optimistic rollups. And ZK is, of course, then we need to go inside the ZK, the ZK box. Okay, and I agree. So ZK box are very complex compared to a signature. I mean, the ZK is something that's some orders of magnitude more complex. What's in there, at least in number of pieces that are in there. But here the good news is that the maturity that's getting this technology is improving a lot. I mean, still a lot of things to do. There are interesting things that are happening. I think that right now the VMs, people see that they are. Look, when I remember, for example, at the beginning when we created the ZK VM, we were talking with Linea people or with even maybe I think with ZK Sync people too. I mean, we were talking and trying to follow this idea of Vitalik of having two provers. That they prove the same thing, but if one was implemented wrong, then at least you have the other that at least can shut down the network. And by the time it was impossible, because when we were type 2s, the things were very different, and we are changing things, so and it was very difficult at the time. But now with the VMs, at the end you are just proving a Rust program there. The Rust program can be the same, but then the black box, the ZK, can be very different and can be differently implemented. So having this idea of having two proofs or two types of proof or three types of proof, this becomes now possible, at least much more than was 2-3 years ago, and this can improve security also on that side. And the other topic that I wanted to mention is also the improvement that we are doing in real time. So I think that right now, so thinking in doing a block proof in seconds is a reality today, and it's getting lower. So, and this also will simplify a lot of the ZK, because we will, I hope that at some point we stop introducing this optimistic thing because the proofs are so fast that, it's just pure ZK rollups.
Yeah, I think, yeah, I think that's a good point. I think, yeah, the proofs are so fast that it's just pure ZK rollups.
Yeah.
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 All right. So, yeah,
Just quickly on the backup for the ZK proof, ZK Sync does have TE proofs also, and so hopefully, like even if there's a bug somewhere deep in the cryptography, like the TE proof will catch it. But I think generally the point that hasn't been discussed yet is cost for user transactions. Like the overhead of running ZK proofs is still relatively high today compared to just the raw computation. And this is affected by most of the ZK rollups being like slightly more expensive than the optimistic rollups. I think ZK technology keeps getting like better and better, and I have a lot of faith that we actually will get it to be like as cheap or nearly as cheap as optimistic rollups. But for now, the like cost does affect end users, and that's a problem.
I have a quick reaction. Can you please say what the T in TEE acronym stands for?
Trusted execution environment.
I think you brought up an interesting point earlier, which was that people don't really care about fast finality. I think one thing that's interesting is, like, let's imagine a world over the next 2 years where, proving costs have dropped 10x year over year, like maybe even more. And it's interesting in that if I do actually think that fast finality is quite important. I know a couple folks who are like working on a protocol that's like on a rollup, and they've had multiple people that want to use their application tell them, hey, we can't use this because we don't want to bridge our money to a rollup where we have to keep it there for 7 days. And if they're moving enough size, they can't use a Cross or some bridge provider to get their money off of the rollup. And so I think in this transitory period, we're going to see that the proving costs are inherently going to be more than optimistic rollups. But if you can drive enough demand and the applications themselves are able to exist on the ZK rollup because they fundamentally can't on the optimistic rollup because people aren't willing to put their money into an optimistic rollup, then I think that cost is no longer as much of a concern. So I do think there's it's not just like, oh, cost is worse. There are actually better user experiences that come about from having ZK. And I'm sure you guys have seen this too. Yeah, I find that to be really interesting, at least. It's just like there's always some tension going on here. And I think the moral arguments to me for ZK, I personally resonate with. But I think it's very hard to make that compelling to an application. They care about getting users. Something that's very concrete is no one is ever going to complain about how they can't take the money off the rollup as a reason why they can't use your application.
So I think we've raised a few very interesting points about the improvement of user experience, right? Having a conversation about optimistic rollups versus ZK would have looked a lot different a couple years ago as we were waiting for 30 minutes for these proofs to generate on our desktops. So, of course, it seems like our panelists will all be very adept at explaining both types of rollups to their families over holiday dinners. But before we think about what these different technologies are going to look like together in the coming years, would love to drill down a little bit more on that UX question. We've talked about waiting periods. We've talked about finality. Are there other aspects of UX between these two approaches that you think are meaningful, whether for end users or even for the DevX of applications building on top, such as the folks you guys mentioned earlier who need to make money to have businesses?
So this is a loaded question. Here's the deal. When you're looking at rollups, the end user experience and UX that relates to this, it's like such a multifaceted kind of view that it doesn't boil down to only ZK versus optimistic, right? We have EVM equivalent or compatible zero-knowledge rollups, and we have completely different ones, right? They introduce new languages that are more suitable for proving in the ZK setting and so on. This obviously does impact the end user experience. You will not have the same tools, you will have different programming languages if you're a developer, you will probably have different wallets, and so on. And there are projects, some of them are sitting right here, who showed us that this is actually possible, right? And maybe there is a good chunk of people who actually doesn't mind, but there is a difference, and there will be a difference. Other than that, I think that the experience when it comes to rollups for the users, aside of those exits and all that, it actually might look very, very similar. So it's more about, what are you willing to interact with? Are you okay with the optimistic approach, or are you not okay with the optimistic approach and require ZK? The last thing that I will bring up is, it also depends what do you really consider to be a ZK rollup, right? We had a comment here from Aztec, which related to some client-side proof generation, right? Well, in that case, you probably will have to make sure that you have sufficiently strong hardware, which if, us engineers, we do our work properly, it will actually be a non-issue. So in the end, that user experience might be, rather similar.
I'm going to be a little bit controversial here again.
Perfect.
But
Let's hear it, Professor.
Look, probably UX is the worst enemy of decentralization. And let me explain. I mean, if you are trying to build an application and you prioritize UX, I tell you, you are going to sacrifice some sort of decentralization on there for sure. Because I mean, you want immediate things to happen. You want fast reaction. I mean, you want giving to the user, but there are things that are not possible yet. I mean, a consensus takes some time, and this goes against UX, whatever you do. So you need to deal with that. So when we talk about UX, I mean, of course, we need to do the things usable. I mean, if you want this technology to go to mainstream, we need UX, and I fully agree on this statement. But we cannot forget what we are building. At the moment that we are prioritizing, and when I'm saying prioritizing is that we are sacrificing the values of the community for the UX, I think that we are going against the community. But again, this is from the business perspective, probably that's the right way to go. I mean, if you are building a product and you want to sell a product, I tell you, you have to go for UX, for sure. But what we're building here?
Yeah, I'll push back some. I think maybe within the rollups, the UX is like not as obvious, but I think if you bring ZK to the application layer, like there's things that are infinitely better UX that only happen with ZK. So for example, ZK email, Clave wallet on ZK Sync is using it for, you can prove that you've sent a reset email to recover your account. So if you ever like lose your private keys, you just like ZK prove one email, just like a Web 2, like forgot your password reset, and like you can get your account back. There's no way to do like optimistic like email reset. Like it has to be ZK email. And so I think there's going to be a lot of cool things closer to like the user and application layer, where ZK is just like strictly better user experience.
I think that's also a great note to call out. There are some types of data, such as identity, for which an optimistic take is not sufficient. And so, very important for us to contemplate those use cases. Quick show of hands from our audience today. Have you guys ever opened up an app or a service and looked at the type of rollup it was built on and said, nah, don't dig this rollup, not gonna work for me? Is that a decision that you guys weigh in how you choose apps or services at all? Interesting. So it sounds like the thorough complexity and desire for our users to understand and make distinctions between them may not be as present. Sounds like also that the sacrifices around decentralization that, for example, enterprise chains built on optimistic rollup stacks are making right now are catering to that sort of apathy. As we look at the proliferation of so-called enterprise chains, right, the bases of the world, the unichains of the world, why are we not seeing enterprise ZKVMs? Or do we think that we will start to see more of them in the future as these improvements are readily available?
Soon.
Yeah. I mean, I think that in the case of Polygon, the aggregation layer, this is very much about that. This is, the ZK tech is very important for this, transferring these things. When we're talking before, some years ago, building an enterprise chain means building a L1 chain, which is, and you just join the word L1 and business, and then you will see that this is impossible thing. It's a difficult topic. So at this point, business, they don't need to build an L1. They can build an L2, and it can be a private L2, and this is going to be a normal thing that you will build in any of these aggregation layers that we are building.
Yeah, I think with ZKVMs, it's just a matter of maturity, because definitely when it comes to the Web 2 privacy model, it is very practical. And the idea that you kind of have some obscurity into the going-ons with a ZKVM can definitely turn off enterprises. But I do think to kind of harp on privacy, there is when it comes to enterprises using the blockchain, there definitely is a strong emphasis as we get mainstream adoption that businesses want privacy, and that is something that ZK enables.
So yeah, I think that's a really great call, is that businesses, operate in competitive environments. And the idea of disclosing the entirety of their order book or their client list to their competitors in a permissionless way is suboptimal to their bottom line. So if we think about that premise and how it might impact the sort of enterprise chain landscape, and Jordi, that's a great call out also. In 2017, we talked about enterprise chains as private permissioned L1s. And today they're inheriting security of other protocols and utilizing tools like zero-knowledge proofs. So as we contemplate the idea of change management, what would it look like for an optimistic chain to upgrade or to make this migration? And maybe Jordi, I'll pick on you because I know the Polygon POS has contemplated the future journey toward ZK EVM. So what does it mean to examine change management for a whole chain in this way?
It's a nightmare, I would say. It's the problem of migrating chains that they have a lot of volume, and we see that in Polygon, but we see it also in Ethereum every time that we do an upgrade, or probably in the other stacks. So when a stack has a lot of TVL or a lot of things that happens there, you need to be very careful when you upgrade and where you are doing things in there. So that's why that's why the things sometimes go slower. Development. Sometimes it's better to spin up a new chain that has less TVL and things, but at least you can play. And if you break it, it's less painful than if you are doing that. So that's one of the things, important things to consider. The other thing is that when you are upgrading things, it's important to understand this centralization. So this involves some sort of centralization. Upgrading a rollup, we go into a multi-sig again, or maybe you can put some time lock, which is okay. It's better than nothing, but it's some sort of centralization that goes there. If you think in the end game, in the end world, rollups should not be upgradable. They are just there. It's just. They don't belong to anybody. They just work, and people is using it. They are stable. For me, this is the end game. So all these, I would say, all this bootstrap, for me, this is part of bootstrapping something. One point that I want to, maybe I debate, because this is something that very worries me about, is that a protocol that starts centralized. When I mean centralized, I mean this multi-sig, upgradable, time lock, whatever. How hard is going to be to kill the multi-sig, or how it's going to be to so it's so I'm thinking like two scenarios. I would say if you just let the scenario go, I think that, so if you let the organizations that are building this to let it go, this will never happen. Because they have to destroy themselves somehow. So for me, the only hope is that there are some external reasons that force us to do that. Maybe there is some attack from some governments or for something that you cannot think, and then the only solution is, okay, let's decentralize, keep there, and then it's working. I hope when this happens, rollups are mature enough so that they can survive. But yeah, this is maybe it's a little early in the history to talk about that. Rollups are evolving, and ZK technology is evolving a lot, and maybe we're very early stage, but at some point we will have to talk about that.
Yeah, I just want to agree heavily on, for me, the bigger change and kind of the more you entrench centralization, the harder it is to move to a decentralized model. That's one reason Aztec is starting off with a decentralized model. I think that, as hard as it might be to move an optimistic rollup to a ZK rollup, and kind of in my opinion, once you start doing regular validity, and especially as ZK advances, I think they just basically become ZK rollups. But I think the bigger challenge in the rollup space, and in some ways rollups are kind of, they lend towards centralization because that's the easiest way to just piggyback off Ethereum. So I think that's a much more important transition and the harder one.
I think that's a great call out, though. Remember, upgrades are centralized. Hardware is centralized. Energy is centralized. Access to the internet is centralized. There are a lot of different aspects of this we need to be aware of. Go ahead.
Disagreement about upgrades being always centralized. So I also disagree with Jordi that rollups, might not be upgradable, that they just exist and whatever, right? Even if you have the most decentralized rollup out there, there is always a smart contract that the community or whoever is running the rollup agrees that this is that smart contract that we are rolling up the state, or maybe the proofs, and this is the DA that we are using. If there is a necessity for an upgrade, even in the most decentralized world, if everybody agrees that we are no longer going to be using this smart contract, we are going to be using this one, and it's also going to have a verifier with it, then you have upgraded your rollup, and you don't need any centralization. It's about the consensus.
Yeah, probably was not thinking on rollups as, a private chain is a rollup too, and it can be super centralized, but I was thinking more, and each rollup is, should be sovereign by themselves, and I fully agree on that, but I was thinking in rollups, let's say public rollups that don't belong to anybody by definition. It's like the thing. I was thinking on this kind of rollups, but I understand your point.
Do you have something else you wanted to add?
Yeah, I think we found that, or I think before, moving to a ZK stack for an optimistic rollup was infeasible, right? Like, especially when you make trade-offs on what type of EVM you're going for. That state migration is like tremendously difficult in a pain, right? Like, I'm sure that Polygon and ZK know this acutely. Asking someone to change their Merkle tree that they store all their state in is horrific. And one thing we've really prioritized is, I think this upgrade path is getting much easier, especially as, optimistic rollups. I think both Optimism and Arbitrum are aware of this, and they've designed their systems in such a way where it is flexible. For us, like, we recently launched this project called OP Succinct, which takes like any OP stack chain and converts it into a fully validity proven OP stack chain. And that upgrade path is like dead simple. You literally upgrade one contract that is storing the state roots. You modify one function. Basically, whenever you're posting the state root, you now post the state root and a proof. It verifies the proof, and you update the state root. So from the contract level, I think upgrading is quite easy. And these like external services you spin up to like generate proofs are also simple too. I think it's just that when you're thinking about having to upgrade with a different type of EVM, then it's bad. But now that I think type 1 proving is more computationally feasible, the costs are becoming lower, and as long as we keep going down that path, it's going to be quite easy to upgrade. And I don't think this like state migration problem will be as big of a thing anymore. That's at least my personal belief, is that, yeah, this is the direction everything's headed. I think upgrading will be easy. It's just going to be a question of, does that rollup want to make the trade-off today of, we want fast finality today because applications demand it today, or they're willing to pay the proving costs, which are going to go to near zero long term, right? So this is, yeah, I guess interesting.
All right, so as we move toward that long term, let's think the next 3 to 5 years out. Would love to check in on what that looks like. Are we happily coexisting with this diversity of stacks? Have we achieved that migration? Were there incentives involved to make some of those migrations happen? How do you guys think this is going to play out?
So my opinion is that we will coexist. The space is big. There is a lot of capital everywhere, and in the end, we sort of somehow agreed, maybe even involving the audience, that the users, in the end, some of them do not care about transacting on ZK versus optimistic rollup, right? And as long as we have enough of them, then yes, we will coexist, and it will make sense. So I think that we will coexist. At the same time, I think that the evolution of ZK rollups and ZK technologies in general will actually be speeding up. The point brought my friend here from Succinct is actually really, really valid. So up until this point, when we were developing zero-knowledge rollups and zero-knowledge technologies, we always had some application logic that we had to encode in some circuits, right? Be it Circom, be it Halo 2, be it something. If that logic changes, you suddenly need to make a change in your circuits, which sort of like brings a little bit more complexity to the table, more work, more development needed. When we come to these general VMs, that's no longer needed, right? Because in the end, you make your change in the logic, in the Rust program that you want it to have, then you compile it, and it keeps proving. It gives you a new verifier, the crypto system, right? And it keeps proving. You don't have to do any extra work. So I actually think that the rate of innovation will be increasing. The number of ZK rollups that we are going to see is also going to be increasing, but we will always coexist.
All right, inviting one or two more hot takes. How is this going to play out, guys?
I have a question for Porter and Jordi. Do you think this mechanism of the AG layer or ZK Sync paying chains will continue in 5 years? Like, Optimism has this approach today. It's mutually beneficial in some ways, but clearly there's a lot of grant money being thrown around to get chains to move on to a specific stack. What's the equilibrium of that, right? Like, everyone wants to bring a roll up onto, their layer. Like, what does that look like in 5 years? Because I imagine it's something that we think about a lot, where it's, it seems kind of unsustainable in some ways. How do you think it looks in 5 years? Like, are people going to be continuing to have these agreements from the foundation with roll-ups? Will that go away? Yeah.
I would say it's a matter of, it will depend very much on the friction for the composability between rollups. The way to scale, and this is, I've been thinking a lot on that, the way to scale is with many rollups. I mean, internet is a set of chains, a set of nets, and they are sovereign, each net is sovereign by itself. And blockchain is going to be, it needs to be very much like that. I mean, everybody should be able to build chains, and their chains are different in a sense, with different token, with different security things, with different block times, with different rules, gradability rules, with different, even the state transitions. So there is a space where each chain needs to be sovereign and needs to be a freedom on creating new chains on that. And everything matters, so the only thing that matters is how these chains communicate one each other. And the important part is the friction that there is in between this communication. Here ZK plays a huge role. I mean, having fast proofs is fundamental for achieving these fast and at the same time scalable. I mean, two chains can communicate fast, let's say relatively fast, if one chain follows the other. I mean, you need a commitment from the other chain and you need to follow the other chain. And this scale, I mean, if you have two chains, that's fine. But if you have thousands of chains and they are creating and destroying every time, you cannot spin a new server for each chain that's created. I mean, this model doesn't scale. Okay? So you need that each chain generate proofs, and this proof needs to be fast enough so that the funds of one chain, you can use it in the other chain. At the moment that you have a low friction, then having sovereignty, I mean, having these chains, that each chain is sovereign by itself, it's different. Chain can be, I mean, a scam chain that's running there. It can be a very powerful, a government chain, a private chain. I mean, it can be a very different kind of chains, and they have this common thing that communicate one each other. In the AG layer in Polygon, we are building this. You can see that if you want in the Ethereum ecosystem, or if you want it at the blockchain ecosystem. I mean, how networks communicate one each other. And it's just a matter of friction. Probably, if you want to communicate, I mean, if you want to do a smart contract that calls another smart contract inside the same chain, the friction is, let's call it 0, okay? If you are calling a smart contract that's in maybe in the AG layer chain, and the other chain, the friction probably is going to be much, so it's going to be very low. I mean, we're trying to minimize that, but we already need some connection there. If maybe one layer in the AG chain wants to call a network in the ZK Sync, it's going to be possible. Maybe we'll have to go through Ethereum, and maybe the friction is going to be a little bit higher. If you want to communicate maybe with some chain in Solana, you should be able to do it, but it probably is going to be even higher, this friction. But everything is about reducing this friction between chains. And again, the only tech, I mean, the tech that we need for that is the ZK tech.
Awesome, Porter. Take us home here. I'm about to get pulled off the stage. We're just about hitting time.
Definitely, yeah. The people I disagree with are most of crypto Twitter, who thinks that like all of the L2s won't be interoperable eventually. Like the same reason like you don't want to be on the internet and not be using TCP/IP. You don't want to be like on a separate L1. Like if you just isolate yourself too much in no man's land, then like no one's gonna want to interact. Like your rollup's not gonna be connected to everyone else. For now, I think it's good that we have like Polygon AgLayer and like zkSync and other teams like trying different interoperability approaches. I think it's good to experiment, but to me, it's super obvious that like the 5-year vision is we're all going to have like interoperability together, and that's definitely going to happen.
Porter, thank you so much. This is a great reminder. Everybody, you cannot have a blockchain by yourself in a corner. That is a database. So whether it is optimistic, whether it is a ZK rollup, we all look forward to supporting you in your adventures on chain. Thanks again to our host today, and I think that is all for our panel.
Okay. Okay, that's super amazing. Thank you so much. You did lovely. You did lovely. Thank you so much, everyone. Please a round of applause again for them. A round of applause, please. Thank you. Thank you. Thank you. That was an enjoyable panelist session, and I had a swell time just listening to them debate, and it was beautiful to see. So we have to go into the next thing on the agenda, and we have a solo presentation by Elias Tazates, the CEO and co-founder of Kakarot. Please, a round of applause for him as he walks up on stage to do the presentation. A round of applause, please. Thank you. All right, awesome.
Test. Okay, cool. Hey guys, thanks for being here. My name's Elias. I work at Kakarot. Today we're going to talk about scaling blockchain with ZK and EVM. I think at least it is when we are talking to between crypto native people, this is a subject that we quite agree on. So I'm going to try and make it more palpable and tangible. I would say we all agree that ZK helps blockchain scale, and then blockchain helps Internet of Value get into a new age. Okay. Oop, I double clicked. Okay, so this is kind of the thesis: is all software will be probably secure. This is good for scaling and security, and then blockchains might become the world settlement layer. So for the little story, I don't know, who has read here the roadmap of Ethereum? Okay. There is kind of like a end state of Ethereum where the entire network kind of relies on ZK for, I would say, the final stage of full scalability, where kind of every transaction is proven and uses ZK for settlement and also security. And this is where we get the 100,000s of TPS that, if you think about it, allows us to absorb existing systems, and we're going to see it later. The vision is kind of that there is a broader scalability landscape. As you can see, there can be alt L1s, rollups, validiums, even non-EVM rollups, and they are all connected by ZK. I think actually Jordi Bailina just touched on this in the previous panel, so for those who were here, ZK really allows for this frictionless interop between chains. And this is how kind of you get this patchwork or this fabric of trust infrastructures, yeah. So why EVM? Ooh, that was a lot. Okay, I've been told that there are magnetic. Can we go back to the beginning, please? I think magnetic waves are getting lost in the midst. So what you have seen now is all the things I've pressed from the beginning. Okay. Okay, all good. So Why EVM? I think we're entering soon into alt VM season, and it's good to. I think alt VMs have a play to make. So who here know what alt VM means, like the concept? Okay, so EVM is the standard in blockchain. It just means Ethereum Virtual Machine. It is the standard for smart contracts and applications on Ethereum and Arbitrum, Optimism, and all the Ethereum equivalent chains. When you say alt VM, what you really mean is anything that deviates from the standard. So panelists before were from Aleo. This is alt VM. What else? Starknet, Move, Aptos, Sui. These are all considered alt VM. Solana. And EVM, if you want more numbers to make it more tangible, 87% of all devs in crypto work in EVM. And then more than 95% of stablecoins live on EVM chains. So EVM is the standard. There are many challengers to the standard, but what's good to take into mind is like the hype cycles are very, I would say, volatile, but EVM is a standard that's here to stay. And what does ZK bring? So ZK brings fast finality, as mentioned again by our former panelist. Fast finality is really important when you're trying to make multiple chains, dozens of chains interop. Lower security costs. There is no attack on ZK like proof systems that there are no equivalent attack on ZK proof system that you could have on OP stack optimistic sense of finality, and then scalability. So ZK really compresses computation, and this is very powerful for just scaling infrastructure to hundreds of thousands of TPS in order to absorb the Web 2, I would say Web 2 use cases like payment, store value, NASDAQ, S&P, all of these structures can be kind of brought on-chain over the next decade. So what is the next step kind of for ZK adoption? I believe we are starting to see more and more OP rollups talking about transitioning to ZK. Currently, only 25% of live rollups are ZK. 75% of them are OP. And I believe that in the next 3 years, we're going to see a shift towards more 100% of ZK rollups. Not only because we have created this narrative that ZK is better, kind of as a black box, just ZK everything, but mainly because it is going to be both more secure, have less friction, and also cost less money. So I think ZK rollups will become the default in all rollup as a service providers. And then the end game is really that ZK gets adopted on L1. This is what I mentioned in the beginning of the talk, but the end goal for Ethereum is to become a settlement layer where nothing else than proofs are verified. And why do you want this? You want this because once proof systems become very mature, having only proofs being verified does not hurt security, but it tenfolds scalability. And why would you want this? We're going to get this into a second, but let's just look at some numbers. We're doing projections, so of course it's all by conjecture, but this is roughly reasonable, is to say that if there are 100 rollups now, and transactions continue to grow, and rollups number continue to grow as well, we could have 500 billion transactions to prove every year. This is not, you could get to the same number in many different ways. So you could say, oh, I don't believe there's going to be 2,000 rollups in 3 years. I actually believe that there's going to be 5. But then those 5 rollups are going to have 10,000 TPS, and then you would fall back on those like 500 billion transactions per year. And why this number is simply to say these transactions are going to be dominantly EVM transactions. Maybe over the years, the number is going to have more like balance between Solana transactions, Starknet transactions, alt VM transactions in general. But regardless, there's going to be hundreds of billions of transactions that are going to need proving. This is why I think you've seen this year, 2024, but going hard into 2025, the next piece of infrastructure that is getting pushed are prover networks. Gavilot, Fermat, Sindri, Sejic, I saw many of them, ReZero, Succinct. And why? Because everyone is seeing that you are going to have very soon, in 10 years, 20 years, at least it's our belief as a community, that there are going to be trillions of transactions and they are going to need like nanocent proving costs and real-time proving. You need ZK to become completely invisible such that it doesn't become a hype narrative anymore. It just becomes a technology in the background. So is this sufficient actually? Like, why would you want even 500 billion transactions? So stocks of NASDAQ trades per year is 10 billion. Futures, so all the securities there are 130 billion of them. Payments, there's 260 billion payments per year of Visa. So this is just orders of magnitude, but you're seeing that 500 billion transactions is not ridiculous. It's actually completely reasonable, if not enough. Cross-border transfers, which is arguably one of the best use case for crypto, essentially because cross-border payments right now are so costly. Even for us today as a company, Kakaot, transferring from France to US costs us over $50. So even L1 during DeFi summer would have been more suitable. So even if you assume something quite conservative, like 10% of Web 2, we get 10% maybe of the equivalent adoption of Web 2 payments and DeFi services that I just described on-chain. You are getting the orders of magnitude needed to get to the numbers I've mentioned. So this 500 billion by 2030. So what do you get from it? Again, you get scalability. And what does it really mean, scalability? It means scalability knowing that you're not in a centralized, obfuscated network. So of course you can get to these levels of scalability if you have a central database and you are the Federal Central Bank or the European Central Bank or maybe like JP Morgan or the S&P 500, because you have servers and you don't need this kind of transparency. You get instant finality and also you get strong network effects. So you get very sweet interop between networks. So I guess what you really get compared to Web 2 today, it's not only speed, because speed we actually have to match, is more openness and composability. So it's not so easy to compose stocks from many countries, but it's even harder to compose AI from different countries. I can only speak for France, because that's the only example I know, but many companies, so AI companies, Mistral, for example, is one, which raised $1 billion last year. They are developing AI models that are catered to the French state, and it's an idea of sovereignty. So very soon, countries are going to close kind of their borders of data, and they're going to want to train their own models, and you're going to see the internet kind of close up. And as we see more and more, trust is I would say this trust graph is trending towards zero. The internet is already fragmented, but when you really look, we have FANG in the US and maybe Europe, but when you go to other countries, they don't have FANG, they don't have Facebook, they don't have these kind of companies, they have their own, the likes of WeChat and so on and so forth. So if crypto doesn't get more adoption, my belief is that we're going to go towards a siloed internet that has very, very little interop, and the lesser the interop, the lesser the innovation. This is my strong belief. So what is Kakaot doing? This is bit of my shield slide, but I realized I didn't start the presentation by presenting myself. So I'm Elias. Kakaot, we've been working for the past year and a half on proving EVM. What does it really mean? It means we wrote a provable EVM. What can you do with it? You can replay transactions that have been executed on EVM chains, Scroll, Taiko, Optimism, Arbitrum, and then output a proof. You can also deliver this software to Starknet, which is what we're doing. And at the end of the day, what does this do? It accelerates the penetration of ZK in the land of Ethereum. And this is what we all want. So this is kind of my map. Some would argue that it's not completely true. I agree with this map, essentially because I think it's an interesting angle to look at agility of code bases and efficiency. Who is familiar with the trade-off between ZK VMs and circuits? I guess this is the the point of the. I mean, no, there are many subjects in this presentation. Sorry, in these past days about ZK VMs, and etc. TLDR is circuits are the lowest level primitives that you can use to prove compute, and ZK VMs are the higher ones. So to write circuits, you need to be kind of a cryptographer to some extent. To write ZK VMs programs, you need to be an engineer, and a ZK cognizant engineer. And so what I argue is RISC-V proving, so SP1, RISC-0, are the more agile, lightweight versions because you don't need to be a cryptographer and you don't need to write DSLs. And then down you have circuits. And then I argue that Starkware's cryptography is the most performant out of all the things I have named in terms of both agility and performance. So it's our sweet spot. It's our sweet spot for the last 2 years. And yeah, I think really the next frontier for ZK, at least for proving for scalability, is the 10x cheaper. 10x cheaper every year. I think this is the only blocker. 10x cheaper, and then just adoption with regards to infrastructure, as our last panelist mentioned. Thank you very much.
Awesome. Thank you so much. Thank you. All right, so we have to go into the next one. Thank you so much, Elias. I did enjoy that presentation. So we have Kobe Dolan and Dennis of One Labs in the building. So Kobe, can you do the honors of joining me on stage? Please a round of applause for Kobe, if your hands are not too busy. Thank you. All right, Kobe, you have the stage.
Thank you. Hey everyone, I'm Kobe. I'm a team lead at ON Labs on the exploration team. So we're kind of like DevRel and product focused, and I'm going to share with you today some stuff about what we're building, and then we actually have a builder here who's going to share what he's building with our tools. So who are we at ON Labs? We are a blockchain company. We're making provable, programmable cryptography technology, so a lot of ZK proofs. I work mostly on the ONJS SDK, and we have some other things as well. We built the Mina blockchain, and we're also working on an O1 VM. So we have a little bit of both, a little bit of circuits and a little bit of ZK VMs. So Mina, kind of our most well-known product. What is it? It's the world's lightest weight blockchain. So it's basically a blockchain layer 1 that ZK proves transactions and keeps a state proof that's up to date without making network participants hold lots of storage at like an ever-growing rate. So it makes it easier for regular people to participate in the network. The succinctness using ZK proofs makes it scalable and trustless, so easy for users to get involved. And it's powered by ZK Snarks. That's sort of the technology that enables this property. And just to sort of set the stage, I think people understand how Ethereum works. You submit a function and call data, and then the nodes in the network execute that function for you. And they agree on the output of the function, and that's how the network reaches consensus about state. But on Mina, what you do is a user will run their own proof, they'll upload the proof to the network, and the network simply verifies the proof and comes to consensus about that. So for a really cheap Ethereum transaction, there's kind of no difference. But where you get value is like a lot of off-chain computation rolled into one single proof with a fixed cost verification time enables some cool use cases that would either be really expensive with gas on Ethereum or maybe even over the gas limit completely. So we basically achieved this succinct blockchain, and with users running their own proofs, you also get these privacy and off-chain execution properties that are quite nice. And so let's explore ONJS. ONJS is a TypeScript SDK for writing ZK circuits. It's quite easy, it's quite nice for engineering ZK aware engineers, I think. And the proofs that you write, the circuits that you compile with ONJS are sort of compatible with the Mina blockchain. So it enables programmable smart contracts in the ZK blockchain ecosystem. What I really love about ONJS is that we say that it's literally just TypeScript. You know, take that with an asterisk, but it's compatible with all of your favorite kind of TypeScript tooling. Like we're leveraging this really mature TypeScript ecosystem and empowering, you know, ZK devs to have that kind of tooling. And we have sort of a standard library for ZK developers as well. From the ZK circuit side, we have a lot of cool, we call them custom gadgets, like more high-level gates than just add in multiplication. And we have like data types that are useful for engineers, like unsigned integers. We have Booleans, you know, et cetera, so you're not just working with fields everywhere. We have Poseidon and native signatures, which I'll get into later actually, but it's the Schnorr signature over the pasta curves. That's our sort of signature scheme. And then what we also have more recently, which is really exciting, is more like foreign field arithmetic. So we can bring other types of cryptography into our, you know, sort of ZK proof system. So for instance, we can do ECDSA and Keccak, and we can sort of verify Ethereum stuff with Mina, which is really cool. And of course, we're building. So, you know, in the world of ZK circuits, there's certain programming paradigms that people would like to have that are difficult to support. One common one that we get from developers is like a runtime lookup way of working, you know, not just knowing exactly what your data will be before you get it, but at runtime accessing something dynamically. We're working on that. You know, I don't want to give a date, but we're working on it. And then the other thing that ONJS ships with is protocol features for Mina. So it sort of natively knows how to interact with the Mina blockchain, submit proofs, update smart contract state. We have something called account updates, so it can sort of do balance transfers, and it knows how to speak to Mina. That's the thing. And ZK program is what we call our abstraction for circuits. So I know that the code behind me is going to be quite small, but oh boy. But I'm going to get into like a really small code example, just sort of demonstrate how sort of easy it is to get up and running. So the example project that, you know, I wrote is like a signature verifier in ONJS, so you can prove that a given Ethereum signature is valid. My motivation for this is, you know, in the past when we've given talks like this, we kind of keep all of our stuff in the world of ONJS and Mina. And it's, you know, it's cool, you can build something that talks to something else in Mina, but not a lot of people are on Mina, everyone's on Ethereum. So with this story that we want to tell about programmable cryptography, part of that is bringing the rest of the crypto world, and not just crypto, but Web 2 cryptography into, you know, our ZK provable world. So, like I was saying, the Schnorr signature over pasta curves is like what Mina uses, but Ethereum uses Keccak, and SHA-256 is common, and there's these other schemes. So could we prove execution of one of those crypto schemes in ONJS? The next slide is going to be sort of the imports and just getting the classes set up for building a ZK program. So this is, we're going to build like a ZK circuit using our DSL, and some interesting things that like we've shipped this year are like a foreign curve and ECDSA and a bytes data type, and these types of things are all wrapped in fields, wrapped in ZK in the ONJS library, but they're exposed to developers in like these nice high-level abstractions. And then the next slide will be sort of, this is like the declarative syntax of how we approach a ZK circuit. So they have a name that's basically just used for debugging stack traces. But sort of critically, they have a public input and a public output, and that's what's visible about the proof going in and what's proved by the proof coming out. And then it has a list of methods as well, which the next slide will be in greater detail. So, so the only method that this ZK program will have, and it can have multiple methods. It's sort of, each method is its own circuit, and then the program is a circuit that wraps the other circuits. So that's what the abstraction does for you. But in this case, we have verify signature. The public input that we defined earlier was actually the message, like the bytes that we're claiming have been signed. The private inputs in this case are the signature data and the public key that signed it. That's sort of an arbitrary choice, but it goes to show you that you as the developer can decide like what's visible to the public world and what's hidden from the public world, and you can prove the things that you feel like you want to prove and selectively reveal what you want to selectively reveal. And actually, it's quite a simple function. All we're doing is calling this method that we exposed by ONJS called verify ethers, which returns true if the signature is valid and false if it's not. So that's a ZK circuit. And getting back to like leveraging the mature TypeScript ecosystem, what's really cool about this is that you can just write like vtest tests, or you can write jest tests to confirm that your circuits are behaving appropriately. So kind of the way this works is ONJS will run the TypeScript code and it'll test that. And if that passes, it'll move on to executing the circuit, which actually happens in like WASM. So the hardcore ZK stuff is written in Rust and it's just exposed in TypeScript. But that will execute second, and if that passes, then TypeScript will say, okay, it worked. So in this case, we can generate a proof, and then we can expect that the proof's public output is true because it's supposed to be true, and it's quite easy. And then I would be remiss to not share with you the concept of recursion. So, ZK circuits are really cool, and you can do this interesting stuff, and maybe it's quite easy to write in ONJS. But in order to make it work with more use cases, maybe more complex use cases, maybe things that need to be shared between different parties, not just one prover, we can add recursion. So in this example, I've added a new method, which is a base case, and I've changed the public output from a Boolean to an unsigned integer, which will be like a count of how many valid signatures have we verified ever. So the first time we run it in the base case, it will either return 0 or 1, depending on whether the first signature is valid. But then going forward, we can introduce the concept of a self-proof. So it's like a proof of the same shape as the proof that we're currently in, and we can verify previous proofs. So after you do the base case, then you can pass in that base case proof to do this recursive proof. So we call it verify signature again. The private inputs are the previous proof, the signature data, and the public key. And then basically the only thing we change in the code is first we need to verify the previous proof, then we need to access its public output, and that's the previous count of how many times we've verified the thing. And then we increment that, or we don't increment it depending on whether the signature is valid, and we return a new public output, and that has now sort of baked in both proofs, and we can keep doing that ad infinitum to maybe do more interesting, complex stuff. So kind of other use cases that we're interested in. Games. I think ZK for games is really cool, especially in like a nascent developer ecosystem where you're not putting user funds at risk. You're not, maybe putting too much stuff at risk, but you're having fun with it. ZK identity and credentials is quite a cool use case that's pretty close. That could be a little bit more serious and interesting to like enterprise type things. DeFi and oracles. I guess the key insight there is like like replacing signatures with proofs, but sometimes the proofs are just proof of signatures. So, maybe there's just some scalability stuff there. And then rollups infrastructure, that's something that at Owen Labs we've seen a lot of people using our tools for. Not necessarily in the Ethereum ecosystem, but like infrastructure for Mina, because Mina has this, rollup proof aggregation technology built in. It makes it quite nice to build an aggregator and then settle to Mina. And then, just privacy stuff in general. Anything that can be done on-chain with ZK proofs, now you can sort of selectively prove that type of execution and share that maybe something is true, but you don't know who the participants were, or you know that a participant participated in something, but you don't know in which capacity they participated, things like that. And now I'd like to bring on Dennis from Astromina, one of our community builders, who is going to tell you about something he's building with our tools. Thanks, Dennis.
Thanks, Kobe. So as we know, one of the biggest issues in crypto is interoperability, and with the emerging tech like zero knowledge proofs, we are going more towards the pink side, hopefully, and we have been seeing a lot of zkVM integrations with on-chain light clients, and recently Geometry Research, they basically integrated Celestia Blockstream on Mina, which enabled verifying SP1, RISC-0, Groth16 proofs on Mina, and we realized zkVM light clients could be utilized for having interoperability from Ethereum to Mina and basically enabling state bridging so that you can verify any kind of on-chain state data you want on Mina. And so ours is on the light clients and relay side, which is for now the most trusted side. And so the way, you can, and okay. So the way the state bridge currently we are implementing works is we just get a KZG plonk for the Ethereum's beacon chain state root execution, and we verify that on Mina with O1JS. And the way we verify it is using the work done by Geometry Research by converting the KZG plonk proofs to Kimchi proofs and having the Ethereum state root as a public output. And once a user wants to prove any kind of data they want from Ethereum to Mina, what they do is they just get a Merkle-Patricia tree of that storage slot, and they just reconstruct the Merkle root, and we compare it with the verified one in the circuits, so that they can verify their NFTs, fungible tokens, their proof of humanity, or any kind of other use cases like this. And thanks to the work done by O1 Labs, we are really looking forward to use especially O1 VM, because it will enable us to just generate proofs for each block, and then using folding schemes or infinite recursion, it will be possible to just have them in a single proof so that we can verify in a more optimized and efficient and performant way.
Nice.
Thank you, Kobe.
And that's our talk. Oh, hey, Connor. Thank you. Oh, questions? Yeah.
Thanks for the talk. Can you verify? You mentioned succinct or something.
Yeah.
What type of verifier does Mina have? Can you verify anything, or must it have been written in O1JS?
So Mina's proof system is currently called Kimchi, which uses pasta curves, Pallas and Vesta. So I would say it's pretty optimized for infinite recursion, so that it's kind of different from the other current proof systems. And this means the current the way you can just do conversion is the only way you can verify other proof system is just by doing conversion, and this includes SP1 proofs, RISC-0 proofs, Groth16 proofs, and basically GNARC-based KZG plonks and also Groth16.
So you could take a proof that Scroll is about to submit to L1 because they wrap it in a Groth16. You verify this proof in Kimchi, and then you settle on Mina.
Yep.
So you could technically have any VM on Mina. You could technically have kind of a infinite amount of rollups on Mina. You don't have to choose a VM.
Yep.
Yeah.
Okay.
And you can settle, for example, Kakarot as well to Mina. So yeah, but I would say proof conversion could be optimized, but it's possible for sure, yeah.
Yeah, so I'll speak a little bit more on that. Specifically what we're referencing is this work that was delivered by Geometry Research. They did like some work for us to prove Celestia data inclusion on Mina. And part of that work is, basically taking what already exists for proving things on Celestia, like an SP1 blob stream proof. And then they wrote the verifier in OpenJS for that proof. So you would have to, like for something other than Grot16 or the versions of Plonk that this deliverable supports, you'd have to write your own. But like, of course, it's theoretically possible to write a verifier for any other proof system, like you can in Solidity as well.
And yeah, well, for Kakarot use example, for Celestia integration, they basically used SP1 with Tendermint Lite clients. So as you mentioned, Cat, like Kakarot, EAT, in your presentation, that could be also utilized in this way.
I guess someone would have to write a Stark verifier in Kimchi, but I guess that could
But
be fun.
Starks also could be wrapped to Snarks.
Yeah, true, actually. And also, I had one last question on your Lightbridge. How do you verify finality on Ethereum, like the 12-minute?
So there are like multiple approaches we take. So one of them is just, from the beacon chain, we just get the finalized blocks, and that's how we just verify like BLS signatures. And also we are planning to just basically, wait for a bit of blocks like appended on that block to make sure, like double check. Yeah.
Thanks for the question.
Thank you.
Okay, that's super amazing. Is that all the question? Yeah. Okay. Please, thank you so much. Thank you so much. Such an amazing session with O1 Labs. So currently we just a minute. Okay, so currently we are on schedule. So we'll be taking like a very short break, a very, very short break. So don't go anywhere. Just give us like a few minutes. We'll be right back. So for now, just listen to good music and have so much fun, because we'll be right back with so much more to offer. Thank you. Okay, so I was enjoying that music there for a minute, and it was so nice. Up next, we have Mr. Pavel, who would be doing a presentation on consideration for the entangled rollup liquidity optimization. So please, a round of applause for Mr. Pavel.
All right.
Thank you.
Thank you. All right. So this is going to be a lightning talk. Typically, this talk is going on for a little bit longer than 40 minutes, so I'll try to keep it condensed. But yeah, I'll have all the slides and everything posted later on my website as well. My name is Pavel. I worked in the Metis ecosystem for 3 years. I worked in business development and as the integrations lead, and then moved on to be developer relations lead for ZKM. A lot of my experience has been practical, taking what aspects and designs and research of the blockchain space and trying to find use cases and business use cases that essentially can be applied practically. So with that mindset, I want to present ZKM. But before I present ZKM, I want to define settlement. So settlement is the state of finalizing a transaction where the transaction is not able to be reverted. So we take a look at Kraken. Kraken has a list of different finalization parameters. Over here, I don't know if it's a little bit small, but we have Ethereum proof of work, and then we have Ethereum network, and the different networks and the different estimated time for gaining the essentially the assets that you deposit into the Kraken smart contract. You will only get that after a certain period. And as we see with Ethereum proof of work, the most recent fork of Ethereum when Ethereum migrated to proof of stake, that it takes roughly 3 to 4 days for finalization to occur. Versus Ethereum network now, it takes roughly around 14 minutes. So there's these big gaps between these different types of networks. So, and then in this case, this is to prevent things like a double spend or essentially the potential reversal of a transaction. So the idea of universal settlement is where any computation can be executed by one blockchain, and the results of that execution can be resolved to any other blockchain. So the idea of the entangled rollup is a way to trustlessly pass messages from one chain to a different one. So this is the overall diagram of the entangled rollup, but the main and core idea that I want to emphasize is the idea of the universal settlement network, where we can connect the different types of networks that are present and essentially connect them as adapters to different types of potentially incompatible VMs. So we have different types of VMs. You know, Ethereum is EVM. We also have Movement. We have Solana. We have other different VMs. But the idea is that a universal L2 can essentially plug in and act as a means to transfer different types of assets in a unified way. And so there's a very quick scenario, but I'll basically run through a lot of these slides as we go. But the idea is Alice wants to transfer 100 USDT to Bob from Ethereum to Avalanche. And she wants these 3 characteristics of her bridge. She wants it trustless, extensible, and liquidity optimized. And this is the third part is the idea of this the idea of entangled rollup for liquidity optimization. So I'm just going to skip some of the this overall ideas, but the ideas behind bridges is we have externally verified bridges, which essentially depend on an external set of verifiers. And what this means is that it's achieved consensus through those verifiers and not by the security of the base chain that they are deriving, that they're actually sending assets to. So I'm dependent on a variety of different validators, but not on the main chain that I'm actually interacting. So I'm not inheriting the security of the main chain whenever I use externally verified bridges. So externally verified bridges have high security assumptions. The idea of layer 2s, the idea of natively verified bridges. So we have different types of natively verified bridges where the different types of, where the layer 2s are essentially taking the security of Ethereum or the security of the base chain and their validator set and using it, using the layer 2s as a form of an execution client. And then the base chain is used as a consensus to achieve consensus and settlements over the transactions. So the idea is there is a native bridge where there's a native mint function that occurs, and they're essentially minted and burned on the L2, and tokens are unlocked and locked on the L1. So what if we can combine both the externally verified or like the idea of the externally verified where it's super extensible, but also natively verified where we have the security of the base chain. So the concept of ZK bridges, we take a batch of transactions, execute them off chain, then post a proof of that execution on layer 1, and essentially proving that the execution did in fact happen and it was correct. So then we have the entangled rollup overview. So the whole idea of the entangled rollup is to use layer 2 as an adapter. And ZK proofs are a method of communicating between these different types of adapters. And so for liquidity optimization, the idea behind this network is that anytime anyone deposits into any L2 that's connected via this liquidity network or the universal L2, is that all of the network would increase in their liquidity. And what does that mean? So if I deposit millions of dollars into the universal L2 on Ethereum, so the unified native liquidity of the entire ecosystem of different universal L2s also increases because I'm able to transfer that liquidity from different chains very easily within this type of structure. So essentially, anytime that I add liquidity to one of these universal L2s, I can come in and use it across all of these universal L2s. So the overall idea is taking a deposit to Ethereum to the universal L2. Then we can, how we actually transfer the liquidity is we can burn that corresponding amount of asset on that layer 2 to the burn address. It can be a public burn address, but also a private burn address, introducing a form of privacy as well to send it across different types of these universal L2s, and that's a different type of extension. But this is just for liquidity optimization, so I'll just talk about that. The burn of that gets sent to the burn address. I generate a ZK proof that the tokens were in fact burned, and as a result, I can take that proof and leverage the native mint function of that L2 as a means to mint a corresponding amount of USDT or any other type of asset that's natively available by that L2. And again, this is native USDT because we're leveraging the mint function of that L2 that's connected via this universal L2 system. So essentially, we're able to take the assets that we have and we're able to, in no way we duplicate this, but we're able to essentially show that we burned these assets on one layer 2 and are able to mint those corresponding amount of native assets using the native L2 mint function. And these are one-to-one with each other. I don't need to have a wrapped version where I need to then swap it to the native version. This is native USDT. This is what the whole concept is. And so simplifying that user experience. And the idea is we can also take not just 100 USDT because it might be, a very small amount. Maybe this is better for like intents for having these small amounts. But we're talking about maybe multiple millions of dollars that we can actually pass through these different types of layer 2s that would then be able to essentially transfer millions of dollars without requiring a counterparty to facilitate that transfer. So I don't need to rely on a liquidity provider in order to provide that liquidity. I can essentially transfer it across different L2s. And what we're seeing with app chains is that one of the leading problems is fragmentation. We can't use assets from one layer 2 to a different layer 2 without requiring this, these different types of connectors. So the idea is, why don't we just create a system where we can facilitate large amounts of transfers using both ZK proofs as well as leveraging the native mint function on these layer 2s. So the idea is that It's trustless, where we don't depend on third-party validation, because we are still interacting with the base layer 2. It's also interoperable. This system can work with EVM and potentially non-EVM solutions. Depending on the structure, these universal L2s can be all EVM compatible, and as a result, this system can all be a unified system. But also, within a ZKVM, you can also prove interactions happen without the layer 2 needing to be fully EVM as well. So they can also be different VMs on that layer 2. So the idea is that I can still use this type of system even if my layer 2 is a different VM. Then the third point, it's liquidity optimized. The idea is that any bridged funds that enter the network can be used across all the networks that are produced. And finally, we see layer 2 scalability benefits. People, right now, there's billions of dollars locked in layer 2s. And as a result, people want to go to layer 2s because they provide a cheaper and more scalable way to interact. And so where we're seeing more and more layer 2s being adopted, that leads to more and more fragmentation. And so people want to stay on layer 2s, but people also want to interact with different networks of different layer 2s as well. So we want to essentially facilitate this across different networks, across different blockchains as well, using layer 2s as an adapter. So there are two major cons. One is that we need the support of the native mint function of the bridge. So the of the layer 2. So existing layer 2s potentially, based on this technology is still very new, very research driven. In order for this to be adopted, likely there would need to be some battle tested and secured way to basically guarantee that an arbitrary amount of funds can't be minted. Right now, the only way to mint assets on a native layer 2 is if you deposit those assets on a layer 1, which then is able to be minted on that layer 2. In this case, we're extending the mint function to also accept ZK proofs, which then allows the minting of any arbitrary amount, which is definitely a big risk factor. We also see that within this structure, if I deposit, let's say, $100 million on Ethereum, and then transfer to the Universal L2 on Ethereum, and then transfer it to Solana, well, let's say Solana doesn't have $100 million of liquidity directly on the L1, I'm not able to withdraw it on Solana. But that doesn't mean that the money's gone. That means I can actually transfer it back to the Universal L2 on Ethereum and still redeem it. The idea is that we can still redeem, the assets are still backed one-to-one with those same assets. They're just on different networks. So if we think of blockchains as just a type of consensus, all we're doing is we are leveraging the consensus verification of the base L1 with the ability to transfer to different networks, even if, and still use that liquidity, even if on that base L1 there isn't that liquidity backing. But within the universal L2 ecosystem, there still is that liquidity. It just might not be on the chain or on the L2, or sorry, on the L1 that you are on the L2 for. You could still withdraw on Ethereum. So that's the main idea, and definitely always looking for feedback related to this. And I think I'm on time, but we're dealing with different research problems or research areas. So including decentralized relays where I want to post transactions reliably without potentially needing an intermediary or third party. How do I do this with redundancy? There's also VM interoperability. How do I exactly move assets from EVM to non-EVM chains in a secured fashion. So, and then the finality parameters, how do I make sure and guarantee that I can include many different L1s within this system, but still retain the full security advantages of these consensus models? So is there a way that we can do dynamic consensus based on the L1 that gets added into the universal L2 structure? Is there maybe an Aave type mechanism where chains essentially need to be added on in order to be used? How we see, or at least how I see this model being adapted, is very similar to Aave, where you have a basket of different assets, and then those assets can be used to loan out against other assets. We can see the same thing of chains being added into this system, where certain chains can have the ability to mint, while other chains might not be. So all of these are all considerations, all plans, research initiatives for the future. And definitely, if you're interested in exploring this area of research in terms of cross-chain interoperability and seeing the different ways that we can leverage the security of blockchains, but still be able to use them for different use cases, such as liquidity optimization, definitely would consider visiting the website and seeing ways we can facilitate contributions, I guess. And yeah, thank you.
Okay, a round of applause for him, please, if you're in the building. Hello, a round of applause. Thank you, thank you, thank you. That was a wonderful presentation, Pavel. Thank you so much. Thank you so much for that. Okay, so without further ado, we'll get to the next agenda on today's list. And we do have an interesting session with the beautiful White Z. Sorry. We do have an interesting session with Alice. And please, if you don't know Alice, she is beautiful. She's energetic. She is really, really amazing. So Alice, do come up on stage with me. Do come. Come say hello to everybody before you get started.
For the intro. Hi, everyone. Thank you all for attending. I'm very excited to be interviewing Porter here today.
Okay, amazing. I'll be leaving the stage for them to do the amazing stuff. So you have the stage, Alice.
Thank you so much.
Hello.
Hi, everyone. Yeah, thank you so much for the intro, and very excited to be interviewing Porter here today, who's a core contributor at Matter Labs. So thank you so much, Porter. And I'm wondering, just as a first question, if you could give an introduction of yourself. So maybe your origin story of how you got into the Web3 and the ZK spaces.
Yeah. So it actually started when I was pretty little. I thought that like one of the coolest things you could do was like codes and code breaking. And so I got very into cryptography like just as a kid. I would watch like the World War II movies and cheer for Alan Turing and like breaking the Enigma. And I was like, if I could do that full time, I would do that. And yeah, it finally, like I had a few career changes and eventually made it to Matter Labs, where I started on the security team, like finding all of the bugs in our ZK for ZK Sync, which was a very fun, like perfect role for me. So that was awesome. And then recently I've switched because we need much more help on like the marketing and like DevRel side. And so now I'm like doing more of like talking to the ecosystem about all of ZK Sync's cool tech.
Nice, and yeah, The Imitation Game is actually one of my favorite movies, so really relate to that. But yeah, that's awesome to hear. And just wondering, because now that you're also focused on and ZK Sync as well is focused a lot on the dev experience, I'm wondering if you can bring some light into some of the main challenges that come with developer adoption and why we haven't seen as much mainstream adoption with ZK specifically for developers.
Yeah, I think it's been tricky. Like there were actually predictions from like Dan Benet at Stanford that like it would take like a decade before like ZK like EVMs would be ready, and turns out like they came much sooner than anyone expected. And at least for ZK Sync, like when we were originally building this thing, like it was still quite difficult. Like the original engineers are legendary, and like so for ZK Sync we had to do things like not be completely EVM equivalent. We had to like there are a couple parts of the EVM that are like very hard to prove in ZK, and so we made some trade-offs like early on. Now ZK's gotten so good that that's actually like not as much of like a necessity anymore. Like you actually can prove the full EVM, and so like I think the developer experience is going to get like much better now. It was just hard to build ZK initially, and now it's better, and now we can focus more on like not just making things work in a basic way, but making things work nicely.
Yeah, so really optimizing for that developer experience. And you did mention about EVM equivalence, which I know that ZK Sync is starting to have plans to release like later this year. So I'm wondering if you can also touch some light onto what that really implies in achieving that full EVM equivalence.
Yep. So if you've been a developer on ZK Sync, you know, like one of the biggest pain points is like certain opcodes and certain pieces are just not quite the same as Ethereum. And so if you like fully want to copy paste your app, that doesn't quite work. And especially if you're trying to build like the same app on like 100 different chains, you don't have time to figure out like the minute differences that you need for ZK Sync. And now we are adding EVM equivalence. It's really going to be like 2 upgrades back to back. The first one is just an EVM interpreter, which is sort of like added on top of the current like stack that we have. And this is good, but it's going to be a little more costly than doing it in like a natural way. And the real end goal is for the next version of our proof systems called ZKOS, and that is going to allow us to do like full like EVM like proving normally. So it should be like much better and cheaper then.
Got it. And I'm also very curious to hear, because you've also had some extensive experience within cryptography in general, so not just ZK, but also with some other cryptographic primitives. I'm wondering just on your thoughts of, first, like the ZK endgame. Do you really think that, like personally, we will have an endgame for ZK, or will we perhaps see a combination of multiple cryptographic primitives becoming more dominant? Like, for example, we're hearing a lot of talks about MPC, about FHE. So do you see ZK dominating, or do you expect that there will be a combination of a few?
Yeah, I think like cryptography by itself has really gone through like a new revolution recently, where like really like public key encryption came in like 1976, and there was like RSA and hash functions, and like pretty much that was like good enough for like 40, 50 years almost. And then really like Zcash was the first one to really use like zero knowledge proofs in practice in like 2012, 2013, I think. And that I think is like what I would call like the start of like the second wave of like interesting cryptography coming along. And so zero knowledge proofs, yeah, fully homomorphic encryption, multi-party computation, like all of these like cool things are like now being like researched and like actively like used again. We're kind of lucky that like blockchains like made all of this relevant. And so I think that I think ZK is going to be absolutely everywhere. There's not just like within blockchains and rollups, but also like ZK TLS, ZK email. Like we're going to just prove almost every single thing that happens on the entire internet. But then there's lots of cool like further like cryptography things. So yeah, more cryptography is good.
Yeah, nice. And I do like how you mentioned that we will begin to see ZK be integrated into real world use cases. So not just within blockchain ecosystems, but then also like what you mentioned, ZK TLS, even ZK email. So we'll see ZK being a very dominant force in the future. I'm also curious to hear about your opinions on the current state of rollups that we have today. So I'm wondering if you can shed some light on in your opinion, some of the biggest challenges surrounding our general purpose rollups today.
Yep. So first of all, like rollups, like full like EVM rollups are still very new. Like optimistic rollups are only like 2 or 3 years old. ZK Sync Era launched like a year and a half ago. Like this is pretty new technology, and it's going very fast. So like I think initially there was a lot of just like, let's try and get these things working. And now that we're working, I think the 2 big directions that are happening are interoperability between the different rollups, so you're not like on an island, and then like speed, which I think it's kind of funny. It'll be like a race between the L1 blockchains that optimize for speed first, and now they're going to try and like add ZK later, versus like the ZK rollups who like built the ZK first and now are going to try and optimize for speed. I think like people are coming at it from different angles, but it's all converging on like super fast, super scaling, super cheap. It's going to be cool.
Yeah, so we see trends in just focusing on the interoperability and also the speed. Yeah, and I also just relating to ZK Sync Era, I know that you guys have plans for later this year for decentralizing your sequencer. I'm wondering if you can speak about the implications of doing so and what kinds of advantages that will bring.
Yeah, I think the sequencer specifically might be more than the year, so don't push me on engineering timelines. But like the goal is to like fully decentralize ZK Sync Era. I think like we want to inherit like all of the security properties of blockchain, and like we have to do this the right way. Like we're not sure how many other teams are going to like fully lean into decentralization because of like our founders' backstories, and like everyone at ZK Sync just really believes in the mission of like giving people like an individual's control of everything. And so just for the mission's sake, even if like, you know, economically, like you don't want to decentralize the sequencer because like look how much money Base is making. Why would Base decentralize the sequencer? Like you can kind of make these like temporary short-term arguments for why like it won't happen, but we're just gonna decentralize anyways because of like the values and the importance to the space.
Mm-hmm. So really catering to the main mission that you have there. Yeah, I like that a lot. And just going back to a bit about the developer experience within ZK Sync Era, I'm wondering if you could maybe provide a walkthrough of the developer experience specifically on Era, and then also maybe some of the pain points that developer-specific pain points that you're addressing.
Right. So the mostly it is just take your Solidity code, compile it with the ZK SolC, like the ZK Sync compiler, and mostly your code should just work. We're adding the EVM equivalents later, which will help, but it's kind of been a pain for like the first year and a half because like it's not just that you have to use a different compiler, but since our bytecode is different, you have to use a lot of different tools. So you can't use Foundry regularly. You have to use our fork of it called ZK Foundry. And like all of these kind of minor headaches, like each one is maybe not too bad, but like overall, you don't want to have to go through all of them. So like I think developer experience is something that we are like pretty heavily focused on right now because it's really been like, I'd say ZK Sync's biggest weakness, but should go away in the next like 6 months, I think.
Got it. And also very curious because you were previously part of the security team as well. So I'm wondering just on your perspectives of some of the security considerations within ZK Sync Era, and then also if there's any sort of best practices for developing secure apps on Era as well.
Yeah, so ZK Sync spends a ton of money on security. Actually, right now, shout out, there's a $500,000 contest on Cypherin for a lot of our new like interoperability contracts that you should go check out. In general, yeah, security for all blockchain, I think, is like absolutely insane. Like, there's nothing that compares to like Ethereum going through the merge. I think that is probably the biggest software upgrade on like a live production system of all time. Like, if you just think about like hundreds of billions of dollars of value, one software change, and like potentially like it breaks, it's all gone, you mess everything up. And you know, ZK Sync like also has like a lot of money on our chain. If you like mess anything up, it's like drastically bad very soon. And so there's a ton of efforts between like, we do internal manual audits, we get external auditors for everything. We also work on things like formal verification, and just in general, you have to be like super careful and try and have like, you know, backups for any like single points of failure. That's security is like very intense, but very fun.
Got it. And I also wanted to dive into more of that interoperability aspect. So specifically with ZK Chain, I'm wondering if you can just speak about some of the differences that ZK Chain offers over, say, traditional bridges that we have.
Yep. So this is, we're kind of marketing it as no bridges, mostly because it's abstracted away from you. It's kind of like built into, we're calling like the elastic chain is like the term for all of the different ZK chains together. And like our interoperability, I think, is very strong. There's like some optimistic approaches to interoperability, which basically require you to run a node for every chain that you want to interoperate with. So if I want to be interoperable with 20 other chains, I have to run like 20 different nodes, like 20 different computers. And this is like quite bad. Like you're not really scaling like at all. And also like if I want to be interoperable with base, like am I going to get Porter chain? Like is base like team going to run Porter chain's node? Probably not. So like I think it's going to be challenging for some other teams to be like as interoperable. So ZK Sync's approach is like more proving to the other chains that like messages have been sent and transactions are included. And so it's more like one-to-one instead of just like broadcasting to everybody. And this will make it much easier for us to like be decentralized, be permissionless. Like it's a much stronger security guarantee too. Like if one thing breaks, it doesn't break everything else. So I think like our interoperability is like really cool. It's gonna be awesome once it's here.
Yeah, very excited to see that as well. And just wondering how it compares to that multi-chain approach as well, and how exactly the native interoperability can be enabled from Elastic Chain.
Yeah. So like at a high level, it's just if you have chains that have very similar like protocol stacks, you can build like very tight interoperability between them. And then if you want to compare between like Elastic Chain interoperability and like Polygon Ag Layer or something, you can still have some interoperability between them, but it might be slower or like not as a little more like expensive. I think long term we'll find like the best interoperability approaches, and all of Ethereum will start to adopt the same standards. But for now, I think a lot of the teams are experimenting with what's best, and so it's exciting to see like the different ways. But I think Elastic Chain's approach is like pretty great.
And also very curious to hear about the kind of the architectural components that are involved in Elastic Chain as well, and how they kind of coordinate with each other, relate to each other.
Yep. So originally, or like the way it works today is essentially like we built ZK Sync Era, and it is a whole like L2, and then we added like Chronos chain as like a whole L2, Abstract's gonna be a whole L2, and they're kind of just isolated right now. What the Elastic Chain will look like from like a technical perspective is sort of shared contracts on the L1, and then a sort of shared like gateway layer, which is what's going to sort of like intermediate. It's going to aggregate a lot of the proofs, so like ZK proof aggregation, but it's also going to help send messages between the L2s without having to go through the L1, which is like slow and expensive. And so it's kind of those two pieces, like the L1 contracts and then a gateway, like sort of very minimal piece, just enough for like interoperability between all the ZK chains. And then still like at the application layer, it's gonna look all the same for each chain.
Got it. And I also wanted to transition into the ZK Sync VM, so something else that you guys offer within the ZK stack. So I'm wondering basically like what that entails. So how does ZK Sync's VM is incorporated into the ZK stack, and what the components look like in there?
Yeah. So this is because it was hard to build like a perfect EVM back in the day. We have what we call Era VM. I think it's like poorly named, but because it's used for more than just ZK Sync Era. But the Era VM is close, but not quite the same as the EVM. The like I'd say another like main drawback is that we designed the proof system to be like exactly the same as the VM, which means that like every change that we make to the VM, if we try and want to be like a little more Ethereum compatible, we also have to change the proof system in like the exact same spot. And so this like at least doubles the amount of work. It's probably more, and it's a huge pain like to make any changes. And so that's why like what we're aiming for with ZKOS, which is the next version of our proof system, is just to have a regular RISC-V ZK VM, and then you can have your like EVM code in Rust or something and just compile it to RISC-V, and this way like protocol like EVM changes will no longer require proof system changes. You can like change each on their own without them being like dependent, and that's going to be like way nicer for security, cheapness, users, better, like faster upgrades. We can add more precompiles, like tons of reasons. ZKOS is going to be nice.
And not having to change like the underlying proof system, but making like similar adjustments. Okay, yeah, I think that really does help with the developer experience as well. And also wondering about, because I remember you mentioned that ZK Sync is also in regards to its proof system, also having plans to change from Plonk to Flonk as well. So I'm wondering if you can share some of the like motivations and also the thinking behind why you decided to make that change.
Yep. So I think we're actually on like the 5th or 6th version of our proof system already, from the origin of Matter Labs and zkSync Lite and moving onwards. So we started with more of like a pure Plonk-based proof system. Then it kind of became Plonk-ish, where it was kind of a variation. About a year and a half ago, we upgraded to Boojum, which did Fry proofs wrapped into Plonk verification. And then I forget when the paper came out, but there's basically a new paper called like FF Flonk or Flonk that essentially is just a better way to do a Plonk verifier. And FF comes from fast Fourier transform. Essentially, the trick is that with Plonk, you have to verify like several different polynomials. And with FF like Flonk, you can kind of like interpolate all of the polynomials together and then just like prove one polynomial. And so this is going to lead to cheaper verification on chain. So this is like directly going to affect our like Ethereum proof verification costs. We actually still keep like the Fry proofs the same at the sort of like top of the proving stack, but as we like wrap the Starks into Snarks by the end of it, like FF Flonk is going to be like the cheapest way to verify in Ethereum. So that's what's next upgrade should be in like a month or two.
Oh, okay, so coming up very soon. I'm wondering also if there's any kinds of trade-offs between the different proof systems that that you guys previously incorporated, and you mentioned some of the advantages, but also curious to hear any potential limitations, any potential trade-offs that come with it.
Yeah, the challenge with the pure snark approach of Plonk and like some of the other snarks is that a lot of them are based on elliptic curves, which have like very sort of static sizes. So you can't really optimize like if you want to tweak it so it's like a little faster for the prover and a little harder on the verifier, or a little like easier on the verifier and a little harder on the prover. It's like you can't really make too many changes to the protocol because elliptic curves, like there actually aren't that many of them that like fit all of the properties that you want, and so like they're kind of tricky to work with. That's why like more and more teams are adopting Fry, because when it's just hash based, it's very easy to tweak the parameters so that in our like full proof recursion tree, like at the first layer, we optimize for being like very fast for the prover. And then like in later layers, we can optimize for being like harder on the prover, but better for the verifier. So that by the time we get to Ethereum, we've made it like, we both started with easy for the prover and end with easy for the verifier. And then you kind of get like the best of both Snark and Starks that way.
Got it, got it. And also very curious to hear about some use cases that you're excited about. And you previously talked about like we'll be beginning to see some more like applications beyond those in the blockchain context. Like you mentioned zkTLS and you mentioned zk email. Are there any sort of applications being built on zkSync, or just ones in general that you're personally very excited to see?
Yes, the one I'm by far most excited for right now is Clave Wallet adding zk email to do account recovery. So today, if you lose your private key, your money's gone. And like when you like Google like crypto user experience, like this is cited as like the #1 like big challenge is like you lose your private key, you've lost all your money. This is really hard for a lot of users who like aren't as familiar with this technology. A lot of money's been lost this way from like Bitcoin over the years. What Clave and zk email are doing is you can, like for the new user experience, it's just going to be, I've lost my private key, I'll send one email to the chain and prove it, and then my account gets recovered. So this is like the full like Web 2 like password recovery, like just like, oh, I forgot my password, click one email and I'm back. And yeah, with like account abstraction, you just have your like money and like a wallet that's set up for this, and like any time that a proof comes that you've sent a recovery email, it'll just move it to a new wallet for you. And so I think this is like completely crazy because first of all, it uses like ZK and like a bunch of math and the protocol like ZK email, like very like advanced technology, but then the user experience is just like infinitely better because now like you can like reset your account with email, which is like super beautiful. So.
Yeah, and I had no idea about that as well. So you're incorporating ZK and all the kind of hard cryptographic security with there, but then also having an optimized developer experience or user experience. And I feel like even those who are not, say, Web3 natives can interact with this, which is pretty powerful.
Oh yeah, I mean, like for my grandmother, there's no way I'm gonna get her to remember a private key. But if we can have like an email reset, where if she sends an email and I send an email and like my dad sends an email, then like we can recover my grandmother's funds and like keep her safe on chain. Like that's so much nicer than trying to get her to keep a private key, a seed phrase or something.
Yeah, super convenient. Definitely can help fuel that mainstream adoption as well. And just as a last question before we close today's session, I'm wondering if you have any sort of advice that you'd like to give to our audience, or if you'd like to kind of make any announcements on behalf of ZK Sync.
Yeah, I think, I mean, for ZK Sync, the big exciting upgrades to look forward to are EVM equivalents, Elastic Chain interoperability. I think like when those two, and eventually ZK-OS, and with those three upgrades, I think our tech's gonna be like completely amazing. More generally for the audience, I think like ZK is still like pretty early stages. Like I think cryptography, ZK, FHE, like and multi-party computation, all of this stuff is going to like completely take over the world. I've been saying for a while, I think like ZK will be like as big as AI, or maybe like all of the new cryptography will be like as hot of a topic as like artificial intelligence is. And so I think like now's still a really good time to like, you know, change your career, get into ZK, come work in the field. Like there's tons of cool applications and things to work on, and like it's a really exciting space. So come check it out.
Yeah, very exciting time indeed that we're in. Perhaps ZK will be even bigger than AI. We'll see. But yeah, thank you so much, Porter, for this interview. I really liked hearing both your vision and then also kind of the technical components there, reasoning behind your design considerations. Very lovely conversation, so I appreciate that. And thank you all for attending as well.
Thank you.
Yeah, thank you so much.
Okay. All right, beautiful there from Alice and Parker. We really enjoyed that. So we'll be having a very short musical break, and when we come back, we would have a session with White Z, where we get to talk about build a zero knowledge mining. Oh, so don't go anywhere. We'll be right back. Okay, we are back again. And I hope you were stretching your body because I was dancing. I was dancing. That was a very beautiful tune. We're about to get to the next section for today. And we have Mr. White C having a session on build a zero knowledge mining pool. Mr. YC, can you come make it up to the stage? Please a round of applause for him. Thank you. Thank you. Thank you. That was energetic. We also had have Zach in the building. Yeah. So Zach can just say hello, then Mr. YC take it on from there.
Hello, hello. I'm Zach, engineer at ALEO. This is White, and he's going to present zk.work. Enjoy.
Okay, thank you all. I'm the co-founder of zk.work, and zk.work is one of the biggest mining pool in the Aleo. We started the mining Aleo from the day one of the testnet, from testnet 2, testnet 3, then to testnet beta. And that's because we are good at doing ZK zero knowledge optimization, so we used to mine a lot of ZK related projects, for example, Filecoin, for example, Ironfish. So that's the reason why we participating in the mining of Aleo from the first day. So today I'd like to introduce the basic architecture of our mining pool, as well as the challenges and the solutions we faced during mining Aleo. Okay. So first, let me have a brief introduction about us. Our company's name is sixborg.com, and we used to be a big miner in many different projects. And we provide two products. One is zk.work, which is a mining pool for zero knowledge proofs, and another is Aleo.info, which is a data explorer for Aleo. And we used to rank the second place in Aleo testnet 2 and testnet 3, and we also ranked the 7th place in Aleo testnet beta. Right now, on the Aleo mainnet, our mining pool ranked the second largest. We are the second largest mining pool on Aleo mainnet, and we possess maybe 30% of the total computing power of Aleo. Okay. Okay, first, let me, the first part of this presentation will be the system architecture. Okay, let me show you the whole system architecture of the zk.work mining pool. We can divide the whole mining pool into three layers. The bottom layer, we call it the infrastructure layer. It has two parts. The first part is the RPC, and the next part is the storage. In the RPC part, we simply launch a Aleo node to provide the RPC services, such as the APIs for the services on top of it. And in the storage part, we have we use three different kinds of storage. The first one is MyCircle. The second one is Redis, which is used as a cache. And the third one is Kafka, which is used as a pipeline for all the data fetched from the Aleo node. And the middle layer, we call it the mining pool layer. It has two parts. The left part is task, which is used to distribute zero knowledge mining tasks to the miners. And it has four different modules. The first module is for distribute tasks, puzzles, and receive solutions. The next is for verified solutions, which is calculated by all the miners in the mining pool. The third one is to broadcast the solutions to the Aleo network to get the rewards. Then there is a statistics module, which is used to calculate all the indexes of the mining pool. And the right part of the mining pool layer is the reward part. We use it to calculate the rewards and distribute the rewards to all the miners. On the top layer, we call it the user layer. It also has four parts. The first part is miners. So we did a lot of optimizations to zero knowledge proof mining software, and the speed right now in the market, our speed for the miner is the fastest. For example, our speed is 5% faster than the miners provided by F2Pool. And so that's the reason why we have a large market, why we can have 30% of the total computing power. And the second one, is a website for the ZK to work, and the miners can use the website to know all the data of their miners. And the third one is the open APIs, which helps miners to fetch data from the mining pool, maybe to have some alert bot to inform them when the miners are offline. And the fourth part is a Telegram bot, which miners can use it to know more information and to receive alerts from the mining pool. Okay, so and we also provide the mining software, or we can call it miners, to the public. Right now, we have the fastest NVIDIA GPU miner on the market, probably. Yeah, because we also do some benchmarks with other mining pools, but right now we are the fastest. But we are not sure if in the future we can still hold this position. And we also have the first and the only AMD GPU miner on the market. Yeah, so right now, if you want to have your AMD GPUs to mine Helio, the only choice is us. Okay, the second part of the presentation will be, we will introduce some challenges and solutions which we had in building such a mining pool for zero-knowledge proofs. And I think the first and the biggest challenge we have is that the complexity of the puzzle in Helio is changing all the time. As you know, in every epoch, the puzzles for the epoch will be changed. So the complexity and the difficulty is also changing. So you can see that the verification cost for a single solution is changing up and down, and as well as the miner, at the same time, the number of solutions to be verified is also changing, because when the difficulty is getting lower in a specific epoch, and the number of solutions will be more and more in that epoch. So everything is changing. So the computing cost to verify all the solutions submitted by the miners is changing up and down. So to solve this problem, you can see that in a traditional mining pool architecture, all the miners just submit all the solutions to a single centralized module and to verify all of them. And then all this submitted solution will store in storage. So that we changed the traditional architecture into a brand new one to handle this challenge in a zero-knowledge proof mining pool. So we just separated a single proof verification module into several ones. You can see from this architecture, from this picture. So in this picture, the module of verifying solutions is separated into three ones. And so we can scale the ability to verify these solutions to a large cluster to handle this. Okay, so that's the first thing we did when we dealing with such a zero-knowledge proof mining pool. And the second challenge is also difficult to handle. So you can see that in Helio, all the solutions can be submitted throughout an epoch as puzzle remains constant for epoch. That is to say, the puzzle for an epoch is constant, and if you find a solution for that puzzle, you can submit the puzzle at any time of the epoch you want. So that we can also do some optimizations in every epoch. For example, we can submit solutions to empty blocks to get more rewards. Also, we can cache all the solutions for difficult decrease. For example, if right now you calculate out a solution, but the difficulty is still too high for that solution, you can just cache that solution and wait for a while. When the difficulty just getting lower, this solution can be validated, and you can resubmit that solution into the network to get a reward. The third optimization we did is that we can resubmit the ghost solutions, because right now the Helio network may randomly drop out some solutions because of maybe the network issue. And the official team calls it ghost transactions. So that this also happens when you submit solutions to the network. So if we see that one solution cannot be accepted by the network, we can also resubmit it to get it on chain. So that's the second challenge and solution we have during the network. Okay, the final, I would like to share some data of our mining pool. Because you can see that in the market, there are many projects claim that they will launch a cloud service, a cloud for zero-knowledge proofs. But right now, you can see that we are the only one who successfully built such a cloud service for zero-knowledge proofs, or you can call it zero-knowledge cloud. So what's the data for our mining pool is very important and valuable. So right now, you can see that we have maybe, this picture is a screenshot from our website. You can see that right now, we possess about 30% of the total computing power of the mining pool and of the whole Aleo mainnet. And right now, our hash rate is more than 100 giga hashes per second. You can see the number is very big, which means there are in the network more than 125 giga proofs are generated in our mining pool. So I think that's maybe one of the biggest zero-knowledge proof platform in the market. Okay, and this is the benchmark of our miner. You can see that for the most high performance 4090, we can have our miner is about 1.88 mega hashes per second, and I think this is the fastest in the market, even faster than other mining platforms, for the example F2 Pool and Ola and others. Okay, and this is the hash rate of our mining pool. Right now, the hash rate of the mining pool is 157 giga hashes per second, and the miners in the market, which means individual ones who participate in our mining pool is more than 4,000, and the workers, which means individual servers in our mining pool, which is more than 41,000. And for each miner, for each worker, they maybe have 2 to 8 GPUs. So right now in our mining pool, I think there are more than 100,000 GPUs in the mining pool. That's a big number. And I can also tell you that maybe 60% of all the GPUs, 60% of the 100,000 GPUs are from Russia, and 30% of them are from China, and the left 10% are from other countries all over the world. Okay, thank you. That's all of my presentation. So, do you have any questions for it? I wonder. Hey, please. Okay. Microphone, please.
我们知道这个石榴啊，是国内知名的这个锄头还有矿齿的供应商。我今天想咨询一个问题，就是，我们现在的对于 Aleo 的这个锄头啊，还有矿齿的支持，主要是针对 GPU。那 Aleo 项目方一直在说 ASIC 才是未来最好的这个性能解决方案。我想咨询一下，就是，在未来石榴有没有专门针对这个 ASIC 芯片的这个优化的方案？然后你们预计 ASIC 方案会在何时能够上线？大概这个问题。
Okay, let me first answer this question in English. This guy just asked us how about the ASIC for the zero-knowledge proofs for Aleo, and when it will come out. I think that the ASIC for zero-knowledge proofs is much more complicated than that for Bitcoin, because Bitcoin just use simply SHA-256 hashes. That's more easy to build design such an ASIC. And for zero-knowledge proofs, that's more complicated, because right now in Aleo, the mining of Aleo is just to calculate a circuit, a random circuit. And if you want to build such an ASIC, it will be totally different from the one of the Bitcoin. So right now, we are also cooperating with some other companies in designing such an ASIC. And designing is finished right now, and I think the final chip will be released in the next I think it will be released in half a year, maybe next February, next March, and that will be the date for Aleo ASIC. And that's not a promise. Thank you.
Any more questions? Okay, I think that's all.
Okay.
All right, thank you so much. Please a round of applause for him, please. Thank you. Thank you. Thank you. So that was an amazing session, and we will moving on to the next itinerary for today. We have a panelist session on ZKVMs, and I'll be calling the names of the speakers here. Please can Mr. Bobbin from Polygon Meeting come out? All right. Please a round of applause for him, please. If you're in the building, please a round of applause. Can Ming come out? All right, thank you. Brett Carter. All right, please. Thank you. Hades. Hello. Okay, so Mr. Brandon. All right, pleasure. Pleasure to have you with us. All right, thank you so much. Thank you.
Hello?
Hello.
Hello? Yeah, I'm good.
Hello. Oh, it works. Hi, everyone. So we have a panel today. I'm moderating. I've never moderated a panel before. Let's see how I do.
Really, I'm surprised. I'm on stage with a couple of times already. So.
Yeah, I've been on panels. So so we're going to talk about ZKVMs, and we're going to talk about a cool part of them, their design and architecture and performance and these kinds of things. I'm super excited to get into it. So yeah, I mean, I guess before we jump in, people should introduce themselves. Should we just go down the line? Go ahead.
Yeah, sure. Yeah. So my name is Ming Guo. I'm the chief scientist of ZKM. Proudly to be your host here. Yeah, that's me.
I'm Brett Carter, VP of Product at RiskZero. I'm the least qualified person technically to be sitting up here, but it's an honor. Yeah, definitely have some thoughts about ZKVM design and excited to chat with you all.
Hi, I'm Hadas. I'm a researcher at LIDA, a ZKVM company.
Hi everyone, I'm Bobbin. I'm a project lead at Polygon Maiden and the designer of the Maiden VM.
Great, and I guess I should introduce myself. I'm Brandon. I'm the CEO of O1 Labs. We're also working on a ZKVM as one of our projects, but I'm not going to talk about that today. I'm here for you. So, shall we?
Please.
So yeah, when designing a ZKVM, how do you think about, or how is this different from a traditional virtual machine? Anyone want to take it?
Yeah. Yeah, so there used to be a saying that you do a proof once and then you can run everywhere. But here, doing ZKVM, you're actually not running everywhere, right? It's just a proof. You don't really run it. So I think that's the major difference between design a virtual machine and a ZK virtual machine. It's for proving, verifying. It's actually not for executing. So, yeah. So that's something to bear in mind. But we'll delve into that, I'm sure.
Yeah, I guess from RiskZero's perspective, I think the team made even before I joined, made a really big bet on really optimizing for accessibility. So that was the idea around selecting RISC-V as the ISA that we were targeting, is to really try to make this available to average developers. And so in that way, I think our focus was similar to designing a regular VM. We really wanted developers to be able to use tooling that they knew. Obviously, Rust wasn't quite as popular within the blockchain and crypto space as it is right now, but yeah, that was really like a key consideration for us.
Yeah, I think it's just about what operations you're optimizing for. So traditional VMs, you're really you're optimizing for what happens on the CPU, and then in a ZKVM, you do have to optimize for that, but first you have to optimize for algebraic operations. So for example, at LIDA, one of the reasons we've seen such speed gains compared to competitors is because we create our own compiler as well as so we have the prover side and the compiler side, and the design things go together. So by building our own ISA, we're able to actually optimize for the algebraic operations.
Yeah, I mean, I agree with all of the comments, but I think like there are multiple dimensions on which you choose, right? You can choose like where are you on the developer friendliness, so to say, and then you know there are different gradations. So like you can build as RISC-0 is doing, for example, the kind of common ISA. You can do as Lida is doing, like different ISA in different compiler, or you can even come up with a different language, for example, that is like there are different gradations in that design choices. You also want to choose like what set of features you need to support, and this is use case driven, right? So for example, do you need very small proofs, or like how small your proofs need to be? Because if, for example, if you're doing something to be able to do client-side proofs, this is important. You need to send them over the network, and then you know the difference between like a few dozen kilobytes versus 50 kilobytes versus like a megabyte is a huge difference. So you want to pick that. And then as you've said, it's basically also how arithmetization friendly you can try to make it, and like how do you want to handle recursion, for example? Do you optimize it to be very recursively efficient or not, or it doesn't matter that much? So like there's a ton of design choices that the usual VMs you don't care about necessarily as much, but here it's like probably half a dozen of dimensions on which you need to make a choice, opinionated decision, and then it depends on the use case.
May I add, since everyone's spoken, may I add that I said earlier that it's actually not running everywhere. It's a proof. So I think the elephant in the room is that why we chose different ISA to prove, right? So
and which is better?
Yeah, it's a little bit contentious, this topic, but let me give my take.
Go ahead.
So actually, Owen and I think we're in the camp of MIPS, right?
I'm the moderator.
Okay, all right. But yeah, but they're the same with us. And I believe you guys are RISC-V? RISC-V, yeah. Both of you are RISC-V, right?
Custom.
They have their custom.
Oh, okay, yeah. So I think this is not like related to ZK, because we kind of use this kind of same kind of approach, like a Plonky, and Plonky 2, some Plonky 3, and then Graph16 for verifier. So I think that the choices between a little bit, not just engineering, but also like market penetration consideration, right? Adoption. The elephant in the room is that, for example, like StarkNet, they have their own custom like VM, like Cairo. I once heard one of the engineer saying that, for example, proving like sharp 206, they're 933 times faster than RISC-0. So they can do that because they have a really simple virtual machine, right? But that virtual machine doesn't exist anywhere else, so you have to just completely like, kind of just immerse in their everything, their ecosystem. But I think for a lot of use cases, we like to verify real-world programs and verify them on-chain for a broad range of application. So I think that's the reason why some of us chose this hard real-world RSA, for example, MIPS and RISC-V, right? And for us, we want to kind of, and then Lida is there because Lida can kind of optimize their own VM, which is very kind of similar to RISC, right? But very optimized for ZK. And I think in the future maybe that's your world. I have to yield to you guys. But the consideration is that you kind of keep kind of balance that you balance for real world kind of market penetration. For example, MIPS is around for like decades. Very simple. It's more simple relatively, right, compared to these customer ones. But for the real world CPU, MIPS is really simple, and then also kind of considering that it should be also good for ZK doing ZKP. So I think that's every project kind of catering to their own market segment and try to be as best fitting for their use cases and audience. So I think for first of the ZK VM design, I think this is I think this is the case for choosing ISA, and then we have other considerations, vectors of Yeah, as well.
So I think so. There are approaches, right? So like ISA, then you like what developers care about. The developers want to write in a language that they know. They don't necessarily care what's running underneath, but like there are obviously trade-offs. So like we discussed some approaches where you have the common ISA that you have compiler tools that already compile to that. You have like Lita and kind of Maiden approach where you try to compile, like let's say from Rust. And custom ISA, there are other approaches as well which are not represented on this panel. For example, you can interpret programs. So you can like have something like is not even compiled, and there are pluses and minuses to this as well. Like developers just cares that they can write in a language that they understand. They don't even care if there is like a compiler underneath or whatever. So like I would say, but all of these choices come with other trade-offs, right? Like RISC-V, you get a tool chain already existing. You don't need to invent or build a compiler. While like in Maiden and Lita approach, you do need to have like some compiler, modifications. Or maybe I don't know Lita to what extent you do it.
Libs as well, yeah. You can probably just pick a program compiled 20 years ago and still generate.
Yeah. And an interpreted approach, you don't even need to worry about compilation. So like differences between compiling in different ways, you like saying, okay, like it's a program, you commit to the code that a high-level code and it interprets it. So there are pluses and minuses everywhere.
So what are the, I guess, with the custom ISA approach, as you're mentioning, you have to build your own, some parts of the stack, right? Why did you go with that choice for both of you, Lita and Maiden, versus a more traditional ISA?
So what we found is that by designing our own ISA, we're able to really reduce the number of algebraic operations we have to do in the end. And so, on the ZK side, as I think you said, we are all kind of doing the same thing. And I mean, you can always use the most you can do is use the state of the art in zero-knowledge proof research. But to have an edge on top of that, you have to reduce something somewhere. And I guess the easiest thing for us to reduce is the number of operations that we have to do, which
like
can happen.
You have like 2 registered, right?
Yeah.
And we have many, many
yeah,
more.
exactly.
Yeah.
We don't have as much. We have like special purpose registers and things like that.
Yeah, I would say basically like efficiency is one consideration because like for example for Maiden, we need to be able to run it in like 2 gigabytes of RAM and generate proofs in 2 gigabytes of RAM. So you can prove it in a browser on a phone. You can have a lot of like setup times. I think in a lot of existing ISAs you need to spend some time to set up. Like there are some number of cycles spent on just setting up the program and initializing everything. In Maiden, your program could be as small as like 256 cycles, for example, and that's enough. I mean, you can do a lot in 256 cycles, but if you have a small, like that's like the minimum instead of like, a few tens of thousands of cycles that sometimes it takes to like just initialize things. So the efficiency is one. The other consideration is like if you need features that some ISAs don't provide. So Maiden is like, as a project, we care a lot about privacy specifically. So we need to build a kind of an environment where you have private and public programs interacting with each other seamlessly. So you need to build in, let's say, context isolation at the level of the VM, where like if you are running in one context and make a call in another context, they can't access memory from the other context. It's not a kind of something that you build on top of the VM. It's a core property of the VM itself. And then you can take it even further. Like we are not there, like with Maiden, but for example, you can implement a full like kind of resource-based model where there are resources that can be shared, and the sharing of resources enforced not by the language, by the VM itself. And that gives you, especially in blockchain context, that would give you a lot of cool properties, but no existing ISA supports that.
Right. Yeah, from the RISC-0 side, what
Yeah, I think actually this is maybe, I don't know if anybody's ever explained this well or how many people know this, but we actually do have a custom ISA specifically for our recursion circuit. So like we have the RISC-V circuit, it proves RISC-V cycles. It's got a couple other widgets on there. There's like a big int multiplication component. There's a SHA-2 accelerator built into the RISC-V chip. But we took and I think the question also has to do with like sort of timing, like when did you sort of start these systems? I know, like Bobbin and their team were so early, sort of like forging ahead, doing really cool stuff, building specifically for a blockchain. And when we looked at RISC-V, people were kind of like, that's a dumb idea, proof systems are too slow, and so we've been mostly focusing on optimizing the prover, and we've had a lot of success there we'll maybe get into. But what's interesting is I think we were the first team to take this approach where there's actually 2 circuits in the protocol. The second one is a dedicated recursion circuit, and this merges segment proofs, like individual RISC-V, sets of RISC-V instruction proofs, through a merge tree like into succinct proof. And that recursion circuit actually has its own ISA for efficiently and quickly verifying these proofs. And there's a couple predicates in there. So like you have to like take one of our segment proofs and do a lift, sort of lift it into a dialect in which we can then sort of join proofs into a proof set. And so yeah, there's kind of actually a mix in our protocol.
So Brett, is the recursion circuit that's its own VM with instructions? It's not a custom.
Yeah, it is.
Really cool.
Yep, absolutely. And
why is that? Instead of just being like a domain-specific circuit that does the one thing of.
Yeah, that's a good question. So we've also built all of our own compiler technology. And you mentioned earlier we're all using Plonky 2 or Plonky 3. We actually have our own Stark-based proof system, so it's not true for RISC-0. Which Plonky 3 is great, and there's a lot of similarities to what we're doing. But at the time, it didn't exist, and so we built our own proof system. And so we describe circuits in one of two ways, either in our DSL called Zurgeon. We've built like a whole stack. It's DSL, compiler, proof system, VM, etc. And I'd have to ask Jeremy because he's the one who figured this out. But it's just from an automation perspective, it's way easier for us. Once the RISC-V circuit updates to just sort of update a constant, all the compiler takes care of all the rest. So it's really a convenience and maintainability decision.
Yeah, so we've started to touch on performance. With each of your specific ZKVM approaches, how do you keep performance in mind? Like what tricks have you done? Like what are the design considerations that you've made to make performance better or make it easier to optimize?
I think like I said earlier, like the industry is kind of just similar. We all read the same papers, and kind of engineering teams have figured out kind of similar paths to solutions. So I think that it just came down to like each like engineering trade-offs that you do yourself. How much you use the lookups, the table, because we're kind of dealing a much complicated like a real CPU here. We have many more like registers, and also we support the 4 GB of memory. So all that needs to be taken into consideration in all of our proofs, and of course there are also specific example for hash and something you have to do optimization maybe separately, and there are definitely rooms for improvement to squeeze. So I think we're because we're kind of like latecomer, but I think it's worth it that we're catching up, and also we're benefited from that. MIPS is a very stable and simpler instruction set. So and it's also very very stable. Like a couple decades, there's no bugs. And because it's simple, there's no like floating point, everything. Yeah, I think it was like we're at the beta 3. It's kind of on par, and maybe in some cases, even kind of near the top. So we're satisfied. We're still improving, but we're satisfied.
When you consider all the steps necessary to sort of write a program, generate a proof, verify it on chain, there's so many things you can optimize. It's actually quite a complex process. And I guess one of the things that RISC-0 did early on is, it was obvious, Ellie, from Starkware wrote the Stark paper. Jeremy, our co-founder, read it, and he was like, "This is amazing. I think this, zero knowledge proofs will be practical, but people aren't going to write circuits." And so when he started looking at, we talked a little bit earlier about ISAs, but he also realized, we need better and faster proof systems in order to make this feasible. And so, at the time, Cairo and Starkware, I think they were using like a 256-bit field. The Polygon team, innovated the Goldilocks field, so that brought fields down to 64 bits, and like proof systems were getting incredibly fast. I remember seeing a tweet that like I was working at O1 Labs with Brandon, and Polygon, like in Plonky 2, somebody was doing like hundreds of hashes in a second, and I was like, what the hell? This is incredible, And Jeremy's one of the key innovations under RISC-0 was like his discovery of the Baby Bear field, which is a 31-bit prime field that actually works really well, surprisingly well, with proving RISC-V cycles. And so again, just sort of reducing the size of the field. Now, we're going to clearly, in Binius, we'll eventually go to, a 2-bit field, but that was a really key consideration in making things go fast, if you will. One of the underrepresented things, though, is like we tend to think of benchmarks and performance as single machine performance. And in reality, ZK VMs, and particularly the approach that many of the general purpose ones are taking today, actually enable dramatic improvements in performance through parallelization if you're optimizing for wall time. So if you're just trying to make a proof go fast, we can generate an Ethereum block, a proof of an Ethereum block today. And like Bobbin mentioned earlier, we're actually interpreting the EVM bytecode. So this isn't a dedicated ZK EVM circuit, but we're actually running an interpreter in RISC-V, and we can generate a proof in 60 to 90 seconds right now for the average Ethereum mainnet block. And so there's just like sort of all along the way, then how do you, many of us do this, we convert the Stark to Snark, lots of opportunities for performance improvements there. And so there's really, in terms of like just pure speed, burr, performance, there's just so many different opportunities to optimize.
Yeah, I agree with that. I mean, there's no one way. But what we do, I think what's nice about the way our and probably most ZK VMs are designed is that it's very, very modular. So for example, we, like when we're developing, we end up optimizing on a chip-by-chip basis. And then after you write something, then doing benchmarks and making sure that everything is getting faster. And then, yeah, on the proof size, side, there's a lot of new optimizations coming out. Field size is one of them, or picking the correct field for the correct application. I don't know. We're gonna be moving to sum check-based Snark soon because those you can totally avoid polynomial quotients with that, which is a bottleneck. So I think it's just about, but what's interesting, I think, is that you can get really excited about one thing speeding up and then find out that it affects the system only a little bit. So I think one key lesson with optimizing things is always take a systems level high view approach to it. Otherwise, you'll end up being disappointed a lot.
What do you mean by choosing the field? Is that a parameter in the?
Yeah, I guess there are some field agnostic snarks so that they work over any field. And so, for example, if you wanted to verify signature schemes in a snark, you can use the same field that the signature scheme is using, so you can avoid non-native operations, which can be a large constant overhead. Yeah, because you have to do modular operations in the circuit.
But I think one of the advantages of ZK VMs in general is that you can be field agnostic. You can swap out the proving system agnostic even. You can swap out the proving system and instruction set hopefully remains the same, and therefore you don't break everything else in kind of what was written against it. So that's, I think, is a major kind of power of just going the VM approach, especially the VM approach that doesn't use field-specific operations or doesn't assume something about the proving system and things like that. And that is very cool. I think yeah.
I was just gonna say, yeah, you could consider that an aspect of performance, right? What does your maintainability look like? How maintainable are the systems that you're building? And I think we tend to just think how fast can you prove something, but there's these other components that sometimes are often much, much more expensive, for example, how do you find talent to maintain a system, write zero-knowledge circuits? We've seen, because of general purpose ZK VMs and really what the Maiden team had really kicked off this innovation of VMs is much more maintainable systems that are much less costly to build and yeah, maintain.
Yeah. I would say Starkware was the first production-ready VM. Maiden was the second one.
Maiden was the second.
Yes, but overall, so in terms of optimizations, basically it's picking again for your use case. As an example for Maiden, we need to pick we're trying to make it fast for our specific roll-up use case, right? So we're making some things faster that maybe in other systems you don't care about, but in Maiden we care a lot. For example, we need to make our goal is you should be able to prove a simple transaction on the phone in under 2 seconds. And so we may not be able to do it with ECDSA signature, for example, but we can pick a post-quantum signature standardized like Falcon, for example, and have specific circuitry as a chip in the VM that allows you to prove Falcon signatures very, very quickly. And that's what you optimize for. I think the other aspect of this is as you said, as you solve for one bottleneck, you come up with a different bottleneck. So you always jump from one thing to another as you progress through this optimization. I think what will happen kind of going forward, your witness generation will become much bigger bottleneck than anything else, especially as we move toward hardware, because everything else is very easily parallelizable. And your proof generation part is actually going to be a small part compared to the witness generation part.
What do you mean by witness generation part?
Computing the trace.
It's already a bottleneck in our proof
Yeah.
system in many cases. It runs at 30 to 50 megahertz, so we can commit to like 30 million to 50 million RISC-V instructions per second on like a pretty decent machine. But because everything else is parallelizable, and if you have a really big block that's like, say, 2 billion cycles, it's already the bottleneck in many cases, so absolutely agree.
You mean like interpolating the polynomial from the data?
Yeah, so the way that execution works in our ZKVM is like first we generate an execution trace and make, generate witnesses between the segments, the individual segments. So there's some commitments that take place between these segments. And so as we're just running the program itself and doing this witness generation or making these commitments, that can only run, it's single-threaded, non-parallelizable, and it can only run at about 50 megahertz today.
Interesting.
And if this is becomes your like ceiling of what you can achieve, because I think again, like especially with hardware generation, like 90% of the time is going to be witness generation time, and like hardware will take care of, all parallelization will take care of like the actual proof generation time.
Why isn't it parallelizable? Because you have to go through the execution trace? Like
It's a single-threaded program that you are usually executing.
So this is interesting, right? Like, does anyone foresee a future where we're going to change, like, adapt to the way we write our programs to be so that the execution trace can be computed in parallel? So I guess like in a traditional system, some kind of concurrency model. Is that something
you can
anyone's
already
thought
do that
about?
today? So like if you're using a general purpose ZKVM and you want to prove Ethereum blocks, there's like a number of ways to do that, right? You can prove an individual block, you can prove sets of blocks. I know, Uma and their team, right? Like in OP Sysync, there's a nice graphic in one of their blog posts where it's like they do these range proofs of like say blocks 1 to 10 and then 10 to 20 and then merge them after that. And so you can kind of parallelize the execution
But those are separate ZKs.
by splitting up the proofs,
But
exactly.
like one program definition in Rust,
Yeah.
but you can compute the execution trace in parallel.
That'll be interesting.
Has anyone thought about that?
No.
I guess
I
it's
don't
too
know.
far away.
We're
That's
thinking
cool.
of things to make execution way faster. We have some ideas and like where we can get to like 10 to 50x probably faster than we're executing now. But I don't know that you can actually like you sort of in order to generate a proof you sort of have to constrain yourself down to this program that does run linearly. And so I don't know how that would happen other than splitting the proof itself.
And there you can maybe, I don't know, your CPU runs at 5 gigahertz, right? Like maybe you can optimize things so like your single-threaded execution will run at like a tenth of that. Like maybe, there is room for improvements and like optimizations. Well, you'll get to like 500 megahertz, but that will be your ceiling in terms of what you can do, except for like maybe long time in the future where you can actually have a custom like RISC-V chip with an extension that, for example, generates the trace as it executes, and that would be like cool, but it's also like far away in the future.
What's funny is we're already talking about performance getting close to like regular CPU performance. There was a team we were talking to, I won't name their name, but they're like, oh yeah, we need to get to like 50 gigahertz of proving performance. We're like, there's no regular processor that goes that fast, So these are good problems to have. Like the space is advancing so quickly that actually like 50 megahertz, if we get to 500, and 10x improvement from here, we're starting to talk about real good, reasonable performance.
Yeah, I remember Jody mentioned that with this massive parallelism, that 12 seconds for a certain block, something like that.
I'm sorry, what was that?
12 seconds for
Just doing the
block.
execution on a block?
Well, yeah.
Proving as well.
proving,
So like if you can actually prove Ethereum block in 12 seconds.
Oh, real-time
by-
proving. Yeah.
Real time.
Yeah.
But I think you still have the delta, right? Because like they actually can execute the block in like 1/10 of that time, or like sub-second for sure. But proving but I think we'll get to the point where you can execute and prove basically at the same time. You need hardware for that, and you need
Yeah. I think like mainnet, for example, the average, and this is like Shanghai blocks, like there's all these caveats here, but roughly you need in RISC-V cycles 170 megahertz of performance to keep up with the chain. And so if our executor is only running at 50, you can do other things like move them out of RISC-V cycles, do dedicated accelerator circuits or precompiles. There's definitely some things that you can do, but yeah, I think 170 megahertz is roughly where we need to get.
Yeah,
for
so
that.
why don't we go into this domain of accelerator circuits or custom chips, or what do each of you how do each of you think about this? Yeah, precompiles, accelerator circuits, custom chips. What is the lingo that you use? Why do you use that? Is there even something standardized across the industry? Like how do these components fit into your stacks?
I don't think there's a standard anyway. Like there are also like these ZK acceleration chips out there. So yeah, it would be nice to have a standard or something. but I think everyone is just to make their own. Do you guys work with any, you know?
Brandon,
yeah,
do you mean standard terminology or?
Not hardware, yeah, like within your ZKVM, your precompile circuits or custom accelerator, like virtual chips. I heard some.
Yeah. I mean, we call them chiplets. People usually call them chips or coprocessors or state machines. I think there's like across different projects, people use different terminology. I think there are also different ways to do them, right? So there is probably, I know, like about half a dozen different approaches of how you do them. Like Maiden does them in one way, Cairo does them in other ways. Like I think RISC-V does them in different ways. I think Sysync does them in different ways. So like, and I think Lida also. So there is like different ways of how you can have chips or chiplets, how you tie them together, because there's different permutation arguments you can do. You can do it through recursion, for example. So I don't think there is a standard. People are experimenting, and again, like some things apply better to some use cases. Some, you know.
So what experiments have you done? Like what experiments has the industry done? What I guess like why are for those of you that are using these accelerators, like why are you doing the approach that you are?
It's funny because I think we have 3 or 4 different approaches that we've tried or are doing in our proof system. So it's not even like just a one or the other opportunity. So I mentioned actually that, like, you know, we have inside of our RISC-V circuit is sort of 2 helper functionalities for SHA-2 acceleration and for big int multiplication. And that's actually like one approach, which is to actually just write it into the RISC-V circuit itself. We can do the same in our recursion circuit. So RSA, for example, actually fits quite well into our recursion circuit. We have, you know, an accelerator or precompile for that. That's coming out in the next couple weeks, and that is actually the same approach, but in our recursion circuit specifically. And then there's something like Keccak, for example, where we're writing what we would call like a machine accelerator, or like, you know, a dedicated separate circuit where we you know, include a recursion predicate. Like we generate this separate proof, but then use recursion to sort of stitch it into the RISC-V execution. So that's 3 different approaches that we're taking just in our proof system alone. But there's, yeah, I think it's still like to be determined if there's, you know, one exact way to do it. It's also algorithm specific, right? So like, you know, I don't know this exactly why, but RSA just like fits quite well in our recursion circuit. And so we're sort of taking a case by case approach.
Yeah, I think everyone's doing something like that. Just we don't call it like a chip in chip, but but do you need like a special instruction to your virtual machine? Did you need compilers to support all that?
Do we need a compiler to support all that?
Yeah.
Yes, absolutely. Yeah. We've definitely doubled down, like, I don't know, 10x down on compilers in our, like, we spend a lot of time maintaining our compiler, you know, writing this DSL. What's really nice is like you can get, for example, there's like work in progress on actually making SIRCOM R1CS compatible with our compiler.
Right.
So you can actually compile any existing SIRCOM circuit down to RISC-0 Stark circuit. So yeah, this is all compiler dependent for sure.
Right. For us, like we're looking both the back and the future. So because, for example, like a Rust, I think a lot of new applications, especially like blockchain applications, are written in Rust. So yeah, so we're trying to do like these experiments to accelerate and optimize them in the Rust compiler support that for our ZKVM. And we're also looking back for compatibility because there are a lot of legacy apps support these special, like for example, edge computing devices, like sensors. They're there, they're very standard, and so we hope that one day that we can just take one of them and have them proved on-chain. Those are the ones that needs blockchain and crypto support. You know, for consumer devices, yeah, maybe not that much. So, you know, so MIPS is very, very good in that, stable, simple for decades. And yeah, and for the future in the Rust and everything. So it's a balanced approach. But I think it's fascinating that you guys are innovating in the, you know, look in the future to, you know, RISC-V definitely has a lot of the modular support for that. Yeah.
Yeah, I think it's not good to have too many custom chips. So it's one thing you have to think about when you're doing it. It's like, does it actually address a general problem? So like, it makes sense to have one for a hash, because you're always going to be using hashes, or for recursion, because that is like reduces proof size for general circuits. So I think before we introduce custom chips, we always think about, is it attacking a general problem actually?
Yeah, what's interesting, we mentioned that you tweak performance somewhere and it creates these like follow-on or secondary or tertiary side effects. One of them of like chips is, okay, now you have like basically, you know, different proofs to optimize. So imagine you have hardware that's built to accelerate, you know, RISC-V proving. there's ways to design it so it could be more flexible than this, but now all of a sudden that doesn't, you have a new proof that you're running that hardware does not accelerate. And so, yeah, to some extent, there are definitely trade-offs that you take.
Yeah, so my approach is kind of like, I think, similar to what Lita is doing in some ways, but also like similar to RISC-0 in some ways. Basically, we have a handful of chips, or chiplets as we call them, that do hashing, that do like binary operations, and a few other things that we care about specifically for recursive proofs. And the approach to handle other computations that you want to accelerate is through recursion, where you kind of like do a syscall in a, and like this syscall like expects that there will be a recursive proof, let's say, for ECDSA signature or for like something that we do not accelerate, and then those, if you have your inside the VM, the recursion if well optimized, then verifying those recursive proofs would be cheap. And I should mention that this is still in development. We don't have this fully working in production yet. But this is the approach to kind of like have a handful of chiplets, because they also increase like the other consideration for Miden is that we want proofs to be small. And therefore, like we have very small number of columns. So like we have, I think 70 columns overall right now. And adding a chip would result in more and more columns depending on how you do them. And so we want to limit that, and we actually like stack chips on top of each other so they share the trace. And this way you kind of reduce the proof size. But yeah, so like handful of chips, and then everything else handled through recursive verification of specialized circuits.
And you mentioned you can use like some equivalent of syscalls to kind of access this logic. Is that, I guess, how does everyone think about this? Because especially for the standard architectures, like MIPS or RISC-V doesn't know about verifying a recursive proof or executing a Keccak coprocessor or something. So how do you escape the like sort of native instruction set?
Right. Actually, for MIPS, it's quite simple because it's the oldest one out there. So the syscalls for the CPU. So we don't have many, maybe less than 10. So it's quite straightforward. Yeah, this is the CPU one, not the system level one.
Yeah, I mean, I guess this is punching a little above my weight, technically. But we use syscalls to essentially sort of escape the RISC-V execution and say, I'm going to call into this other circuit and a recursion circuit in order to use what we call like a machine circuit, sort of like a dedicated separate circuit that we'll do recursion for. We have to write a recursion predicate for that particular circuit that gets added, incorporated into our recursion circuit. And so, yeah, that's essentially how we enable these two, disparate circuits to communicate our systems.
Cool. Should we? I think we have like less than 10 minutes. If there's any question in the audience, we can take one, or I can ask more.
I got to say something real quick.
Oh,
which
go
is
ahead.
Like, it's funny because in a lot of this stuff, we don't talk about security. I think that's
Okay,
something we have
let's
to
talk
talk
about that.
way
Go ahead.
more about. We're building ZKVMs not to just like generate proofs in space, right? Like we're building like financial systems and decentralized systems on top of these. And so, yeah, no, I don't necessarily have anything to pontificate about, but we do as a space, I think, need to start emphasizing the security of these systems.
It's time to pontificate. You
Yeah.
brought it up. So how do you think about security in RISC-0, and then we can go around the room. Like what aspects of the design of the ZKVM or the design or the mechanism by which you're developing the system do you like? How do you think about security in those processes?
Yeah. Number one, like audits are a bare requisite. It's a bare minimum, not a bare maximum. Like I think we tend to think like, oh yeah, it's audited, therefore it's good to go. It's like, no, that's actually, just like bare minimum. And so I think one of them is, how many bits of security are provided by the underlying proof systems or the way that these circuits are constructed. And I know that's something that Paul on our team just has spent, copious amounts of time making sure that we have peer-reviewed materials on the bits of security provided by our proof system. Another one, and this is true of our proof system, and I think some of the other Stark-based VMs as well, but like for example, when you select what we call a segment and what the SP1 team calls a shard, when you select the size of those shards, like in our system, you configure a PO2, which is like how many, to the power of 2, how many RISC-V instructions do you want in a segment? that actually does determine the security parameters of the system. So by default in our proof system, it's set to 20. So there's about 1 million to the 20 or 1 million instructions in a single segment. If you go up to 21, that brings the bits of security provided from roughly 99 targeted bits of security. By the way, this is conjectured security. You can also get to proven security in Stark systems, but this brings the security down from 99 to 98 bits, and we think that's like the appropriate lower threshold. You could actually like hard code bigger segments into the ZKVM, but security would go down essentially a bit at a time. And I don't think this is like a component. Many people don't understand this, and we've in our docs, there's like 6 dedicated pages on security, because this really matters. There's like so many ways to potentially exploit these systems. You have the proof system, the circuits themselves, multiple proof systems, right? Because we do, CIRCOM, and we're all doing, wrapping the Starks and Snarks, et cetera.
I mean, on that note, I think I guess what I was going to say is that there's many aspects of security. There's the security and the soundness of the proof system itself. There's making sure you write the code as is specified by the protocol. And then once it's deployed, there's actual just like end-to-end security where there is in any software system, and there's so many ways that could go wrong.
Then the
and
contracts to verify them, right? It just keeps going.
But it is something to focus on. But in terms of conjectured security, I'm a PhD student as well as working at LIDA, so I focus on this a lot. And I think conjectured security is an interesting thing, like especially with the Frye-based proofs. To get the proof size to be like tolerably small, you end up having some kind of not so great provable security that you like compensate for with proof of work. And I think that's probably fine, maybe, but I think it would be nice. I think it's probably wise to focus more, like as a research community, we should focus more on getting the provable security down and without compromising proof size, because, I think it's not good to use conjectured security.
Can you explain more, like what is this term conjectured security? Like what is the specific,
What is a conjecture?
What is a conjecture?
Yeah. Yeah.
Well, that's not a question for me.
Well, yeah, I guess there's a few conjectures flying around. So, okay, one of them is that you can, let's see. Provable security is saying something like we have a proof, a mathematical proof, that there is a probability of like 2 to the negative 100 that a prover can cheat. Okay, that's great, because that's a really low probability, and it's proven. Now, let's say we only have like 2 to the negative 80, so that's less good, and now we'll do 20 bits of proof of work. And what that means is that the prover is it's like normal proof of work. Like the prover has to create a certain number of hashes before it's allowed to prove. And so the idea is that 2 to the negative 100 security is good, because it means that a prover would have to try so many times before they get somewhere, more times than what they have computational resources for. So it's like, okay, if we just throw that at it, then it's fine. But I don't know.
And conjecture, that means in this case is that we don't have the mathematical proof, but nobody knows how to exploit it yet. It doesn't mean that there is somebody may find a way to exploit it, but we just don't know of a way to exploit it right now.
Which is the same security we get from SHA-2 and other hashes.
Right.
Like this is actually, we're often operating in conjectured security. And somebody else would have to describe why this is true, but in Starks, you have this unique characteristic where you can actually prove the security of the system, like she was describing a minute ago. Is like, you sort of know how much work needs to be done, and therefore you can actually generate a mathematical proof of the security.
It's true that hashes are conjectured. However, they have had decades and decades of like scrutiny from communities, from the entire security community, not just like the cryptography, not just the zero knowledge proof community, but
and like where does this like 2 to the 20, let's say, bits of proof of work come from? Like, is it just natural in the fact that the work that you're doing to do these ZKVM proofs for like a moderately sized program is computationally intensive, or do you actually have to, in your implementation, like have loops that their only purpose is to do this proof of work?
Yeah, that's pretty much
It's a parameter that you say, okay, for this proof I want to have 20 bits of work. For this proof I can go to 24. 20 bits is usually fairly acceptable. It's negligible. It's very, like on a CPU, it's very quick. You won't notice it from the user. But you can go like up to like, let's say if you wanted to get more bits of security, you could go like 24, 28. It just like, it will take much longer to generate the proof, but you can compress the proof size and make it smaller because you maybe, or either you compress the proof size or increase the security level. So there's all these trade-offs. I think the other aspect of this is that like we're all now using, or most of us are using like around 100 bits of conjectured security. Like there are very few projects that I'm aware of that like use more than 100 bits or use provable security. I think provable security is definitely one thing we want to go to. The other aspect is we probably want to go to more than 100 bits of security, and this is not something that we need to do right now, my personal opinion, but like in a span of like 5 years or so, ideally we would get to 128 because like, Bitcoin network, for example, does like 96 bits of work in a year.
Oh.
So
yeah, that's true. Also, computers are getting more powerful, so you have to be able to adjust for that.
So hopefully like 5
yeah.
years from now, we will all be in like 128 bits of provable security. For this, we need to make advances both on like implementations and like theory and all of that stuff. I think one other thing I want to say, so this is there are different facets to security. Like this is one. I think the soundness of the constraints is in my mind is one of the biggest ones where
That's true.
In other places, like I think we have tools and figuring out how to do it. Soundness, I think like you can do formal verification and other things, but like I don't think anything is bulletproof in there. And like you try to make constraints as simple as possible. You try to like audit them, you try to do it, but like I think this is like a big thing that worries me personally is like a basically missing constraint problem.
Yeah, I don't think, like a really important conclusion of what we said here is, I don't think people realize you can trade off performance for, like security for performance.
Yeah.
One way to make it go faster is just to actually make it less secure.
But
So-
then what's the point of doing it at all?
Yeah, exactly. So
that
we need to
makes-
be much more conscious of the fact that security really matters here in performance context.
Are you hit?
No, I'm just saying that we need to get more people to generate all that usage, right? Otherwise, if nobody's using it, then why worry about security, right?
Which converging on a standard would help for that as well.
And
Right, yeah.
Brett, are you saying that other projects aren't setting their security parameters properly?
Brandon's trying to make this spicy, but I'm not going to let him.
Okay,
Yeah, I mean,
I'm
look,
just
like,
asking.
You should have a verifiable trusted setup. Like, I'm not going to point fingers or name names or anything, but like, yeah, I think we've gotten, because these proof systems have been so slow historically, we've become laser focused on performance, and we're not talking nearly as much or thinking nearly as much or asking nearly as much about the security of these systems.
Yeah,
Okay.
I also want to make one distinction, sorry. Like frequently, or at least in the past, and maybe still right now, like you can have like much lower level of security that people run, even like there was some like at 60 bits or 40 bits, and this is obviously unacceptable in a kind of open setting, but like sometimes those systems are like, I think it's okay to run, let's say, at 80 bits if you're centralized prover, you are the only one doing proofs. Like as soon as you go decentralized and like people can do proofs, like that's like becomes super important. I mean, you don't want to have like 20 bits of security or 40 bits of security, don't get me wrong, but if like 100 bits or 80 bits may be acceptable for now if you're like a centralized prover because you don't, nobody else can generate proofs. You're kind of like making sure that you are the ones who cannot cheat. You're kind of only protecting against yourself, and you are in that case a company that people can come after and all of that stuff. So it really depends also in what setting you're running. So in some cases, like it may be okay-ish, at least for now. In some cases, you should like obviously do much better.
That's true.
Thanks. So we're out of time. Thank you, everyone.
Yeah, thank you.
I mean,
Thanks, Brandon.
Oh, we have a question. Oh, we're allowed to do a question.
Okay,
Great.
thank you. Really fast question for Risk Zero. So you mentioned that you just need like 20 seconds to prove a block for the Ethereum. So I can assume that the block gas would be reach up to 30 million gas, right?
I'm sorry, I don't understand the question.
Okay.
The 30 million gas fits in where? The proof itself is only less than 300,000 gas to verify on chain.
Okay, so my question is, how much dollar do we need to prove a block?
How much dollars? Is that
Yeah.
what you said?
Yeah.
What kind of computer do you have? No. Yeah, so we shared some numbers. Tycho did a significant round of testing on like sort of our private cloud cluster, a service we called Bonsai. And we got up to, I think, 25 megahertz, so that was 90 seconds to prove the average Ethereum block. I don't know how much, obviously Ethereum targets 15 million gas. I don't know that that's the actual average, but so that block in 90 seconds is about, let's assume, about 15 million gas. We've since, like in our next release, it's probably 40% plus speed improvement on that, just because, again, the executor was the bottleneck there, and we're up to about 35 to 40 megahertz on this instance type that we use. And so that'll bring the time down to about 60 seconds. Cost on that is well under $1 to generate that proof. I don't know the exact numbers right now, but I would say if you have you're running your own hardware, including the cost of that hardware, cost of financing that hardware, and the power, everything, it's like close to 50 cents, which is really incredible. We can prove mainnet Ethereum today for about a little over $40,000 a month. And again, it's getting like next release, that'll get 40% better. We have at least another 4x in mind. There's just tons of optimization still. So it's just, it's getting ridiculously cheap.
Awesome.
Thanks. We are out of time, right? Okay. Well, we're out of time. Bye.
Thank you, everyone. Please, a round of applause for them.
Thanks, Brandon.
Yeah, thanks to all the panelists. Forgot about that.
That was awesome. Brandon, you did amazing for a first time panel. All right. Okay, so we have to get right up to the next thing on the itinerary for today. And we have an interview with Omar and the beautiful Alice up next. So you can have a seat. So I will leave you to the beautiful hands of Alice to take on the interview session with Omar. Thank you.
Thank you so much for the intro. Hi, everyone. I'm Alice. I'm from ZKM and House of ZK. I'll be interviewing Uma from Succinct. Very excited. They're doing a lot of work making ZKPs more accessible to developers. So very excited to dive into that. Yeah, thank you so much, Uma, for joining us. And I know that you and the Succinct team are on a mission to make ZKPs more accessible for developers and really want to dive into more of that. So really excited, and thank you so much for joining us today.
Yeah, thanks so much for having me.
Yeah, of course. Okay, let's sit. I was wondering if you could go into some more details about the origin story behind Succinct. So what was the intention behind developing a RISC-V based ZKVM and the problem areas that you're trying to solve with it?
Yeah, so we've been building in the ZK space for a really long time. We originally started by building a particular application of ZK, ZK bridging, and we had built with circuits. So we were building with languages like CIRCOM, custom SDKs and DSLs like Ponky2. And honestly, our team was just really tired of that. It was really difficult. It took months to build a particular application. And we kind of felt that it wasn't sustainable and it wasn't really the future of ZK. We quickly realized that the future of ZK was having a general purpose technology where you could just write normal code for any application and then prove it. And we became very bullish the ZKVM approach, where you can just write Rust, you compile it to a normal instruction set like RISC-V, and then you prove it. And we thought that basically ZKVMs are the future, but it's also really important that they're very performant. And the existing options out there weren't super performant, or they weren't super general purpose. You had to learn a specialized language. So we kind of set out to build a very, very fast ZKVM where you could still write normal code. And that's what we built with SP1.
Nice. And then you talked a little bit about how originally you were first focused on the circuit design approach. And there has been some recent debates on whether the future of ZK is more going to be towards circuits or towards ZKVMs. So like over here, you're more of an advocate towards the ZKVM-based approach, but I'm wondering if we could discuss a bit about the trade-offs that exist between both approaches. So maybe like the benefits that circuits may have over ZKVMs, vice versa.
Yeah, so for those who don't know what a circuit is, basically you take your computation you want to prove and you break it down into this very primitive add and multiply gates, and it looks a lot like writing very, very low-level assembly. So the trade-off is that the developer time is probably like 100x. It's 100x more complicated. It requires 100x more expertise. It's just very, very difficult. And with the ZKVM, you can just take the same computation and write it as normal code. So in terms of developer velocity, I think the ZKVM approach is probably 100x better. In terms of performance, circuits are theoretically better because you're hand coding for your particular application. For your particular computation, you're kind of hand coding the specialized circuit for it. So there's less overhead than a general purpose approach. That being said, in practice, we found that our ZKVM is actually sometimes more performant than circuits because we can really optimize it because there's so many applications and developers building on top of it. So you can think of it as like a normal programming language, for example, like JavaScript, where JavaScript inherently isn't a super performant programming language, but because so many people use it, you know, the browsers have gotten really good at running JavaScript in a very optimized way. They do JIT compilation, they do a lot of different techniques, and for us it's very similar. Like, because there's so many people that use SP1 in our ZKVM, we run it on GPUs, so we implemented a full GPU prover. We've had this system of precompiles where you can basically have specialized circuits talk to your main RISC-V ZKVM, and that gives it a lot of performance, and you get the best of both worlds. And there's a bunch of other tricks that is generally difficult for any circuit developer to do because it's just one application, so usually it wouldn't make sense to put a lot of engineering effort into just one application. So we've actually found that our ZKVM outperforms circuits, especially with our precompiles, for the grand majority of use cases that we've tried. I would say the one exception is for client-side proving. If you want to do proofs on your phone, or a really restrictive environment like your browser, where you're not able to run code on a GPU, you're running it in your browser with WASM, or you're running it on your phone, which doesn't have that much memory. Their circuits are still more performant than ZKVMs, but I'm confident that if that became a priority for our team, that we could also do kind of a similar level of optimization to kind of get the performance on par.
And it's great that you're taking that approach of combining the best of both worlds. And now for ZKVMs, even though they're more generalized, we can do more specific optimizations on there as well. So I think that that's a very great stride towards, in general, just making it more accessible. And I also wanted to ask you a bit about adoption as well. So, I mean, in recent years, we've seen things like proof generation costs becoming lower, developer experience, like with what Succinct is doing, making the developer experience more accessible as well. Despite kind of these advancements, we're still not quite at the stage where ZK has become mainstream yet for developers. I'm just curious to hear your thoughts on what sort of challenges and limitations still exist in making ZK more accessible and for mainstream adoption.
Yeah, so I think the biggest driver of proof volume over the next few years is going to be ZK rollups. I think every rollup is going to be a ZK rollup using a ZK VM. And actually recently we announced our OP Succinct integration where we take OP Stack, which is a very popular rollup framework, we put it in SP1 using their Rust implementation, and then we can convert this optimistic rollup stack into a ZK rollup stack. And I think that's kind of just the starting point of how everything's going to go. Like all these rollup frameworks on Ethereum, OP, Arbitrum, all these things are going to be ZK provable with a ZK VM. And in that sense, I think that's kind of mainstream adoption. If we succeed on that goal, then every user will be transacting on a ZK rollup. They might not know that it's a ZK rollup. They're not going to, developers still write Solidity, users still transact with the EVM as normal, but underneath the scenes, it's secured by ZK. And so I think already we're actually on a great path for mainstream adoption. It just it might not be super legible or super visible to the end user. There's also a lot of other ZK use cases that I'm excited about outside of blockchains. So for example, like attestations, identity, verifiable like image editing, all that kind of stuff I think was really blocked on the existence of ZK VMs. Like you couldn't write all those computations without having a general purpose framework that takes any normal programming language. You were never going to write a circuit for that kind of stuff. So I think now that ZK VMs have actually come into production and are actually fast only over the past year, or really only over the past few months, now there's a lot more of those applications that builders can experiment with. And actually there's a lot of builders experimenting with that stuff with SP1 even today.
Yeah, and I'm personally very excited to see those real-world use cases come up, like even beyond the blockchain context as well. But just going back to OP Succinct, I'm very curious to also hear about the integration process that devs need to take if, say, they wanted to upgrade their OP stack to a ZK rollup. What does that look like, and are there any sort of customization options available? You also mentioned that you want it to be as seamless as possible, so they don't even realize that they are using a ZK-based rollup. So I'm wondering what that process looks like as well.
Yeah, so the beautiful part about SP1 is you just take Rust, you stick it in, and you can use proofs. And so for the OP stack, we didn't have to do much for the integration, which was very much by design. They'd already implemented their state transition function in Rust. We were able to take that code, stick it in SP1, run it, and do a very lightweight minimal integration where thankfully their stack is very modular and very pluggable. So we could just plug in the validity part, and instead of using the Optimus default proofs, we were able to use the SP1 proofs. So from our end, we actually did the integration with the help of the Optimism team. But in the future, if there's other roll-up teams that want to use SP1, I think the integration would be pretty similarly lightweight and pretty straightforward if you have good abstractions, because again, you just take your normal code that you're using for your state transition function. A lot of teams already use Rust, and then you just stick it in SP1 and it kind of just works.
Oh, nice, nice. And also very curious, just transitioning a bit onto the architecture side for SP1. One thing that stood out to me the most was that you guys offer developers the choice of different prover modes. So like, for example, like the Stark prover mode, a compressed prover mode, and Groth16 prover modes as well. So I was wondering, in providing developers that kind of choice, what does that enable?
Yeah, so we have two modes of proving. One is generating Stark proofs. Stark proofs are usually a bit bigger, so they're like hundreds of kilobytes, and you can't verify them on EVM chains because it's too big, that's too much call data. And then there's Groth16 or Plonk proofs, which you can verify on EVM. They're only hundreds of bytes, so it's very cheap to verify. It's like between 200K and 300K gas. We offer those two different modes depending on where you're using your proofs. So if you're using your proofs on Ethereum or another EVM chain, you're probably going to use Groth16 or Plonk. If you're using the Stark proofs, you're probably verifying the proofs like on another device or not in an on-chain context. Generally, we see most of our developers using the proofs on-chain, so most people use Groth16 or Plonk. But we offer both options because just more flexibility.
Yeah, nice. And I do like that idea of providing devs with that choice depending on their kinds of needs or what kinds of use cases they're building. So that sounds all great. Also wondering if we can touch upon, which you briefly mentioned, about the precompile options that you guys have. So maybe just some intentions behind designing an architecture that was precompile centric, and also with having or enabling developers to have their own custom precompiles. What does that enable?
Yeah, so generally what a precompile is it's a specialized circuit for a specific operation, like a hash function like Ketchak or SHA-256, or verifying signatures like SecP256K1 that talks to our main RISC-V CPU. And the reason you'd use a precompile is that it's much more efficient for that particular operation than having to do it in RISC-V instructions. So you can kind of think of it as in normal programming languages. When you want to implement something really optimized, you implement assembly directly. In ZK world, we implement a precompile. So you can kind of think of it as ZK native assembly. One of SP1's major innovations was our precompile-centric architecture, where our architecture, we did a lot of clever cryptography to make it so that you can have very general precompiles, where you can have precompiles for Ketchak, precompiles for SHA, precompiles for a bunch of different elliptic curve things. And that's really what made SP1 an order of magnitude faster than other options on the market, because you have these precompiles for these very specific operations that are very frequent in things like proving an Ethereum block. So we have these precompiles, they make SP1 super fast, and it's also pretty easy for developers to add new ones, thanks to like our open source architecture and how, in general, the cryptography behind the scenes and how we've set up our APIs and SDKs. For example, our intern over the summer, he learned everything from scratch. He was a superstar, he's very, very smart. But he added a precompile for the BN254 curve, which is used in Ethereum. And we've had other people and other teams add precompiles as well to SP1. And that can really help accelerate any performance bottleneck. So basically, you write your program in RISC-V, and then if you find there's a performance bottleneck that's something very repetitive that can be accelerated through a precompile, you can add it yourself, thanks to a very flexible architecture, which is pretty awesome.
Yeah, I think that's awesome as well. So thank you for mentioning that. And I also wanted to touch upon some of the other kinds of offers, like product offerings that Succinct has. So there's SP1, and then you guys also offer a proving network as well. And that proving network I know is decentralized. So I'm wondering if you can also touch some light onto the value proposition behind making a proving network decentralized, and what kinds of implications that brings compared to, say, a more centralized approach.
Totally. So for ZK or running SP1, you can do it locally on your laptop. Now, it's not really a fun time because it's a very computationally intensive process. And actually, like, we've gotten a lot of performance benefits from running it on GPUs, and most people don't have like, a GPU sitting around in their house. Additionally, you can get a lot of speed benefits by running proving not on one GPU, but across hundreds of GPUs, which we regularly do in our cloud cluster. We have hundreds of GPUs that we help people run proofs on, but usually people don't want to set up that infrastructure. So Prover Network is just a mechanism for anyone who wants to use SP1, who doesn't want to run proving themselves. They can just send us a proof request with their program, their inputs, and then we generate a proof for them and send it back. And it just makes developers' lives easier. It's kind of a positive sum collaboration where they don't have to set up their own infrastructure and they can pay us and we can run the infrastructure much more cheaply and efficiently than them and also save them a bunch of time. Now, a decentralized prover network kind of takes that concept and adds and puts it on steroids. So instead of just us running our own GPUs and generating proofs, the idea with the prover network is that anyone in the world can plug in their GPU and help contribute proving capacity for SP1. And today we don't have that. Today it's just a prover network of size 1 where only we are generating proofs. But towards our long-term vision is to build this decentralized prover network where, like I was saying, anyone can join and contribute capacity and kind of participate in SP1 and Succinct and the future of ZK.
And in that long-term vision that you have for decentralizing your proving network, I'm wondering if you can talk about the roles within that proving network. So there'd be provers, there'd be people requesting for those proofs, and how exactly you would imagine those proofs to be delegated across the different provers.
Yeah, so kind of the actors in the prover network are the users who are sending proof requests. They generally send a program, they send a set of inputs, and then from that information, you have everything you need to generate a proof. Then you have the provers who are actually generating the proofs. And the biggest question is, how do you price the proofs? And also, how do you allocate the proofs? And how do you make sure that there's not too much wasted work where there's not multiple people competing to generate the same proof, because then that's just wasted GPU compute. And also, how do you price the proofs in a way where there's cost competition amongst the different provers so that the end value accrues back to the user and they kind of benefit from this competition. And that's some work we've been doing a lot of recently, and we're pretty excited to share. We have a lot of ideas on interesting cryptoeconomic incentives and mechanisms to price the proofs and allocate them that solve a lot of problems of doing a pretty naive solution. And yeah, we have some upcoming work that's going to come out on kind of that architecture and design and the mechanism of our prover network soon.
Nice, very much looking forward to that. And just back onto the topic of choice, specifically for SP1, I know that you guys also offer developers a choice of them aggregating their proofs. So I'm wondering, in what sort of scenarios, because proof aggregation seems to be a pretty big trend across a lot of ZK VMs, in what scenarios is proof aggregation maybe not needed? And what implications does it have when you provide developers with that choice on whether to use proof aggregation or not?
Yeah, so today verifying a proof on Ethereum costs around 200K gas, which isn't super expensive, but it's not super cheap. For example, on Ethereum, the minimum transaction cost is 20K gas, so it's 10x more expensive than that. With proof aggregation, what you can do is you can take a bunch of proofs, you can aggregate them, and then you can verify 1 gigaproof on Ethereum and amortize that 200K gas cost across many, many proofs. And you can make it so that the actual cost of verifying a proof after you take into account this average becomes much less than 200K. Maybe it becomes around 20K. So if you're a developer and you're really cost sensitive, then proof aggregation could make a lot of sense. If you care about latency, though, for example, you want to get a proof on chain as fast as possible, then aggregation makes less sense, because to have proofs to aggregate, you have to wait some amount of time to be able to aggregate them. Another case where aggregation doesn't make that much sense is sovereignty. So for example, if you don't want to rely on an aggregation service, you want to be able to land your proofs whenever, you want to control that cadence, then maybe using an aggregator doesn't make the most sense. So I think we offer kind of both options, depending on the specific use case. And for a lot of people, the cost of verifying proofs on Ethereum is not that bad. So they haven't needed aggregation yet, but maybe in the next year, gas prices will go up again, it'll become a big theme, and proof aggregation will become more important.
And so it really depends on the developer's needs. like what you mentioned with sovereignty, or if they're focused more on cost, latency, just depending on the use case that they're trying to build. Got it.
Yeah.
Nice. And also, I wanted to touch on the topic of open source as well, because all of Succinct's developments, including SP1, are made open source. So I was curious to hear your thoughts on how important you think open source is, especially for the ZK space and even the greater Web3 space.
Yeah, so I think all of crypto is generally open source, and I think there's a deep open source ethos to the ecosystem, kind of like from the original days of even like Bitcoin, where everything was done in the open. But I think also from a really practical perspective, beyond just ethos, it has to be open source for security, because if we had a ZKVM that was closed source, then who knows what we'd be proving. And so from our launch day one, we've always been open source, because I think it's just critical for people to know exactly what are the cryptographic statements that we're proving, and make sure that proof doesn't mean anything unless there's this underlying hard mathematical backing and you know exactly what's going on. So open source is really important. And we also think, the open source community is very nice and very compounding. So there's a lot of teams that have forked SP1, added their own precompiles, tried doing a bunch of optimizations, and we've even merged some of those things back upstream. So for example, the Lurk team, I think now they're called the Argument team. They're a really, really talented team, and they forked SP1. They added a bunch of BLS precompiles, which is really valuable for an ETH-like client. And then we merged those PRs upstream, and it was wonderful because we were able to leverage their work, and performance got a lot better on the Ethereum-like client use case. It went down, I think, by a factor of almost 20 or something like that. So yeah, there's like a 20x speed up from their precompiles. So yeah, I think open source is awesome, or not only needed, not only part of the ethos, but also very practical, helps other teams feel comfortable and good about adopting it. And yeah, I think the future of a lot of the ZK stuff is very open source for all those reasons.
So it definitely helps on the transparency side and also even on the development side as well. Great. And also curious to see, just scoping out a bit about your vision for the ZK space. So how do you see the space evolving in the next couple of years? And I'm also curious to hear about what the ZK endgame really means for you.
Yeah, I think for me, like in the short term, the most interesting and highest need consumer of ZK will be blockchains. I think for example, the Ethereum rollup roadmap has kind of needed ZK for a very long time. And there's actually a lot of technical debt that we've accrued by having these systems or rollups in production that are just multi-sigs, not verifiable. I think you kind of have to question, well, what are we replacing? The whole point of blockchains is trustless, decentralized systems. And a lot of the rollups we run today are not even trustless. So I don't even know if they should be counted really as rollups in the true sense of the word. So I think ZK is a burning problem for rollups and blockchain scaling today, and I think that will be the biggest driver of proof demand over the next year or so, or maybe even a couple years. But beyond that, I think ZK can actually do a lot. I think it's actually this new cryptographic computing paradigm. You have this old generation of cryptography, which was digital signatures that kind of brought authentication to the internet, right? You know who's signing something, and you can verify that with their signature. ZK is really powerful because it's programmable. You can verify anything. You can prove any computation. And with that extra flexibility, now you can start doing things that are more complex than authentication. So you can do things like, a verifiable credit score. You can verify that an image was transformed in this way. You can make sure that prove that not only this person has a particular public key and is a certain identity, you can prove complex statements about their identity. I am this person, I'm in this set, I have these properties, here's my credit score, here's some pieces of information about my nationality, without revealing, all aspects of your identity. So I think those are some of the things like authentication, credit scoring, insurance, stuff like that, where today, the only way of having verifiability is through government regulation. But with ZK, you can imagine now you have verifiability through this new computing paradigm. And I think I'm really excited about that on the 5 to 10 year time horizon.
And I like how you coined it as the new cryptographic computing paradigm, and how we're able to see the shift because of programmable cryptography. So lots of exciting new developments along the way. Just on this topic of vision, I'm wondering if you can also speak about some long-term goals that you see with Succinct and how you see Succinct evolving in the next, say, 5-10 years.
Yeah, I think, so far we've been really focused on delivering value to real customers and real users, and I think that's gonna continue no matter what. So even in like the short term, our goals are to make SP1 the best ZK-VM possible, and because we kind of have this pretty simple thesis that ZK is really important to blockchains and scaling, the future of ZK is ZK-VMs, and we want to build the best one. And so SP1 is the fastest ZK-VM out there today, and we want to keep on continuing that and making it faster, having better performance improvements, making it work for client-side proving and server-side proving, and just making it a tool that any developer can really use as easily as possible for as cheap and fast as possible. So I think that will always be a goal of our company. And then I think the other biggest focus of our company right now, well, there's two things. One is like the prover network. So basically taking SP1 from a piece of software to something that anyone can help contribute capacity towards and building this like global proving cluster instead of just us doing all the proofs for all blockchains. And it turns out that's actually pretty important for a lot of our customers because in blockchain systems, it's important things be decentralized. And so it's also important to them that proving is decentralized. There's no single point of failure. And then finally, I think we're just really focused on adoption and getting all those really exciting use cases out there and built. So for example, I think every rollup will be a ZK rollup. And OP Succinct is a great start towards that. But there's a lot of other stacks that people use, a lot of other rollups people use, a lot of other VMs that are not EVM that people use. And getting all those state machines proven in SP1 is a big focus. And all the other use cases that I talked about that kind of go beyond blockchains, I think it's finally possible to start working and iterating on them. So helping support those builders working on these kind of like more novel, far out ideas is also a big area of focus for me and something I am very personally excited to help those builders and founders work on.
So we're beginning to see the sort of ZK mainstream adoption coming here, and now it's just about like kind of embracing towards it. So very exciting times again that we're seeing. And yeah, thank you so much, Uma. Really appreciate you for being here today, and also really loved hearing not only about the what for what you're building, but the why behind it and the vision behind it as well. So really appreciate it.
Yeah, thank you so much for having me.
Yeah, thank you.
Okay, okay. Okay, we are back from the lunch break, and I hope you had something really, really nice because I did. I mean, the food area today was really, really superb, and I had a lot of meal. But before we get started with the first presentation for this afternoon, we have to give appreciation to those people who made this possible, the brands that made this very much possible. O1 Labs, Elio, ZKMs, Rig Zero, HBZK, and SciSec. And with that, we will say thank you so much, and we will get right into the first presentation from Lucas Fraga. Thank you.
Okay, thank you. Hello, everybody. My name is Lucas. I work for ZKM as a ZK researcher. And today I'm going to give you a very brief presentation of about what ZK MIPS is, what it means, and like the choices that we made during the design of ZK MIPS. So, okay, first of all, ZK MIPS is our ZK VM. But what is a ZK VM, right? A ZK VM, in simple terms, is a proof that a program was executed correctly. And technically, this means a proof of knowledge for the correctness of a computation. A proof of knowledge is a protocol where one of the parties involved wants to convince the other party that it knows something that it claims to do. And in the case of ZK VMs, the knowledge being claimed is the correctness of a computation, meaning the prover claims to know a sequence of states that matches the program definition. So what we need to prove here is that we executed the program and that this execution resulted in a sequence of states that are valid. And our goal when we started designing ZK MIPS was to produce a proof that is parallelizable. Okay, so ZK VMs, they usually take a long time to compute, and they also take a lot of space. So we want to make the procedure as parallelizable as possible so we can run this faster. And also we want to prove that is easy to verify. And in order to make a proof that is easy to verify, the first choice that we made was the instruction set. We chose MIPS. And why MIPS? Well, first of all, MIPS is simple, very simple. It is simple to describe, meaning it's also simple to prove, because in the proof procedure, you have to describe how the CPU works. So if you have an architecture that is easy to describe, you will create the prover easily. And because it's easy to describe, it's also easy to simulate. And we need to simulate the CPU in order to verify it. The verification procedure is basically a verification of simulation of a program inside the CPU. And besides being simple, MIPS is also very stable. It doesn't change much. I think the last change in the version that we used was like decades ago, so no bug has been found in it since then, and no bug will probably be found, so we don't have to update the logic of the proof once we write it. And also, MIPS is very popular. A bunch of languages support MIPS, and if we support MIPS, then we can support more languages more easily. So, okay, with this we can achieve the easy to verify goal. And to achieve a parallelizable proof, we carefully chose 3 proof systems. We chose Starkey, Plonky, and Graph16. So Starkey and Plonky, they are implementations of the Stark and the Plonk proof systems. This Stark proof system, without the Y, it is a proof system that is non-interactive, or at least can be made non-interactive very easily. it's also transparent, scalable, but it's not succinct, meaning it's easy to verify because it is scalable, but the proofs are not short because it's not succinct. But it does, it is indeed transparent because it relies only on hash functions, which is a good thing. And the non-succinctness is not a problem for the way we use Stark. So we don't really have to care with succinctness at this point. Plonky, well, the original Plonk, it can be easily made non-interactive too. It is not transparent, it is not scalable, but it is succinct. The Plonky that we use with the Y, it is transparent, is scalable, but it's not succinct because we use the library that we use, Plonky2, that implements this proof system, uses the Stark backend. So it inherits the transparency, scalability, and non-succinctness from Stark. And we choose these two proof systems because they are implemented in the same library. So it makes them easy to combine and to compose. So at some point, we need to prove one proof system using the other. And because they are in the same library, this is something that is quite easy to do. And finally, when we need a proof to be verified on-chain, we also use the Graph16 proof system, which can be easily made non-interactive. It is non-transparent, but it is very scalable and very succinct. And non-transparency is a problem because being non-transparent means that a proof system might have some toxic waste, but we remove the procedure that introduces this non-transparency by multi-party computation, meaning that a protocol where only one of the people involved in it needs to be honest. If one people is honest, then the proof system toxic waste is not trackable, and it increases the trust that people have in our proof system. It is very scalable and very succinct, which is good for on-chain proofs because we want to save gas. So a proof system that is scalable, it's easy to verify, and it will take less gas. And being succinct is also a good feature because the data calls to the smart contract, they take less gas. And finally, all those proof systems, they also support zero knowledge. So if you need private proofs, ZK MIPS can give it to you. So now, just to finish, I will present the layers from our prover, and I'll explain what each of these layers do. I like to think of ZK MIPS as stacked layers of proving. So stacked in the meaning that we start the first layer, and then we start the second, and then we start the third. And the third one, which was the last one to start, it's the first to finish. Then the second one finishes, and the third one, and the first one finishes. So how this happens is, in the first layer, in the execution layer, we execute the program inside a special MIPS VM. And inside this VM, we will pause the execution from time to time to collect what we call segments. Segments are pieces of the program execution that has a fixed size. So we log the first and the last state from each of these segments, and we are able, with these two states, to re-execute this segment later in order to prove it. And we do this in the modularization layer, where we recreate the segment, and we divide it in smaller segments that we call modules. The modules, they are instructions categorized by their types, their MIPS types. And we define 4 different modules for the MIPS instructions, and we prove each of these modules independently. And once these modules are, once they are proven with a star key proof, we combine them in the second layer using a lookup protocol. We use logup, and this logup is written as a star key proof. And once we have all the segments proven, we will combine them very in a similar way to the way that we combine modular proofs. And we will combine these segments 2 by 2 recursively until at the end we have one single proof for the entire program. And well, I have more slides, but I don't think I have the time to go through them. So I already made this presentation earlier, and it took me at least, I don't know, 30 minutes. So that's all I have to show for now. Any questions?
All right, thank you so much. That's super amazing. So right now, before we get into the next session, we could do a little bit of stretch. In case you want to stretch, I mean, your leg hurts, you could do that. I've been stretching since. You could stand up and stretch. All right, so without further ado, I think we'll just get right into it. The next session will be a panelist session of benchmarking standards. We're going to have Ishmael join up on stage. Is Ishmael around? And we're also going to have Brett and Ratan. We're going to have Ratan, then Pavel. Please do well to join us on stage. Please a round of applause for them. Thank you, thank you, thank you, thank you. Okay, thank you, thank you. Okay, everyone is here. Okay, so Pavel, is Pavel around?
Yeah, I'm right here.
Okay, sorry.
He's such a cool guy.
All right, so it's your
shy to
stage.
Awesome. Thank you for the introduction. So great to have you guys here on a panel. We have plenty of expertise here discussing benchmarking standards. We have, I guess, to the very end, we have Brett, the VP of Product at RISC-0. We have Ratan, which is the founding engineer at Succinct. And then we have Ishmael, which is the co-founder and CEO of Lagrange. Plenty of expertise in the sector of ZK proving, and definitely want to hear your thoughts and perspectives on benchmarking standards. But before we dive deep into this topic, let's first give a round of introductions, what your project does, and how you're accelerating the ZK space. So starting with Brett.
I guess we'll start at this end. Hey everyone, I'm Brett Carter, VP of Product at RISC-0. First started thinking about ZK benchmarking working for O1 Labs, the labs code behind MENA protocol. There's a former colleague right there. Yeah, so great to be here. Thanks for having me.
Let's see if I'll try this one first. Hello. I'm Ratan. I'm a founding engineer at Succinct. We've been working on SP1, which is a ZKVM which allows you to prove any Rust program. Most recently, I've been working on OP Succinct, which lets you prove any OP stack chain in ZK.
Thank you all for having me. My name is Ismail. I'm one of the co-founders of Lagrange Labs. We focus on two core things. The first being a ZK coprocessor that allows you to prove SQL-based computation over blockchain data. Think Dune Analytics, but verifiable on-chain. And the second being a decentralized prover network that powers our ZK coprocessor and other things for some of our friends. You want my mic?
Sure, I guess we'll share. All right, thank you for the introductions. I guess we'll get right into it in terms of the current state of benchmarking in the industry and where the primary challenges we face today in achieving fair and reproducible results. I guess we could start off with Ismail. Ismail, sorry.
I'll need my mic back for that. But so I think one of the difficulties in benchmarking standards is the decision of what the specifications of hardware and the equivalent comparison is across different systems. So we often talk about the difference between academic benchmarks and industry benchmarks. In an academic benchmark, what you want to do is find a normalized comparison between both systems. If system A can't do recursion, system B shouldn't be run in a recursive setup. If system A can't be parallelized, system B shouldn't be run in a parallel implementation. So you should compare them in a way that is agnostic in academia. In industry, the question is, for the performance of a use case, you should say the best running on system A versus the best run of system B, which one is more performant? Because that's the question that matters for a customer and end user. It's less of an intellectual pursuit and more of a practical one. And I think this is where we run into issues as an industry when doing benchmarking, because we either will take the approach of, I'm going to compare my best to your worst, or we take the approach of, we're going to limit the features of all of them and not have a comparison that's practical to end users.
Yeah, I think Ishmael brings up a great point, which is, I think I mostly agree here too, so I'm not sure if we're gonna get much contention on this point, in that I think that industry benchmarks are really the thing we're optimizing for. Like, what do people care about? With ZK, it's two metrics, right? It's like cost and latency. And one really nice part about ZK is it's fully self-verifiable. So it doesn't matter where your compute gets done, it just matters that it gets done. And so as long as you're optimizing for benchmarks that output those two metrics, you have the things that you need. And I think in the early stages of ZK, it was interesting to take an academic approach. But I think as all of us here probably have noticed, what actually matters to the people that are using us is the fact that, that cost is getting better, by an order of magnitude year over year. The latency is getting progressively better in the systems too. And I think that is the right approach.
Yeah, what's interesting, lots of alignment here. There's a lot of things you could measure. You shouldn't necessarily measure all of them. I remember Delendum wrote a really nice sort of ZK benchmarking article maybe a year or two ago, and Remco Bloemen did like a really great analysis of proof systems and their polynomial commitment performance. But in practice, those things don't matter too much, right? Like how that sort of gets to the end user, it's so far down and abstracted, those things aren't super useful today. So I think like application benchmarks, how fast can we prove an Ethereum block? What does that cost, et cetera? That's exactly where we want to be focused. What's interesting is like cost is actually something that's quite difficult to measure, and there's essentially no standard for. I think the closest we have to standard is like, hey, are you doing it on the same AWS instance as me? We're sort of using AWS and the fixed costs that are transparent and public to sort of measure cost, but that's something there's plenty of room to improve on as well.
And I think this is a good point too, which is like, I think until you reach a point where there's a market price, you're not going to get there. Yeah. And so I think right now, most of the proofs that are being generated are by the teams that made, the ZK VM or the ZK system. And when that changes to be a market system, then I think we'll have proper industry benchmarks. And that like, there will no longer be a way to enforce, a different cost than the one you got, which is what the concern is with like, making sure people are running on the same AWS instance. Instead, the market will decide that, hey, I'm only willing to offer this service for this price, and that is what's going to give you the actual benchmark.
I mean, I think in many of these services, cost and latency are trade-offs. You can get lower latency by going more parallel on more expensive instances, and you can decrease cost by putting something on a single instance that's cheaper, that's not a GPU instance, and just run in sequence.
It's surprisingly not true in our proof system, because we can actually it's actually expensive to run it on a slow machine. Like for example, we could put it on a CPU instance that's quite inexpensive, but it does run much longer than it takes to sort of, you don't get any actual cost savings in that case. You're right though in that having hundreds of machines available to generate a proof on does have an associated cost with it. And there's something that we called, like we've done pretty rigorous cost analysis on these things. There's something that we called, actually can't remember the exact term, but essentially the downtime or like the latency, those machines not being active does have an associated cost. Once you have them though, like for example, you can keep up with all of mainnet Ethereum today for just a little bit more than 100 GPUs roughly. And so 100 GPUs aren't actually really that expensive. And so the downtime you're not using those machines, also isn't that expensive. So the costs are just coming down so dramatically. I'm not sure that's quite as true as it was in a single machine instance or case as it is in a single machine instance or case.
Interesting, but you don't have any, but in theory, if you could go unbounded on how parallel you do your computation, you can do successfully larger proofs that you'd recursively combine. So I'd assume the statement that you could prove is fundamentally constrained by both cost and latency, which you can trade the two of those.
Yeah, it is. I guess so one of the important drivers here when it comes to performance is actually the speed at which you can execute today in a general purpose ZKVM. So for us, I don't quite know where Succinct is at right now, but on the average machine, it's like runs at about 30 megahertz. So we actually can't go unbounded is partly what I'm saying. We can go, we can only go up to like 100 machines, and you're bottlenecked at sort of that 100 machines right now.
Okay, that makes sense, because you have a bound of 100 machines.
Yeah, exactly.
Okay,
roughly.
Right.
Yeah. And I should specify, that's on an individual proof. If you could split up a proof into multiple smaller proofs, you can also parallelize those 100, which, so there is some aspect to which, like there is a trade-off at some point. It's also an engineering complexity as well.
Yeah.
Yeah, I think I would agree here that cost and latency don't trade off as they do in normal systems, or as in previous ZK proof systems.
Or in computer science more broadly, right? Like if I was doing distributed computation of any type.
Sure, but the thing that's interesting here is like, okay, let's say you have 100 units of compute that you need to do. My point is, you can do 100 of, like, the parallelization cost is not that high. It's kind of my point. Like, the cost that's induced by parallelism is much less than the units of compute. So like, kind of the point that you're making is, let's say we have 100 units of compute that we have to do. We're okay doing this on an instance that can do 1 unit of compute per timestamp. So like, let's say it does 1 unit of compute per second, but now you're saying in a parallelized system where let's say we want to do it in 1 second, you're going to induce a lot of units of compute additionally. My point is that additional induced cost is not that high. And so like what you see is that cost and latency don't trade off that much.
Interesting.
Yeah, I think the other assumption there is that like these computers are somewhat scarce, right? And in reality, like, there's probably 100 people in this building that will give you access to hundreds or thousands of GPUs, and so we're at a certain place in immaturity in the market where supply significantly outweighs demand in terms of compute and for ZK proving.
Yeah. So it sounds like there's consensus and alignment in terms of the overall like the cost and the latency for this. What about hardware requirements, like in terms of hardware standardizations? The talk about GPUs and these things, like should there be, and you said that if everyone's running on the same AWS machines, then essentially we are all in alignment. Like if one performs better on one type of machine versus another performing better on another type of machine, like should the machines themselves be standardized as part of this?
I think the better question to be asking is like, what is the purpose of benchmarking? It's like the purpose of benchmarking is to see how can we generate this proof as quickly as possible and as cheap as possible. And I think as we've mentioned, like the way that you actually verify the cost, to me at least long-term seems like the market cost. Like there will be some market for this in the future. There will be some associated costs that people are willing to offer this service at. And that's what's going to tell you how efficient that proof system is. Like, let's imagine that you can put any proof system on any hardware. With some amount of effort, you could do that. Now the question becomes, who's willing to offer this service? And that's what tells you, like, for Bitcoin, you have like the cost of hash rate, right? And like, you can tell like who the most profitable miners are by where they're placing their Bitcoin miners around the world, and that tells you, okay, like this is the cost that I'm competing with. I think for proofs, you're going to see a similar dynamic. So I think it's interesting in that we're in a transitory period from academic benchmarks into industry benchmarks. And so we're making these like weird trade-offs where we're like, no, like on GCP on this instance it's better, no, on AWS of this instance is better, and like that clearly is directionally wrong. Like what we should care more about is like people are willing to offer the service for this price. That indicates what the price of doing this workload is on this specific proof system. Proof systems will have, they'll diverge in their costs for different workloads potentially. Maybe, one proof system will dominate on all workloads. Maybe there's a short time where, like, let's say, for example, one proof system is optimized for, specific kinds of operations more so, either, with like accelerators or precompiles. There will be divergence there, and so I think that's where you're going to see people are willing to offer the service at some cost, and that's what actually matters more so than like picking a specific instance. It's just like what cost you're getting quoted for proving a workload.
Yeah, I would agree. I think normalizing to the same instance for a bunch of very different proving backends is not the correct approach. I think what you want to do is say if you were to run proof system A within a certain cost constraint at the best possible speed you could run it, or a certain time constraint and the lowest possible cost you could run it, which would be better? And so I think, very generally, like that is what's relevant in industry. I think the comparison to hash rate is very apt. And I also say, I think, the more benchmarks we're able to produce that kind of look at actual data of execution, for example, proving Ethereum, for example, proving the cost of a transfer, cost of a DEX swap, the better we'll be able to determine that which proof system is more relevant for certain applications in production.
Awesome. So I guess like the focus is on the real world. What the real world proof market, what people are paying for specific operations.
One point I'd like to make is I think we should send Fibonacci benchmarks to 0. Like those should not exist. Like why? Like I've heard multiple people ask me like, oh my God, like this proof system is better on Fibonacci. I'm like,
which is like cute when you could only write a circuit to do Fibonacci, right? But in a general purpose ZKVM, which has much more utility than that, they're pretty useless.
Like I think the bar for what you are benchmarking on goes up over time, right? And I think we're at a point where we should stop as an industry like benchmarking on things that don't matter and benchmark on things that do.
And in terms of the things that do matter, in terms of what the direction. So I know that the OP succinct, like you're directly working on that aspect. Are there any other types of benchmarking that would be I would say like where do you see more of that being used as relevant metrics and statistics for that?
Yeah, I mean Ishmael can feel free to jump in.
No, the question's to you. You jump in first.
I think rollups are a clear use case. I think that OP-Stack is one of many, there are many different rollups that have many different configurations, right? Teams roll their own rollup stacks. And I think that for benchmarking, it's probably good to have consolidation around, one specific kind of rollup stack, or you can maybe test the common ones. But then what's interesting is like people are also going to test for their own rollup stacks what the performance is. So I think rollups are a clear one. I think bridging is another use case where it's like you have some recurring proof that's being posted in order to migrate the state over. I think in applications that kind of have this recurring nature, benchmarking on the real cost and latency matters a lot. And so I think other applications that fall in that category probably would be things that I'd benchmark. So rollups and bridges are clear.
Proof recursion is probably a good third category that's emerging.
Yeah,
like
I think
the cost of maintaining proofs from disparate proof systems and aggregating those in an individual proof.
Fully agree with that. I would also, as a counterpoint, I would think that we need to be more specific on what is actually being benchmarked when benchmarking rollup execution, because it's a very different cost to prove a transaction versus swap versus a precompile. And I think it's, we talk about, oh, you can prove a transfer in a fraction of a cent, but that doesn't really give the full picture of how much it would cost to run a ZK rollup within a ZK VM for a material period of time. And I think that's part of the issue that we still face with our benchmarking, because these are still not practical when we are looking at very specific types of transactions that might not be reflected at the correct scale in actual live execution environments. So I think a much more relevant benchmark is, for example, proving Ethereum block execution, which has a very large heterogeneity of what the transactions, in fact, that are included in that.
Yeah, what's funny about that is there's still quite a bit of variety in the size of blocks, for example, right?
It is, but like
So-
over a duration.
Sure, yeah. Like I think mainnet is actually a good standard, right? Like some sampling of mainnet blocks, having an average gas size, of et cetera. Because I've actually realized in some of, we talk about Ethereum block proving, well, most OP blocks are empty, for example. So you can prove those for a lot less expensive, to prove an OP mainnet block on average than it is to prove an Ethereum block. You also have difference in block frequency, right? So like the operational cost of running a rollup itself can vary because of those parameters.
Yeah, I think just prove the chain and you'll know how much it costs. Yeah, I think that's the right metric for rollup benchmarking is like, this is what we see with OP Succinct is like, you can take any OP stack chain and prove it. And like, we can determine the cost for that, like very concretely. And in a world where, many different provers, then you have like a market cost for that as well. And that gives you your benchmark.
And so could you determine that a priori to them working with you, or would you have to go through and prove the whole thing to tell them how much it costs?
You have rough metrics that have like, it depends on what hardware you're running it on, right? Like for example, pricing is difficult because let's say we even isolate it to cloud. Like people have reserve deals. Some people might be using a home data center that has different costs. So cost is difficult for you to assess a priority without knowing what the cost of compute is for an external party. Like for example, let's say you have a bunch of compute. I can't tell you how much it's gonna cost for you to run it. Only you can tell that. But you can see before you run it, okay, let's say you've been running an hour of, OP mainnet blocks or Ethereum blocks. You now have a good gauge of how your execution of that block maps to the actual proving cost. So you can execute it for a fraction of the time that it takes to prove it, and it's quite a cheap operation, and then you can use some regression analysis to determine, okay, given this new block, here's what it's going to cost me to run it. So I think there are actually quite good metrics that you can get from seeing how your workload performance on your own whatever compute that you have, and then determine your costs. But it's compute provider specific.
That's interesting, because that's a comment on the lack of the value of benchmarks prior to a customer directly engaging with each of the teams. Because if you require them, but that's a very interesting point, because that's kind of against a lot of the early topics we're discussing on the panel about having industry-wide benchmarks. This is a comment for not having industry-wide benchmarks. It's a comment for saying we shouldn't benchmark anything. We should instead just directly engage with counterparties and have them test each system and see which one is more performant for their workload.
I think to Pavel's point, it's more a comment about the lack of an open market for proofs. That when there is an open market, a transparent market for buying proofs for various chains, it'll be a lot easier to have these standards, and we're just lacking that today.
Got it. So in terms of the overall what the discussion is proving based on the real world application. What the real world application is proving Ethereum blocks, and in that way, we can of course design our own proof systems to be highly optimized for that specific use case. But then having it being with an open prover marketplace, you can essentially see how it works in the real world on various different types of machines, and how those machines can then generate proofs efficiently based on the variety of these things.
I'll say too, I think like the closest thing we have to that right now, and maybe this will give like Pavel a laugh, is like when you have a team that's working with the ZKVM, the best way to figure out what the cost to prove your given payload is to just like port the SP1 guest into RISC-0 or vice versa, and then ask them what the cost is, and that's really the most practical sort of assessment you can do in terms of cost right now. Eventually, as we have these open markets, and actually, I would like to ask Ismail to some extent. We're sort of hogging the agenda, mostly talking about block proving and stuff. How should we be thinking about cost versus latency and sort of like historical proofs on chain as well? How are you guys thinking about the cost drivers for those?
Yeah, that's a really good point. So for us, it really comes down to how many data elements are touched in a given proof, as well as fixed costs on pre-processing of data. So the way we do our proving is really in two steps. We have a pre-processing phase where we use an updatable vector commitment that our team published a paper on recently called ReckleTrees to generate a batch proof of the inclusion of a large subset of data within a given blockchain, either receipts, transactions, storage. And whenever a new block gets in, we update that vector commitment to include the new data. And what we prove with this inclusion proof is both the existence of some subset of elements within the tree and the equivalence of the data contained within the tree to a new data structure that's more performant to compute proofs over. We remove the RLP encodings, we remove the catch-back hash, and we change the arity of the tree. And then so we have, in essence, have a giant binary Merkle tree built with Poseidon 2 that's much more performant to generate proofs over top of it. We can change it to an algebraic hash if we want. In the future, there's nothing that constrains us there. And then we can compute very, very large queries over this new optimized structure because we no longer have to deal with what is a very large unbalanced tree of a varying arity, which is the MPT tree with obviously block connection. And so because of that, we can go very far back in queries or over a very large range of blocks in queries in a much more performant way. And so for us, cost drivers are two things. It's how much does it cost to generate that pre-processing for the contracts that we need to generate proofs over, then how much does it cost to generate an arbitrary query over that data when requested. Generating the arbitrary query is actually very cheap, and it amortizes the pre-processing cost across it. So it's very much like a volume-based pricing model, the same way you'd expect in a lot of software. If you need to make a very small number of queries to a data set that's very large, and you need to store that data set, it's expensive. If you need to make frequent queries to a very large data set, it's on a per query basis much cheaper.
It's interesting because just a realization just now that's maybe useful to externalize and say is, when we're looking at the cost of proving a chain, you sort of have two different paradigms. You have optimistic rollups, you have validity rollups. And in a validity rollup, the proving cost is incremental to the operational cost of the optimistic rollup, right? It's an additional cost if you think about it on the balance sheet. When you're using a coprocessor, you're actually not like sort of competing with another prover, you're actually competing with on-chain execution, right? So that's actually, I think it's useful to actually look at, and I'd be curious to know in Lagrange's case, like the amount of compute you were able to offset from the chain itself and how those costs sort of compare.
So it's not just compute, it's storage. Because if you want historical data available at the current state of the chain, you have to store that.
Yeah.
And every storage read is I think
3,000 gas, right, for S storage or S load?
Yeah, right. S load is right. Yeah. But read is about 2,100. And so you can think of if you need to structure a very large computation over some large subset of storage. Let's say you want 1 million events that you're going to store in a mapping. Every time someone does something, instead of emitting an event, you're going to store it in the mapping. Well, you can think of the cost of relatively high, over 1 billion gas or 3 billion gas. And then to read on that, every query you're going to have to do is going to be proportionally high as well. So, I mean, even structuring a very basic query like select all NFTs that you own between block X and X plus K would be infeasible to write in Solidity, especially when the number of blocks you're querying over K is very, very large. And so in our current benchmarks, we can handle queries of about over 1 million storage slots in sub 1 minute over an arbitrary block range. And that, we think is an order of magnitude greater functionality available to dApp developers than what they can do right now in Solidity.
I have an implementation question that might be a little bit nitty gritty. Do you guys walk back in the consensus tree to get the store, you get the
go back and epoch at a time, and
you go back and epoch at a time. You open, and then you
the whole thing unfurls. You can think of the blockchain as a very large unbalanced binary tree, right? All the blocks are connected with RLP encodings and Keccak hashes, and every tree is connected that way too. So if you're structuring a batch proof, you have to structure the batch proof over this very large unbalanced tree. Then a new block is added, and you have to update the underlying batch proof to be verifiable with respect to the most recent block header. So the public input to the proof is just whatever the most recent block header is of the chain, and you can go arbitrarily deep. And when you're recomputing, because we've changed the arity of the structure, you don't have to compute a number of hashes proportionate to length.
Bringing it back, and I guess the last question in terms of the panel, what are the biggest opportunity for improving the benchmarking practices? I know we have different focuses here in terms of optimizing, in terms of doing these things, and I know that there's that look at the market demand, look at the different block the block spaces, as well as essentially what can we do in order to achieve that set standard, other than just following what the market is saying?
Build, baby, build. Build something useful, build something people want to use, and then benchmark it on real world use cases with technology that's in production. That's what you have to do.
I think we need a market, right? I mean, that's like a clear conclusion from this. We need an open, permissionless market where these, the prices for these things are transparent. That's something I guess I could chill. We're building a protocol called Boundless to do exactly that, sort of open up the proof supply chain, if you will, fully decentralized manner. I believe the Sync team's working on something similar, and so that to me is like one of the most important things we need to solve in order to make this not only the benchmarks themselves more transparent, but in order to make this technology feasible and scalable, et cetera.
Yeah, I think too, it's interesting to know there's so much agreement, across the board, because I think that benchmarks are quite splashy. I'm glad that we're moving to an era where it's like focused on real workloads. And I think that, it'll be really interesting to see how the kinds of workloads that we do change. I think, at least to me, it's pretty clear that a lot of the rollup demand, I think, will move into ZK rollups. And once that happens, the next workloads we're benchmarking get much more interesting. Like, with ZK rollups, you have these like large workloads that are done by chains. What happens when your workloads are done by consumers, right? Like, what happens when you have like dozens of millions of incredibly heavy client-side proofs or just like consumer proofs that are happening, and what does it actually look like to optimize for that regime and have like benchmarks that work well for people? Because let's say you're running a protocol that is incurring those costs on consumers, the way you think about your pricing model is very different than you have to think about it with a rollup, right? Like with a rollup, all of the costs are done by the service provider. When you're pushing those costs into the consumers, how do you think about that? And how do you think about, subsidizing that as an application? I think that's gonna be quite cool. And I think at Succinct it's also a big priority for us to make sure that getting this market rate mechanism is incredibly important. Getting it right is important. There are many ways to price things, but some of them are better at accruing value to the end users of, let's say, a prover network. And yeah, to us, it's very clear that that needs to be done critically well and with a lot of thought about making sure that the excess value is pushed to applications and not towards the market.
To interject very quickly, so our team also focused on building prover markets, prover networks, and underlying infrastructure to do decentralized proving. And one thing that was very relevant for us is research into mechanism design and formal proofs around mechanism design for resource allocation and resource markets. And so we have a great paper our team actually just came out with called DARA, or Double Auctions for Resource Allocation, which is, to my knowledge, the first incentive-compatible design for proof assignment in a double-sided marketplace for proof demand. And so I suggest anyone here who's interested in that, definitely go check it out. It's, I think, some really good work. It's submitted to Financial Cryptography this year, and it's exciting.
Awesome, and I think we're on time with this. Thank you all for sharing your thoughts, and glad to see alignment.
Yeah, thank you.
Thank you, everyone.
Thank you.
Thank you for having us.
Okay, that was very insightful. Thank you to our panelists. Any question? Any question for them before they go?
I'm tired of the Fibonacci benchmarks.
Okay, that's amazing. Thank you so much. Really do appreciate it. That was very insightful from our panelists. I mean, they've given us a lot to think about when it comes to creating a benchmark standard for our project. So furthermore, we will just take a short musical break and let that sink in for a moment. Then when we come back, we'll be having another session with Viv and Alicia. Thank you. Okay, that's amazing. Amazing tunes there. I mean, I'm a sucker for good music, and that was a good one. And up next on this particular session, we have Alice again, and this time around, she'll be doing an interview with V Ford, the VP of Community of Elio Foundation. Please, a round of applause for them. If your hands are not too busy, please, let's go, let's go, let's go.
Thank you so much for the introduction, and thank you, Viv, for being here. Super excited to interview you today and talk all about community building in Alio.
Yeah, my pleasure.
Yeah, of course. And I'm wondering if we can first start off with an introduction of yourself. So how you got into the Web3 and also ZK Spaces.
Yes, how I got into Web3. So in 2015, I arrived in San Francisco, and I moved into a house called the Crypto Castle. And it was 14 crypto bros in San Francisco, California, and I was in desperate need of a place to live, and so I just took a room there. And within the first day, one of the guys living in the basement was just like, "You don't know what Bitcoin is?" And I was like, "Nope." And that kind of started the whole trend of learning about crypto. I didn't officially start working in crypto until about 3 years ago when I joined Alio. And it's been, I guess 10 years of a ride.
Oh, nice. So 10 years of first being introduced from that house to now working at Alio, and now you're completely in the space.
Completely in the space,
Nice,
for better,
nice.
for worse.
Nice. I'm also curious to hear about your thoughts for the ZK space, kind of your vision for it. Like we've seen a lot of developments in the past few years, like for example, proof generation costs lowering and some more like improvements, at least on the developer experience side. But besides that, we're still quite some time away from like full mainstream adoption of ZK. So I was wondering about your thoughts on what kinds of challenges, what kinds of limitations still exist before we're able to reach mainstream adoption, and maybe how Alio is trying to help with that.
Yeah, I think, like first and foremost, zero-knowledge proofs are really hard. They're complex. They're difficult to like understand, even from a developer's perspective. I'll start kind of with what Alio what has been trying to do to make it less hard, and then I'll talk more generally about like what would the world look like if it were more accessible. But Alio basically came out with this programming language called Leo to obfuscate the complexity of coding a zero-knowledge proof. And the idea was, yes, you have to learn another programming language, but you don't need to learn the complexity of coding a ZKP, and you can choose privacy and whatever level of privacy you want to have in your application. I think the bottom line is that convenience will always drive success, and zero-knowledge proofs are incredibly inconvenient right now. They're costly, they're slow, and people are working on these solutions. I think one way you can tell how complex something is how much are people talking about it, and people talk about ZKPs a lot. And so I think because they're talking about them so much, it shows just how far we still have to go to actually like integrate these things into life. I think a successful version of a ZKP is like someone uses ChatGPT and has no clue what's going on the back end, and they shouldn't know, or maybe they should if they want to, they can figure it out, but they know if ChatGPT is broken and they know if it works, and they don't need to know anything beyond that. And I think the same is true with zero-knowledge proofs. It'll be probably some time before this thing is so deeply integrated into the internet or applications where someone doesn't even need to know the word zero-knowledge proof and is still able to like appreciate what it can do for them.
Mm-hmm. So not necessary to know exactly like the underlying how it works, but just how to apply it into use cases, into integrations.
Yeah, I mean, ideally you don't even have people know what the word ZKP is. Like my mother wouldn't know. My mother knows what a cookie is for like Google, but only because people have been talking about it a lot in the last 5 years, but actually she might not even. And she's an intelligent woman. And so it's an interesting moment of, we're talking about ZKPs and trying to integrate these things into the world without realizing that actually the goal is to make it so the world doesn't need to know about them, but is still using them. Mm-hmm. Like if you want to better the world, Steve Jobs said it first, don't ask people what they want, build it and give it to them. They will want it.
Yeah, definitely valuing the convenience, ease of adoption there.
Yeah.
Mm-hmm. And just on the topic of like applications and use cases, I'm curious to hear about the use cases that you're personally like most excited about, or ones that are currently being built on Alio that you see a lot of potential in.
Yeah, I think probably like a use case that doesn't really require blockchain, but I think is really interesting is voting. There's, you know, I'm from the US, we just had an election, and everyone is always talking about kind of like the sanctity of a vote, and how do you ensure that a vote is honest, true, and really from that person, and voter ID stuff. So I think ZKPs could do huge for that. And then more kind of maybe more crypto side, a lot of crypto is KYC and making sure that you know who you're dealing with. But ironically, we are KYCing people, though we also believe in privacy. So there's a disconnect there of just kind of like what the world values for privacy, and then compared to like, you know, if the world values privacy, then it would be easy to do KYC. But the world doesn't value privacy. So if you're the only one valuing privacy, your KYC is just going to be open and a mess, and you're going to get a lot of information that you don't want. And so personally, very excited for the potential of zero knowledge proofs expediting, making it easier to run KYC.
Definitely, and I'm also, you also mentioned, like, for example, voting those that are beyond, like, the blockchain ecosystems that can be applied to. So personally, like, for myself, very excited about those real-world use cases as well.
Yep.
And also very curious to hear, since you are VP of Communities, so you focus a lot on the community building aspect. I'm wondering, on your perspective, what are the most important aspects of community building for both, like, the end-user side and the developer community side?
Community is really interesting. I think, what's the #1 company in the world? Apple. And so it's not a bad idea to mimic what Apple does. They definitely have a huge market share for it, but not their products, but just like kind of how they run their company. And never before has there been a company in Web 2 that has had a Discord for their community, where you've been able to like engage directly with the engineers who are building this thing, and where people feel like a part of the team in a way that they have never before. Maybe there's been, you know, like kind of evangelist programs for Google and things to get people excited, but it has never been so blatantly like, hey, open invitation, anyone come join this Discord server, see what's happening. We're an open source project, hopefully, so please learn what we're doing from the ground up. And so I think that's kind of like that understanding of just, this is a new way of interacting with your users is pivotal to building a good community, because essentially you can't pretend that your users are there simply because they want to be there for the goodness of their heart. They are there because they are hoping for something in exchange. And that something can be validation, it can be being seen, it can be a whole variety of stuff, but they are there for something. And I think that's really important. It is a mutually beneficial relationship, and it is, you know, when you build a community, you want to open the doors to everyone to allow to come in, but you want to be very selective of who you actually choose can really be close to the source, close to the code, and close to the project, and like kind of spread the word of the project in a way that feels honest and true to what it really is.
And I really like how you phrased it as mutually beneficial, like a symbiotic relationship between the company, between the users. So like company, they want to build a product that's great for the end user, and the end user also wants to have a product that fits for their needs.
Exactly.
So having that interaction there, and I think it's really great, especially in this space. You mentioned that like never before have we seen a time where you can just directly engage with developers on Discord and not have to fill out like a customer feedback form that they'll may not ever like respond to. So we're definitely seeing like a lot of progression, at least on the interactions between like the project itself and also the end users.
Yep, totally.
And I'm also very curious to hear about any sort of challenges that you've come along in the way when it comes to community building, or if you have any advice to any community builders in the audience who are looking to further develop their communities as part of their own projects.
Probably the biggest challenge is like when something goes wrong internally and your community is waiting for, you know, when you disappoint your community, they will leave. There's probably a short rope for them to stick around, and you can't really blame them to want to leave if something doesn't go the way it should go. So if you are not super organized in your organization, and if you have promised whatever, an NFT, something of the sort, to the community, and then you are delayed, and you are like kind of, if you are delayed in what you are giving your community, they won't stick around forever, and we can't assume they will. Now, the question is always, okay, what does that mean if they don't stick around forever? Are there new people who come in? What's the turnover? And though that's kind of a harsher way of asking, like, how much do individuals matter, you have to ask that when you're building a community. And I think, you know, we have a 500,000 person Discord. 450,000 of those people probably came on twice. And it was probably right around when mainnet was gonna launch and they thought they were gonna get an airdrop, and then they were disappointed. And then not even 50,000, probably 10,000 are genuinely curious about zero-knowledge proofs and that technology, and they came across Aleo and they were like, wow, this is a really cool decentralized private computation. Like, how I can do that on the blockchain, this is incredible. But still, those 10,000 people are also involved in 10 other projects that also claim to do something similar. And so then you narrow it down, and by the end you have maybe 100 or 200 people that are sticking around in there for a reason. And those people you really need to nourish and kind of like thank for being there, because it's a freedom of entry, freedom of exit world, and they're not getting paid. So why are they there? And I think you have to constantly ask yourself that question when you're running community.
Yeah, definitely. So definitely optimizing for that quality over quantity in terms of the terms of the people that you're trying to capture.
Yeah, totally. Like, yeah, absolutely. I say this, and this might be like an extreme kind of thing to say, but it's the same thing as a religion. Like, these people are there because they believe in this thing that you are building, and you know, you want to open it up, and you want everyone, if you have a new religion you're pitching, you want everyone to believe in your religion, of course. But you don't let everyone come and give, I'm not religious, I don't know what they give, whatever talk the priest gives, let's say, the sermon. You don't want anyone coming up and saying a sermon. I mean, that'd be a little bit iffy. So I think it's just an important, like, okay, there's gates for them to pass.
Exactly, and I also wanted to go into some strategies that you've employed, especially when it comes to the long-term engagement in terms of retaining the community that you've built. So I know that you're also leading the ambassador program, which I believe is a points-based program, and ZKVM has also done something similar where we have a points-based program as well, but it was really difficult for us to capture the members who were truly passionate about the project and weren't just there to collect points. So wondering about kind of your strategies for that long-term engagement, long-term retention.
Yeah, the ambassador program, the points-based ambassador program, points hold no inherent value. I've had to say that 50,000 times. That's been interesting. I think it has been, yeah, it's an ever-evolving, growing, breathing platform for people to get involved in. My sole goal with every new introduction of a thing on that ambassador program was to make it so not one person is responsible or centralized to this program. So every time I added an element, I made sure that if that, the person running that element left, it was still running. So for a bit more detail, I basically did tiers, right? What do people love more than anything? Competition, especially when they win. So I tiered it out, made it very clear where it was just like, hey, you are coming in as an ambassador, you're an apprentice, you have an intense application process, we are strict about who we bring on, probably around 100 people each round, and we had around 4 rounds, I think, so not that many. We had about 400 people in our ambassador program, and you will pass the first round, and then you become an apprentice. And we built a bot for Discord called the ambassador bot, where people had to directly upload content. They needed to upload 2 pieces of content. I created a tiered system of apprentice, voyager, and maestro. Don't ask me why I used those words, but I did. And then I did a maestro checker, which was the top. And the maestro checker was responsible for checking the works of all of these 3 categories. And if you wanted to bump up a category, you needed to do more work. You needed to get a certain number of points. And then if you didn't get those points, you would be bumped down. And you would be booted if you didn't continue. And so it was just this points-based system to help to just run it in a completely decentralized manner where I was never checking the works, and I wanted to be sure of that because then people could individually come to me and be like, why didn't I get this many points? And it was a decentralized system of no one knew who was checking their work, but people were checking their works, and they would pass the ranks or go down the ranks. And if they I think the cool thing is that people then met other people who were as involved as they were. If you're in the Maestro category, you're at the top category, so you're gonna meet people that are as excited about Aleo for XYZ reasons and hopefully build something or come up with a cool app.
So it's definitely that kind of tiered system where someone always has something to look forward to, another kind of almost like a level to be upgraded to.
Totally.
Yeah.
I mean, it's everything. there is no difference in any aspect of life. Like, imagine if you were just told that you have to like run a 5K every month, and well, this is not a good analogy. Let me think of another one. I was gonna say you have to only run a 5K, but people wouldn't want to run more anyway, so it doesn't matter. But like, yeah, if you can never level up, why are you gonna do the thing? You know, if you go to the gym and they're like, hey, you have to stay at 20 pounds the whole time, you can't get stronger. You're gonna be like, I'm not going to the gym. That's lame. And instead, you're like, yeah, I'll go up to 100 pounds and then I'll continue building. So
Yeah, definitely. So having that kind of system where someone always has something to look forward to, like
Yeah.
a new goal to achieve.
Yeah,
Yeah,
exactly.
definitely. So I think that's great advice for any of our community builders out here who are looking to have that kind of long-term incentivization. So yeah, thank you for that, Viv.
Yeah.
I also wanted to transition a bit into Aleo itself. So I'm wondering if you can give like an overview of what Aleo offers. So there's a network, there's ZPass, there's the cloud as well. So I'm wondering if you can give an overview of those components and maybe how they work like together, how they relate to each other.
Yeah, totally. So Aleo was born out of a paper called Zexy. Sexy, if you will. And it was created by a couple of people back in 2019. They basically wanted to do private decentralized computation. And they, a couple guys from the Zcash team found a huge kind of hole in the market where you had the programmability of Ethereum, but it wasn't private, and then you had the privacy of Zcash, but it wasn't programmable. So what if you had Ethereum and Zcash? What if you had them have a baby? And then that idea was Aleo. And so it was kind of born out of this desire to do these private computations and private applications. And so it was started by this guy, Howard Wu, who now runs Provable, which is the for-profit arm of the Aleo Network Foundation and Provable. And he, the goal was basically, okay, what if we did computations off-chain? And so you could run unlimited runtime off-chain, and you would basically get zero-knowledge proofs that would be then validated on-chain, and that would be the only thing validated on-chain. So like the shadow of an object, like the shadow of a chair, you don't exactly know it's a chair, but you know something is there, and you know it to be true, you just don't have the details. And no blockchain to date was doing this at the time, or has really done these like private computations like we have, in the sense of being able to like build on top of this blockchain and build private applications. And the key thing with the private applications was like, okay, we want to be able to have people choose the level of privacy that they want within an application. And if you want privacy, Ethereum is not private on the base level. So you need to start from the base layer and build privacy into your blockchain. And so, yeah, we basically have, Aleo stands for, oh no, wait, which one is it? I think it's Autonomous Ledger Execution Off-Chain. And so there you go. Fun fact, I don't know if I'm allowed to say this, but I'm gonna say it. I don't think that they actually, I think they came up with that after Aleo. They like named Aleo and then they were like, actually this could work if we did it this way. Fun. So yes, ZPass is one example of an application being built on Aleo, and ZPass is basically our solution to KYC. And so basically, how do you prove someone to be who they are without revealing the contents of who they are? You put it in a zero-knowledge proof, and you verify that. Currently, I don't think you can actually use it yet, but I know it has a website.
Okay,
So,
yeah, nice. Definitely check that out if you're in the audience. Nice. And I was also wanted to talk a bit about your recent mainnet launch. So first, congratulations on that huge milestone.
Thank you so much.
And I was very curious to hear about the evolution going into mainnet, because I know you guys had around like 4 different testing environments, including DevNet. So I'm wondering what kinds of like features and functionalities were prioritized like coming into mainnet, and what you hope to see out of it.
Yeah. The main priority was MVP, minimum viable product. Get this thing shipped and out. And the idea was like, you know, I mean, it's such a fallacy to think that you can build in private and then deploy something perfect. And I think everyone knows that, but no one internalizes it until they're actually in like kind of struck in the face with like, oh, I need to ship this thing. And so we had 3 test nets, and I think 2 of those were incentivized. And then we basically looked and we said, okay, what is the minimum, what is the basic definition of what it would be to launch Aleo? How can we just get that out the door? Once we get that out the door, we can build from there. And we can, we can bring on more validators, and we can bring on, it is now an open and living and breathing network. So other people who have ideas can help contribute to this. And so that was really just the MO of the last, probably from January to August, right before we launched. It was just like, okay, actually let's redefine what a minimum viable product looks like, and get it out there. And amazingly we did, which was great, because now we have a working, living blockchain. And the great thing about that is that your community calms down because people don't think they're going to get an airdrop. So you get rid of about half the people, and what a relief. So sorry to say.
Yeah, and just retain the users who are actually like there to
Yeah,
build.
who are building on it. We have really wonderful grantees who have been with us for years and who, like, thanks to them, have made a robust kind of network of applications. We have Puzzle, we have DMOX, we have Arcane Finance, we have a staking protocol, Pondo XYZ, that was built by DMOX Labs. Like, we really, I think without our grantees, we would be, we wouldn't be where we are for sure. And I think that that's a whole other kind of element of ecosystem and community, but it's definitely like, you realize, a very important push to make sure that these grantees feel like they have somewhere to build. And when it's live, it's better for them. I think. I should check with them, actually. I think so.
I get feedback, yeah.
Yeah.
Yeah, also very curious, because when you previously mentioned that users are able to choose the level of privacy that they have on Aleo. So I'm wondering what the implications are, like between users choosing which information is public versus like which information remains private. So what are the implications there?
Yeah, I mean, it's kind of all up to the user, and that, the bottom line is, like, privacy is not easy to build into your application, and you should, like, building with ZKPs is hard. And so if you care about privacy, then it makes sense for the struggle of actually, coding this up into your application. If that's difficult, that's okay, because you care about privacy. If you don't care about privacy, you shouldn't necessarily build an application then on Aleo. It wouldn't make sense. The default is privacy. But it's really just, certain levels. I mean, it totally depends on the person, right? What information does someone want to share? What information does someone not want to share? A dating app, what information would they want to keep private? What information would they want to verify that they're human? Like, kind of, you can think of the whole spectrum of just hidden information and public information and go from there.
Got it. And I also wanted to discuss with you a little bit about the developer experience as well. So that definitely contributes to the developer experience, and you also previously talked about Leo as well, which also contributes. So I'm wondering if there's any other kinds of tools or approaches that Aleo is taking to really help optimize for that end developer.
Yeah, I'll preach this again, but convenience drives success forever and always. And if we don't have easy, convenient dev tools and dev docs, there's no way that, I mean, the on-ramp to success is so much harder. I think a lot about Ethereum in the early days and how, like, coding in Solidity, how it was kind of messy, but people were just, like, so excited for Ethereum that it didn't matter. They were down to, like, learn this new language. And there were people on whatever Discord version they were using back then that were, like, helping to answer questions for sure, but it was difficult to learn, and yet people had a desire to learn it. And so that's kind of, I think that's actually what you need with most, like, blockchain projects, especially ones that are ZKP focused, because it's just inherently difficult. So we are doing a big revamp of our dev docs to get more devs. We are focusing very heavily on developers and applications. So within the community, we are running code sprints, which are basically month-long competitions to build out an application, an MVP, and then hopefully either pass through our grants program for funding to actually properly build out this project, or maybe it's just a really easy project that you can now launch on chain. And so putting emphasis on people just, like, learning kind of, how to build an application with Aleo, and refocusing most of our energy on that and on hacker houses. And
Yeah, nice. And I really like
workshops.
the builder-focused approach that you take, especially with these programs, and really incentivizing devs to just build and learn on the way, and also collaborate with each other as well.
Yeah, and I realize I sound like I'm saying nothing because everyone says that. So, and I wish I could have something else to say, but there's often truth when everyone says the same thing. Or there's often just not truth at all, and we're all confused. But I think in this one there is truth, and I think obviously everyone has like a desire to find like everyone knows that without devs, you're screwed. And so everyone is just trying to find the way to find the dev to convince them to build on your chain. And who knows what that actually, who knows who ends up winning in that race and what that looks like. But
Yeah, exactly. And it is quite tricky because, devs, as you mentioned, have so many other options, so many other projects they can build on, and of course they're not being paid to do this as well. So you really have to convey the message of why devs should build. on you
dude,
specifically, yeah.
I hope devs feel special because, man, we're all vying for their attention and their energy, and we're doing so much to get them to build. I hope they're out there feeling like $1 million because I would if I were a dev.
Yeah, I agree, definitely.
Yeah.
And I wanted to scope out a little bit and ask you about the vision for the space in general. So how do you see the ZK space evolving in the next maybe 5 to 10 years? And I'm also curious to hear about your thoughts on the ZK endgame. So what does that look like for you?
God, probably what I said at the beginning, like the ZK end game is that I don't have to hear about ZKPs, and that they're just integrated into the things that I'm using, and they are giving an element of privacy that is, that is I don't want to say desired by people. I don't even know how much, we care about privacy, maybe not, but we are a very small subsect of the larger population, and if you ask most people, do you care about privacy, their answer tends to be no. So I think the real question is, will technology follow culture with privacy, or will culture follow technology with privacy? And how are you gonna get people to care about it? How are you gonna get people to to actually acknowledge that maybe this is an important thing? If people do care about it, then I think it would be, the end game is that your data is private, and it's not assumed that it's just going to be shared and open. I mean, the amount of sharing of data is insane. On the other hand, it's now the baseline. So can you change that baseline, or do you have to build from now to the future and hope that people now care about privacy? And I'm not sure, but for me, the beautiful thing about ZKPs will be when you don't have to hear about them anymore, and they're just so integrated into this technology, into the internet. This technology means nothing, but the internet, or whatever you want to say. Voting, that'd be great, and it can just guarantee a level of security. Probably security is actually a better word than privacy.
Yeah, definitely. And applying that vision, I'm curious to hear how Aleo is approaching it. So what's the long-term vision for Aleo, or any kinds of developments that you're hoping to see in the future? How do you see it evolving in the next few years?
Yeah, I mean, the long-term vision for Aleo is to I'm gonna say change. I'm gonna say build a better internet, and I know how that sounds. It sounds like it doesn't mean anything, but what it means is just build an internet that actually works for the people. I love Reddit. I think Reddit is an amazing website. I think the IQ of someone answering a question on Reddit is high. I trust those people with much of my life. And I love Reddit because it's an open platform, and I can understand what's happening, and I know that it's most of the time an individual answering these questions, and I just have information about the website that I don't have on most websites. And I think that there's there's kind of a huge opportunity for Aleo to kind of give people trust again in the applications they use and in the internet. Trust is gone. So how do you rebuild trust? I mean, people don't care about trust anymore. And probably some people would say it doesn't matter. I'm making my bets, and I think it does matter. And so the goal is just to rebuild trust on the internet and in applications. And if Aleo can be as simple as, if it can be so easy for someone to just code up an application with privacy on Aleo, that would be the dream.
Yeah, I really love how you touched on that long-term vision for rebuilding trust. especially within, like, as we're becoming increasingly digital, that's something that I think we all need to prioritize on.
Totally.
Yeah. Thank you so much, Viv. Really
Yeah.
enjoyed hearing about your thoughts on the space and then also your vision behind it as well and some community building strategies. So hopefully this is really helpful for those who want to have some advice on how they can have longer term engagement with their community. But thank you so much, Viv,
Totally.
again.
Thank you so
Yeah, appreciate it.
Comedy tomorrow at 7 p.m. I have a solo comedy show about how I moved into. It's a true story. Find me. I have the Luma link. You won't want to miss it. It's a quick 45 minutes of just me talking and hopefully making you laugh. Great. Thank you so much.
Oh, sorry?
We might likely need you again.
Oh, again? For.
Find the moderator for the next panel session.
Oh, yeah, I'm so sorry, but I think I have 2 interviews in the podcast room, so I'm a bit busy. Yeah, but there may be some. I'm not sure if Kyle from our team is still here.
We're currently looking for like Sebastian. He's supposed to be.
Yeah, I see. Yeah, unfortunately, I do have an interview at that time, so I won't be able to make it. But yeah, I really hope you're able to sort it out.
We're just trying to figure it out one way or the other.
I'm the moderator.
Oh, you're the moderator. So that was really an interesting session, and we loved it. If you actually like that session, can I hear you clap a little bit? Just all right, amazing. They did a good job. Alice did a good job. Vive, it's an honor. It's an honor. Okay, so we would get to the next one. We have a panel session. Will ZK be bigger than blockchain? And we'll have a lot of amazing people on that particular panel session. And first, I'll call the moderator of that panel session, Sebastian. Can you just walk up to me a little bit? How are you doing today?
Very well. Thank you for having me.
Please.
Yeah, I think my mic is off.
Okay, so you said you're doing good today, right?
Yeah.
Are you looking forward to the panel session?
Yeah. Honestly, I already knew most of the projects that are talking today. And I went through the documentation as well, and I saw that they have very different views and uses of zero knowledge. So I think it's going to be very interesting.
Okay, really looking forward to that. What's your view though? Like your perception now? I'm just asking, as a neutral person that is going to be, moderating the panel. What's your view on the conversation?
I'm not 100% neutral. I mean, our project has like 7 or 8 different uses of CK, so I have a very well-formed opinion. I think CK was known in the beginning by privacy. Then the utility came for its scalability now, and I think now it's time for privacy again, right? So I think how people perceive zero knowledge or the utility they perceive is changing over time.
Okay, amazing though. So while we're waiting, I would just say, take your seat, and let me get to call every other person on the panel session. Please, can we have? Okay, I'm trying not to kill the name though, man. We have Slive, right? Sylv. Okay, I'm sorry. Pardon me. Sylv. Can we have Sylv in the building?
Sup.
Okay. Can we also have Neil? All right, thank you. Can we also have Ayosh? I got that right? Perfect. All right, so we can also have Ming in the building. Okay, you? Oh, amazing. Thank you so much. You can take it on from here, Sebastian.
Okay, thank you.
Oh, wow, you prepared and you have questions. We're cooked.
Yeah. There's gonna scoring at the end.
I was just coming here to wing it. Not how to think.
I just heard the previous panelist saying that people love competition, especially if they win, right? First of all, I went through all your docs, right? And all your projects, and everything looked very interesting, but I also realized that you have different visions of how to use CK or everything is related to scalability, right? I don't want to
to deviate from that. But then your approaches are very different, right? So I like to start, let's start with a context question, which is something that will help people to understand the role of ZK in real uses or real industries. And the first question has to do on how ZK, the question is very long, right? It's uniquely positioned to impact industries, but the short question is, where do you think ZK may have the biggest impact in terms of industries, use cases? And if you can attach that to real world cases, that would be much better, right? So what is going to be the first killer app in the real world of ZK? We can start with Ming, and then we can go here.
Sure. Yeah, hi everyone, I'm Neil. I'm the founder of Radio. We are doing a parallel ZK EVM. When you talk about the impact of the ZK, from my perspective, we has been doing ZK for the past 3 years. I met Sylvia for many years ago when we were at Stackware ecosystem. And along the way, we are listening to developers. They really need an EVM. That's where we build these high-performance parallel EVM powered by ZK. But that's, to a lot of audiences, already a traditional use case. I talked to a lot of our customers and builders. Really interested to see what they are building. There are many. Maybe I just take one example just to explain. One of the customers called ISO Network. So they has been doing autonomous AI. So when it means autonomous, basically everything, when the large language model was running on the blockchain or off-chain, the off-chain logic will be verified through ZK. So that's something interesting to me, because a lot of customers like them has been doing the similar things to make sure the computation integrity is there. Look at all the OP ecosystems, right? Not so many people really care about that. But differently for all the ZK ecosystem, we see they really believe the computation integrity and build on top with so many different applications. To me, that's very exciting. Yeah.
Thank you. Sil, do you want to add anything?
Yeah, sorry, I was focusing. So I'm Sil, I'm the co-founder of Highly. We're a lean blockchain for probable applications. The one thing that I think is really interesting about ZK is that we first used it for privacy reasons. Zcash, for example, to hide things. You want to hide your transaction. Second, and that's mostly the paradigm that we're in, we're using ZK for scalability, make blockchains go fast, and that's where most of the funding is going right now. What I'm really interested in is using ZK for what I call flexibility. If I have to give you an example, one of my favorite ZK applications is, after ZKML, obviously, it's proof of passport or ZK passport. It is currently the best option that you have to prove that you are of a certain age or of a certain nationality. So DEF CON, for instance, did this. If you come, if I remember correctly, from Southeast Asia, and you're able to produce a zero-knowledge proof of it, you get a discount. In any other setting, without ZK, you would need full-on KYC. And that means that it is more cumbersome, more expensive, and not as private. So it's the flexibility aspect of it that I really, really love. And that's the kind of project that we really want to support on Highly, which is designing a system that solely made for these type of applications.
Thank you.
Sweet. Yeah, I'm Yush from ZK Email. Yeah, I also like thinking about applications from like ZK as proof of, like ZK being most interesting from proof of signatures. We've seen that from blockchain, you can prove blockchain consensus or blockchain transactions because those are, ECDSA signatures often, or in the case of Ethereum consensus, you have some BLS signatures too, but you can do general signatures elsewhere, and that's what I'm really excited about. So, I mean, I think a lot about signatures in emails, but also signatures in passports, signatures on websites, signatures in documents all over the place. So I think, yeah, I think if you can have a ZK proof of signature, then you can bring that thing on chain and interoperate with it with either money if you use the chain, or any other ZK proof of signature if you don't want to use a chain, which is cool. You can get privacy, you get selective disclosure.
Yeah, hi, yeah. I'm Ming, so you met me earlier, so I'm the co-founder of ZKM. Also, welcome you to our event, ZK Hub. So when I see like all the possible use cases, I like to think that similar to what we had done this before in both Web 2 and Web 3, is that every new innovation technology will probably enable you to be able to do something that we can't even imagine, like sitting here, right? So of course the first stage would be we try to do everything again, right? That's happened many times. In Web 3, it's more so because we can actually do many things that existed before, but were not satisfied. For example, the other day I was in San Francisco like 2 weeks ago. I heard someone saying, I'm gonna do ZK Binance, right? That sounds kind of strange because Binance is the biggest exchange. So why do that? Because it's a centralized DEX, right? It's a SEX, well, SEX. And with ZK, you can actually turn that into something decentralized while keep all the operation intact, right? So this is very exciting. And ZKM is project on ZKVM, we call ZK MIPS. This is the very exciting, I call it third generation of ZK technology. It's like in the beginning we have like circuit boards, right? And then we have CPU, right? That's the new thing. And the CPU enabled a general programmability, and that kind of created all the apps afterwards. It makes programming development much easier, more accessible, instead of like big corps that they can manufacture those like circuit boards. So same here, like ZKP is quite difficult, not because it's expensive, it's because it's expensive to develop, right? You need all that knowledge, and it's still case by case. But with the power of ZKVM, you can have that kind of generalized ability that enable all kinds of new apps that's not possible before. So that's what I got very excited. Pardon me, because I can't, like my colleague, peers here that give you a concrete example, but I'm sure the new killer app is the one that we don't yet know today, but it will definitely appear because that's always the case.
Thank you. So summarizing, I have two answers that goes for verifiability of computation, and I have two answers that go for verifiability of data, right? It's quite interesting. But these concepts, the verifiability of computation and data, are not exclusive to blockchain, right? Especially the first example, and I like all answers, but I felt really close to the first two. Obviously, for obvious reasons, for the proof of age, right? It's quite interesting. We are now in the middle of a tender with the European Union, and they basically allocated 5% of the total budget to CK. So they say, do the solution, and then optionally, 5% to add CK on top of it, like sprinklers of CK, right? So I think the understanding of our institutions still in CK is still something to work on. But the first case about AI and CK ML and proving models, I think it's very interesting. And also shows that CK is bigger or wider than blockchain. So the next question is, how dependent do you think the success of CK is from the success of blockchain? How do you think the adoption of CK is going to move faster, or will reach wider audiences than the blockchain? And if so, it doesn't matter what is your question, but the second question is, why is CK so strong in blockchain and not so much outside?
I think that where we're going is not going to matter anymore. I like Ayush's idea of it's like an extension of signatures, and basically like blockchains are made out of signatures. And if we now have a better paradigm that just expands upon signatures, we're going to bake it in. So right now we're in a fun situation where blockchains are 16 years old, and there's a 10-year-old forum posed by Satoshi Nakamoto they said, there's this weird area of math called zero-knowledge proofs. If that thing worked, it would be really cool to have it in Bitcoin. But hey, it's just a paper at this point, so we can't have it. And so now we're trying to cram ZK into blockchain. And it's really funny when you look about it, because if you look at the EVM, it's like it was purposefully designed to be ZK friendly. The hashes are very difficult to compute. And so it creates a weird situation where a lot of basically all the ZK research right now is funneled into like blockchain scalability. And the constraints that you have specifically on Ethereum is the 300K gas cost for a proof verification, which means that you need to use a proof system called ROS16, which is the most widely used system. But you have many other systems that you could use, but the design space, even like the field limits of the field elements are even constrained by that. So I think that where we're going to design blockchains around the affordance of ZK. And that's what we're doing at Highly.
Whoever wants to take the next?
Yeah, I can take next. I think any technology takes time for people to understand, right? So when I was working for a company called Twilio, there's a lot of telecom engineers. They need to understand all the telecom protocols in order to program, to connect to SMS and VoIP, right? But with the Twilio, with Twilio's API, you are able to connect within 5 minutes. Now the developer don't need to understand that anymore, right? I teach blockchain scalability at the Nanyang Technology University. 2 courses are focusing on ZK, but after 2 courses, the students are still don't understand how to code on ZK, which is normal, right? But with companies like ZKM and many other infra companies coming up, making the technology easier to adopt, at the same time, the underlying doing all the research work, I think for the students or the developers, they just need to understand this is the secure technology they need to go to if they are looking for such kind of solutions. And the companies like ZKM, right, can abstract all the complexities and the needs, and developer just to do the interconnection. And that's what we are using some of the companies like ZKM now. I think it will move there very soon.
Yeah, I feel like blockchains are just one step in the evolution of cryptographic infrastructure. There was asymmetric key cryptography, and then there was end-to-end encryption, and then there was blockchains, and then there was ZK, and then now there's more FHE, and soon there'll be witness encryption. And I just feel like blockchains have just gotten a lot of attention because there's a lot of money in them, but I don't think they're any more powerful than anything else. They're just a layer where you can plug it into something else. And so I think it's kind of people think a lot about it, and there's all this kind of companies and economic value being created, but it's kind of it's very simple. It just lets you execute things in a distributed way. I think it's only interesting, in my opinion, when combined with other interesting cryptographic techniques. And so far we've explored very little. A distributed Turing machine can only do so much. And we've seen all of the classic things people were excited about kind of die out a little bit. So I think as people realize, blockchains are not interesting in and of themselves, but as settlement layers for ZK proofs, for everyone to have universal truth, or as ways to connect money to other more interesting cryptography, I think that people will realize, blockchains aren't useful as an ends, but as a means to get something else done. And I think that's kind of how I see this evolving.
Yeah, okay. I like to share 2 of my recent thought about. First is the engineering part of this, and another one is another take on blockchain. So the engineering part is for any technology to be widely accepted. First, you need to get through developers, because you need developers to use that technology to develop apps for the general public to use, right? So there's absolutely no way that you can ask end user anything. The end user should be just totally ignorant of any technology they're using. They just need to use it to their satisfaction, right? So that's the first goal pole that you have to achieve. But in order to reach that goal pole, you need to satisfy the developers. And for developers, it's kind of similar that you can't require them to know a lot of the internal domain knowledge of the underneath technology. I like to think that requires something like a protocol or internal technology agnostic. that the developers shouldn't know ZK that much. They should know the general purpose of why they need to use it and what kind of characteristic or features they can develop it with, but they don't need to know all the, all the inner workings of, for example, algebraic circuits and, polynomials, all that, right? For example, it's like in communication, they use APIs to write networking, app, code or app, but they don't need to, sort of kind of argue with all the details of handshakes and TCP/IP, the inner workings, everything. So I think it's the same, but we're getting there. We're getting there by developing like general purpose like ZKVM, and under the general banner of it's verifiable computing, and not just to ZK. Actually, they should feel free to choose what kind of verifiable computing that suits them, right? So original blockchain is also a kind of verifiable computing, but it's very limited that you can only generate consensus or verify very limited, like you said, like a truth. But with ZK, you have like unlimited power. Of course, you pay the price of it's more expensive. Maybe it's need more time to reach a maturity that is fast and cheap. But I think, yeah, that's where we're going. In terms of blockchain, I like to think blockchain as a, recently I'm dwelling on this thought that blockchains are like universe, right? Like each blockchain is its own universe, but they're kind of siloed. So we humans, we see many blockchains, but the blockchains themselves, like they only know themselves, right? In Bitcoin only knows Bitcoin. It doesn't recognize that there exist other blockchains, and the same for each blockchain. Well, humans actually sit above them, so we're kind of seeing them as a multiverse, like we're above time and space. And what does that mean? That means like we can see a lot of different consensus, and these kind of have a great impact on what kind of future blockchain is, which is not limited to financial apps, right? With AI, we have all kinds of data. So I think blockchain is suitable for reaching a kind of like different point of view of data, with different like consensus, which requires a big like a zoo of different blockchains and universes. And ZK is a great intermedium to act as the interoperability layer. So you can kind of generally prove facts or carry over truths across all different point of view, different data set, different consensus securely. Because right now, like the bridging interoperability is kind of like a just like a duct tape or glue. It's not secure at all because it doesn't really touch any of the universes or blockchains that it connects to. But with zero knowledge proof, you can achieve something like a native level security between all blockchains. So that's something got me excited, and thinking that's the future that we can reach to a much broader application space other than just payments like the original Bitcoin is great, but yeah, there's just why like Bitcoin still occupies the the TVL, everything over 50%, only growing. That's because it's disappointing that the whole blockchain space, crypto space, it's still about something related to payment. Even that is not completely solved. But with zero knowledge proof, we can kind of go much more beyond that. Yeah, and finally, I think that is the future, and that is why I think ZK itself is going to be much bigger than blockchain. Yeah.
Okay, thank you. I'm going to touch on it's not a completely different point, because everything you have said has to do with the verifiability, the trust or transference of trust. Either you trust that I have something, or either you trust that I have execute something, right? And in most cases, trust equals to accountability. Trust equals to legal implications. So trust can only be turned into actionable real-world things when the regulatory environment supports that, right? So now moving more to the real world and to the real applications of all these concepts. Myself, in our project in Privado, we see this every day, right? I mentioned it before, but it's not the first time we see a lack of understanding from institutions about this, but also a lack of support in regulating about how trustable or how credible something is when it's verifiable cryptographically, right? Also, ZK, I think in many institutions is still not seen as secure or safe enough cryptography, still seen as experimental by many regulators, right? So what is your view on that? What are your experiences on that? And more important, what is the impact that this has on your projects? And what changes or shifts do you think are needed to support the application of ZK to real world cases? In the scope of regulatory changes or acceptance.
I'd like to maybe offer a view on this, and I'd love to have you folks thought on that. It's the end goal here is to establish trust. That's the end goal. You want to be able to trust something, either a piece of computation, a balance on a website, or whatever. So you have the main two ways we've done it is either zero trust or full trust. Full trust is I trust my bank. I trust my bank that they're not mismanaging my fund because I have a legal contract with them, and there's an entire, it's like an L2 built on top of the layer 1 of the law, and not because these laws exist that I'm able to trust what the bank is doing. So that's one, that's fully like trustful. And then you have blockchain, where we decided to remove trust. I think the term either was coined or popularized by blockchain of trustlessness. I do not need to trust anyone. What interests me about what specifically the kind of affordances that we can do with ZK probability, validity proofs, et cetera, is that you open up a spectrum between 0 and 1. And this idea that we were talking about right before of the proof of passport is extending the trust that you have that the government is managing their keys well. It's extending it for the application that you want to build, but you do not need to ask for permission. That's really what I think is the key unlock of like the expansion of cryptographic keys, basically. You get 50 shades of trust in a way, and I like the term like vices and or crimes, and the kinky stuff comes into. What do you think?
Yeah, I think a lot of the tension between the general public and the regulator body and our industry is mostly misunderstanding or misunderstanding of the role of technology. I was fascinated about how people see technology, like in over the last 100 or more years. I remember like reading that just at the turn of the 20th century, that the U.S. Congress, right? They pass the laws that it needs to be handwritten. If it's not handwritten, they don't even trust like printing. So
even the idea of signatures, like it's very skeuomorphic, like you sign things.
If a human writes it, then it's the real law. It's very ceremonial. So I think this is just this relation is perceptive, right? So I think all the techniques are there, right? Like for example, at the border, the control, like it's considered to be, the authorities are so like blunt, right? It's no one feels like they're treated like a human being a lot of time, right? Just it's the most unpleasant interface between a regulated body is at the point of access control, right? So that's you feel the full blunt of authority or that kind of uneasiness. Zero knowledge proof, can make this experience actually much nicer, but the regulated body has to enable laws to allow this technology to be used. It's like that, right? Like, printed is okay, right?
Let me give a couple of examples to make it super down to earth. I usually think this is going to be close to you. right? So right now, using your project, I can generate a credential or a CK attestation on chain on an email that I've received, right? If it's signed by someone, right? So imagine that I receive an email from the government, right? That says that this is my name and my address. Do you envision that at any point in time that will be legally binding? That this CK attestation on chain can be presented to a government body to prove any of these things, because that's the regulatory environment. Another case is proof of execution, right? You mentioned we can prove that an agent has run a certain model and a certain parameters, right? Is that legally binding when we are trying to prove that the bot adheres to the European standards of data protection, for example, right? So this is all these proofs seems to be very technologically sound and good and beneficial, but then when the rubber meets the road, right, how far do you think we are from these things to be accepted in the real world?
Yeah, I think it comes down to a question of like what creates legitimacy, like what do people trust and why do they trust it? And I think the government is kind of a last adopter. Like they will adopt or trust a thing once the rest of the world has already talked about it, touched it, adopted it, whatever. And we saw this in like how they had AI regulation, or how even I would say they're like 5 to 10 years behind in crypto regulation. Like they're not really, you know, proactive on the new things coming out. They're still kind of focused on the like classic scams, which I think is good. But it's kind of, it means that whether these ZK proofs are relevant to the government or not is sort of feels like a question that's like N years out. Like I think the real question to be asking is how do we get people and then, you know, companies and then organizations and then institutions to adopt these or trust these, and what are the things that lead to trust? So for instance, if a ZK proof is locking a lot of money on chain, then it's more likely to be secure, similarly to how hash functions were adopted. Because hash functions were used so ubiquitously, they were like, okay, because this thing secures all the communication, probably there's no hash collisions. And I think this is kind of how people determine legitimacy. They're like, oh, are there people using it? Does it secure a lot of money? Does it seem secure? Are there bug bounties? Things like that. And I think that the government trusting it or accepting it will come way downstream of that. And even before governments, there's other bodies that I would argue matter more, like maybe a standards body saying this is important or this is necessary, we should have selective disclosure or whatever, is more important to the world adopting it than a government saying we should have it. But also I think new governments can be very progressive on these things. The US government is probably the last government to do anything, but EU governments are very proactive on regulation. And I think if you present to EU legislators, hey, you can force people to do selective disclosure. You don't have to have them keep private data on their servers. And that way, when their server leaks, the whole thing you're trying to protect with GDPR, it won't matter because they're only storing proofs. And I think if people were able to communicate with, say, the EU government that's passing these laws like GDPR about these kind of affordances, I think they would absolutely jump on. They'd be like, oh, great, like what are the things we need to spur the adoption? And you mentioned the 5% thing, like it sounds like they're thinking about it already. So I'm optimistic that as these things are both useful to people and seem intuitive / legitimate to people, adoption will increase naturally.
I think there's this idea of like customs. Like it has to become customary before it goes into law. You look at like the Homestead Act in 1852 in the US, I think. It put into law something that in the US like people were just doing naturally, which is you were the owner of a piece of land if you were living on it for at least 3 years. But people were already doing it, and it was like fully decentralized law. It was customary, and then you put this into law. And I really agree with what you were saying about standards. It's a question of customs. Like, oh, it's better to do it this way. It's cooler.
Yeah, I think I agree with all the other panelists has been said. But just to add on, right, I think there are two faults. One is the government still think about the decentralization is equivalent to anti-government. So that's where, you know, the blockchain has been really difficult to push forward with so many behavioral users on the blockchain still doing something bad. At the same time, blockchain itself for the different infras have a different belief on how the decentralization needs to be built. Like there are so many layer 2s, 95% of the layer 2s are doing OP, right? And I heard a company recently who are helping other company to launch their own layer 2. End up, the other company want to leave from this platform, but somehow they cannot because the company helping doing the layer 2s are actually holding the key of the customer, and they just don't want to give the key. So for blockchain, how can you do like that, right? So these give the industry really a bad thoughts on what these guys are doing, right? I think, so to us, we need to really act and also start to do more education at the same time, really start to adopt the technology to make it really decentralized.
Yeah, not your key, not your roll-up, it seems.
Exactly, right?
Yeah, I agree with Neil that education is of the paramount importance. And I think, I felt like maybe the tide is turning because we can see that the Bitcoin is actually getting into the mainstream, at least in the US. Yeah, we'll see, but
I think
yeah.
and on the education part, how many of your companies is investing in lobbying or educating legislators?
I'm lobbying that we learn ZK ourselves. I'm widely uneducated. We need to invest more.
It's interesting because there is companies like Microsoft or Google, when they want to put a standard on the government, they lobby a lot and they educate institutions a lot. They spend a lot of time making sure that their standards get approved by NIST or other organizations, right? And I think that this is probably an area of improvement for the CK community, right? Especially seeing how little is known about CK in all these organizations. Okay, so next question is about adoption, but I think I'm going to make a mix between that and the last question because we are
spice it up.
We are taking quite a bit of time in each question, but I think I can mix two, right? Questions were about the speed of adoption and the future of CK, right? I would like to turn this question into what I think are areas of use of CK, right? Because I see, as I said in the introduction, right? In the beginning, people were thinking about CK in terms of privacy. I have information that I want to share, so I can prove. But then later, at some point, we realized, oh, we can prove execution as well. And it was then suddenly all about scalability. In blockchain, that has a big impact, given the cost of infrastructure on running things. So I think for some time, we have shifted the CK attention to scalability. Now, I think that's a field that is becoming more and more mature to the point of reaching production readiness. And now, suddenly, not suddenly, but we see a lot of attention again on identity, on privacy, and the new concept that is arising, which is the proving execution not for the sake of scalability, but for the sake of trusting that we are running the right thing, right? And that's especially in the context of AI, right? So these, I would say, let's put three areas, right? Privacy, execution with scalability, and execution for trustability. How you see the adoption speed in each of these areas? What is your bet, right? In terms of if I had to put my money where I would put it, probably I know the answers given your projects, right? But then I'll leave you some time as well to give your opinion on how you see the future of CK in terms of future adoption, development, trends.
I can paint a picture of something that I 100% believe is going to happen, which is if you look at like computers and the internet, there was a word for a time which was digitizing. It was about, oh, we need to bring the data outside of the internet on the internet. And at the same time, you had a fun thing, which is that the internet had to work with the existing infrastructure, mainly landlines, phone lines. It was a second-class citizen. And the thing that happened afterwards is that we created so much more data with the internet and with computers that digitizing doesn't really even make sense anymore. And we even flipped the phone to the point that now you're using like FaceTime more, you use like phones more on the internet that you would use back on the phone lines. And I think it's going to be the same thing for, I'm going to say attested data in general, data on which you can make statements and make truth statements for legitimacy. Right now, we're just, like, there's so few pieces of data on which we can, that are signed, and on which we can build upon. Like emails, we have this. There's the Cursive team has a really cool repo called Stuff with Signatures. And it's depressingly sparse. There's just so few things, it's so sad. So you have emails, passports. We realized in France that there's a standard called 2D Doc, and we just signed a gazillion number of documents like utility bills, identity cards, so that's cool. We can extend this. And what I believe is going to happen is that we're going to start with this, and this is going to be extremely fast. We're going to be able to onboard people. Like the cool thing with ZK Email is that every single person on the planet has a wallet, theoretically. And so imagine a worldwide airdrop. Like in France, like we could, like with 2D Doc thing, we can airdrop 65 million people like that. So it's going to go like extremely fast, quickly. And the second thing that's going to happen is we're going to flip signed data. We're going to create much more data that is perfectly amenable for this, the same way that we had fiber networks, and then we put the phone on it. So I'm willing to bet on that.
Yeah, I actually like Sylvie's point a lot. Like, because you can have these signatures around the world, like the way we currently think about people doing things with blockchains, oh, they got to first get a wallet, and then they got to interact with this thing, and they got to understand why they have to click 15 times to get something done. But this is way cooler, right? Like this, you can say, oh, like, I'm going to automatically make it so that everybody who's a French citizen can access my thing, or everybody who's graduated from the school can access my thing, or everyone who is part of this organization can access my thing on day one. And I think that's like super compelling for adoption. I think the adoption patterns are going to look totally different from what they've looked like in blockchain. It's not going to be like emergent from people and their friends. It's going to be emergent from communities that are like, oh, that's cool, I can build this on top of my community. So I like that a lot.
I mean, we were talking about the fact that Bitcoin is going mainstream. Like, we're not mainstream. We're not mainstream by any margin. Even the smallest, like, top 500 internet company has like 10 times more users than any of the, like, all the Web3 users combined, and 90% of them are bots. And it's just bad. We need to do a lot better than this.
Yeah, I think there's a lot of delusion in the space. Like, people think, oh, I have 10 million users, and I have all this money, and the VCs, like, for some reason, see this as legitimate. It's like, no, you have like 18 users, and they all run Sybil bots.
9 of them are in your company.
Yeah. And I think we could just use a lot more intellectual honesty if we're going to get real adoption. I think stop throwing around numbers like you have 10 million users. Stop throwing around numbers like we have one user with one product that matters. And when I see that, I'm like, okay, like, at least they're honest. And I think that's where we'll actually see real adoption, is when you solve a real problem for one person. Then you go from there. I think that'll be quite cool.
Neil?
Yeah, for, you know, from the future for the key perspective, you know, I used to ask Eli from Stackware. I asked him, like, zero knowledge is supposed to be for privacy in the first place, but why you end up doing scalability? The answer is no one wants to pay for privacy. Scalability actually saves the cost for the people doing on layer one. That's where, you know, everything started, right? And for me, with all the AIs and also the games on-chain, but people declare they are autonomous, but you know, if they put all the computations on blockchain, it's really heavy. And now maybe ZK has another way to save the cost. So from there, I bet on the computation and trustability due to the cost saving for the people I really use. I mean, at least they are building for that, right? I'm not sure how many users they have. But at least if they really believe that's what they are building and ZK help them to save the cost, I think it's a no-brainer for that to really to be adopted.
Yeah, let me just follow up with Neil's thought that computation is beneath everything. So our society in the world today is running on computers, right? And we have all our data kind of put online. So our digital existence is composed of data, right? It's like we have another us, totally different on chain. Instead of like DNA and cells and proteins, you know, we're comprised of all kinds of data. And right now, the old economy and regimes of society is arranged with very static set of rules, and those are kind of forced onto all the data that we generated. And for example, blockchain is about like assets and money, and that is actually forced upon everyone, right? And with AI, we also have this thing to align our values with data, through data, but everyone's just talking one kind of AI, one kind of alignment, right? Google and Meta, they have their own alignment requirement, and government might have another one. But I like to say, like each one, like all, we're all humans, but all our DNA are different. So naturally, our data is actually very different. We can see them as like point of view data, and for data to be different and have each individuality kind of manifested in their online presence needs a lot of computation. Computation is the foundation to make data live, to make data different, to represent all kinds of point of view. So, and to kind of reach different kind of consensus for that, ZK is a fundamental technology, and computation, verifiable computation represented by the ZK technology, I think will be the glue for the future, the AI dominated and all kinds of point of view of data. And for your ultimate question, I think if one technology is far removed from the user, the much adoption it will have. For example, today we're everyone's using like TikTok, your email, everything. You never really think of TCP/IP. That's because that technology is couple layers, many layers down. So I think that's our model too. We build ZKVM. So this is a very like low level beneath everything. We're even below like EVM, or we're below all the other VMs. So if we can build this, we can build something that can provide the general purpose verifiable computing for every technology that's built on top of it. And I think that's the kind of way for mass adoption to really happen.
Okay. Well, I'll still have some time for questions, but I want to do the close up and then open for questions. First of all, thank you, all of you, for your participation. Again, I really went through all your projects, and they all look very interesting and very promising. Thank you for your points of view. I would like to summarize what I hear in your last question. If I would be in the audience, I would listen to your input. I would think, okay, so in the short term, I would put my money on scalability. On the long term, I would expect ZK to solve for the verifiability and trustfulness of the internet as a whole, right? If that's a good summary, I think we can. Thank you. I think we can close it here, and we have some time for questions. No? No questions? Okay. Well, thank you very much, and hope to see you soon.
Thank you.
Thank you. Thank you.
Okay, that's such an amazing session. That was very insightful. Thank you, Sebastian. Really loved that. Without wasting much of our time, we would get into the next presentation. We have a presentation by Adam. Yeah, so this is one of those people I saw yesterday, and I really, really look up to him. He's doing an amazing stuff, and I can't wait to listen to everything he has to say. So if you're also listening, please, a round of applause for Adam, please. Thank you. All right.
Hello. So does it work? I should aim at the black pillar. Oh yeah, it works. Although it does several clicks at once. Yeah, we'll see how I'm gonna go about it. But first, I want to talk about user experience in private wallets. The talk will be somewhat technical in the sense that I'm not going to be focusing on like a mock-ups of a private wallet frontend, but rather talk about how it looks from the blockchain perspective. What is actually private, and what choices do we actually need to leave to the user. So, like, as an introductory word, I strongly believe that in order to have the actual adoption of blockchain privacy, we cannot expose too many technical details to the user. Like, the private wallet should mimic non-private wallets in the UX. I mean, users are already used to non-private wallets, so any complex technical decision that will be exposed to users will be a big obstacle when it comes to adoption. And I'm going to talk about exactly such obstacles. So first of all, this is what we call Shielder primitive in our team. So this is basically how privacy works. So this is roughly what outside observer can see on the blockchain. So there are some transfers between some actors, like Alice is sending some funds to Edgar, which in turn sends them over to Frank, and so on and so on. And there is this white rectangle. So what lies inside of this white rectangle are also transactions, which are kind of the same as transactions outside of the rectangle, with the difference that we're using a crypto magic to, well, conceal them. So I'm not going to go too much into details. We're on ZK Hub, so I assume everyone has some understanding of how this ZK-based privacy works. What's important for us, for the context of this talk, is how it looks from outside. So that some of the deposits are entering this crypto magic world, some are leaving, and whatever happens inside is obfuscated from the outside observers. And one more thing that you would like to be able to do is interactions with DeFi smart contracts. So perfectly would be if a user of such a private wallet would be able to, for example, use a decentralized exchange or any other type of financial smart contract without ever leaving this land of privacy. So it would look like that. There is this magical private world and Bob residing inside of it. There is some smart contract, and then Bob would like to send some tokens and some additional data, for example, like type of the call that he's doing, and get some other tokens in return. So this can be a decentralized exchange. It can be, for example, liquidity provision. Then Bob would send some tokens and get some LP tokens in return, or any similar type of interaction. So first, there is a problem, because how this kind of privacy systems work is that Bob funds are residing actually in the smart contract, which operates the dark pool. So all the users have their funds in the same smart contract, and hence it's problematic for these DeFi contracts that assign ownership solely on the interacting address. So this is a bit technical bit, but for example, when it comes to lending protocols, when depositing tokens into the lending protocol, the protocol assigns the ownership of this token based on the interacting address. So if we don't want to lose this information, we actually need to use intermediary address between this privacy world and non-privacy world. So we need to send some tokens to intermediary account, and then only from this account, the public account, we can interact with smart contracts. So this are already two operations, and actually it's even a bit worse than that. The problem too is, this is a more ZK-related problem, that the smart contract interaction is usually unpredictable in the sense that at the moment of transaction creation, user does not have the full knowledge of the output. So this, for example, relates to front-running in decentralized exchanges. At the moment we're sending the transaction, we don't know how many tokens we'll get back in return. So that's why we cannot claim them back to this privacy world. Yeah. That's the next slide. So what actually needs to happen is this kind of interaction. From the privacy world to intermediary account, then to smart contract, then to intermediary account back, and only then we can go back to the privacy world, which in turn means that 3 transactions are needed to be done. So from the private world to the intermediary account, then to contract, then to intermediary account back, and then to private world back. So, well, I mean, we're talking about user experience, so that raises a natural question. Does user need to create 3 transactions instead of 1? So, well, yes, but a well-designed wallet should handle this automatically. So, like, in case there are no decisions to be made, and if every interaction pattern would look like that, this is relatively not so bad, because wallet could do it for users. So the wallet should create all the 3 transactions and sign all the 3 transactions, exposing only the fact of doing this single operation to the user. But unfortunately, it's not that simple. So how would that look like when it comes to like the general lifetime of a private account? We could use a single intermediary account on a given chain. Then every time user would like to interact with some smart contract, he would use the same intermediary account that is assigned to this particular user. This is, for example, how it works like now in Aleo. So every time we leave the privacy world to the same intermediary account, do the smart contract interaction, and then come back to the privacy world. So well, what's unfortunate here is that all these interactions can be linked by any outside observer. So this is only illusion of privacy. If we do it like that, all the actions we ever do in DeFi can be linked together and can be linked to a single user. So, well, this is clearly bad. Seemingly better solution is doing it like that. So every time we do some interaction, we spawn a new intermediary account. So then every action is unlinkable to each other, which is great, but there is also, unfortunately, a bad case for this. So in case user wants to do something like that, first interact with smart contract A, then again interact with smart contract A, and do some related action in the second interaction, and then interact with smart contract B, this may pose some problems. So for example, if the first interaction with smart contract A was depositing some funds, and the second interaction, in the second interaction, user was aiming to claim some rewards, this may be not possible. I mean, these rewards can be assigned to intermediary account A. So the wallet needs to somehow predict that. Wallet needs to predict what kind of action user is doing, which is very unfortunate because that means that we need to expose some kind of a decision to the user. It seems that the wallet cannot just assume what intermediary account needs to be used because the wallet does not know whether the user will be doing the action which is related to any of the previous actions or the action which is unrelated and hence should be unlinkable. So how it actually looks like, so it should be like that, where we are using the same intermediary account for 2 interactions with smart contract A and another intermediary account for interaction with smart contract B. And of course, like this is only in the scenario where 2 interactions with smart contract A are related. It could very much happen so that the user wanted to make 2 interactions with smart contract A which are unlinkable. And there is no other way of telling that like other than just asking user for the choice. So how the final flow should actually look like is something like this. So user opens some application. Then this is the question, is it the first time user is opening this particular dApp? This is the question which does not need to be asked to a user. The wallet can just remember that. So if the answer is yes, this is the first time the user is using this particular app, then, well, it's clear that the fresh intermediary address can be created because like there is no previous interaction to which it would be possible to refer to. But if it's not the first time, then we need to expose a choice to the user. So we need to ask the user whether the user would like to create a fresh address and hence enter a fresh interaction without any history, or maybe use one of the old addresses and use some history. So for example, claim the rewards from previous investment or doing similar action. And only after exposing this choice, the user can choose and the interaction can happen. So, well, this is I see this general concept as one of the obstacles when it comes to the user experience of privacy wallets, because like this means that inherently there is some inherent complexity where they cannot offer the same simple experience as regular MetaMask. So thank you for this opportunity of sharing this thought. If there are any questions, I guess I've got like 1 minute. Okay, so thanks again.
All right, thank you so much. Thank you so much. I really do appreciate that presentation. So we'll just get right on into the next one. Amazing. I think everybody's out already. So Xavier will be taking us on a project workshop on ZKP. So Xavier, you have the floor.
hello, hello, but okay. Hello, we will start later, but we will start. On this, it's supposed to be a workshop, but we have only a slot of 30 minutes, so it's not enough to do the workshop, but we will show you how we generate or how we are generating ZK proofs now. Using PIL2, continuations and aggregation, we have worked on the last month on, on what we call THISC and Proofman. It's our new products. We are Roger Taulet and Chai Pinsak, myself, from Polygon. And I will start to explain some quick and basic concepts about virtual machines and about witness computation and related things. So a virtual machine is a machine that executes a proof, a program, with public inputs and other inputs that can be public or not, and give us a result. But when we are talking about ZK virtual machines, we can get the result, but we want also a proof that the execution has been generated correctly, right? So a ZK virtual machine, the inputs are a program, public inputs, a proving key that we'll explain later on the next slide, and the output will be the result, and also the proof that verifies that the execution has been generated correctly. And we have also a verifier that, given the same public inputs and the verification key and the proof generated by the previous ZK virtual machine, accepts or rejects the proof. Okay. And here there's the workflow. There are specific part, the setup part, that it's run only once. That, given some error descriptions, error means algebraic intermediate representation descriptions, and constraints, and some constant data, and some setups related to the prover, generates a proving key to be able to generate the proof, and a verification key to be able to verify the same proof. Okay? That's basic concept. If we dive in the ZK virtual machine, we see that we have 3 stages, 3 phases. The first one is the execution that gives us the result itself, the result of the execution. Then we have a witness computation that, from the execution generates some inputs. That inputs generates some traces that defines the witness. And then after this, we can, with the witness generated, we can prove it and generate a proof, okay? If we dive in on the witness computation part, this is a schema, is a sketch of the witness computation of the current Polygon ZKVM, where we have a big matrix, a big buffer, where we store all the related data of all the state machines that are computed inside the ZKVM. These are examples: the main data, the main traces, the ROM traces, the memory, the binary, the arith, or all the other Keccak. Okay, so if we use a public input that generates, for example, a lot of access to the memory, we will fill the memory trace, and we will not be able to generate the proof, right? Because the memory is almost full. Then if we generate more memory accesses, we will not be able to generate the memory. So this is a limitation. In the current ZKVM, there is that limitation that we cannot, we have a limitation about how many rows we are generating when we are computing the witness computation. And here is where it comes the concept of bad cops. Bad cops means variable degree of composite proofs, where what we want is to generate as many traces as we need to execute a given input, okay? So in this sketch, you will see that the main execution, the main state machine, generates 2 instances on the left. The left main 0, main 1 generates 2 instances. The ROM needs only 1 instance. The memory needs 2 instances, the binary, and so on. So we are able to generate as many instances of a trace that we need. This is a change because if you see in the previous slide, after the witness computation, we have only a big buffer. That buffer is the input for the proof, and the proof use only that buffer and computes the proof. So in the bad cops, what we are generating is a trace for each state machine, and the proof system or the proof backend has several inputs, and that several inputs generates as many proofs as we need, as many proof as instances on the Windows computations we have generated, okay? And then here appears a new concept of aggregation. Aggregation is a process to take n proofs and generate only a single proof from these n proofs. It's a recursive process that we aggregate like a binary tree, yes? So we take the pi0 with pi1, we generate a new proof, the pi2 with pi3, we generate a new proof. These are also aggregated recursively and so on until we get only a single proof. Okay, so the last months we have been working with the Thisk. Thisk is a new project. That is a virtual machine, is a ZK virtual machine from Polygon. This is the repository, you can check it if you want. This is work in process, is almost functional, but we are still work in process on some state machines, precompiles, and so on. The functional specification for this is that a user can be able to write any deterministic program in Rust at the moment in Rust, and automatically convert this program in a proof, okay? So we have only 15 minutes, so.
Yeah, hello. So the idea is that we will do a quick demo. We will show you, we will take a simple Rust program that does n number of SHAs, and we are gonna generate a proof, and we're gonna explain briefly like all the different pieces that compose ZISC. So let me jump into the code. I'm gonna show you first the repos. You could reproduce what I'm gonna do, although now we have like several steps pre-computed because we have just 15 minutes, so otherwise we would not have time. So great, the screen's showing. So the main, the first and most important repo is ZISC. That's this one I'm showing. But there's 2 more repos that are important. So ZISC is, as Xavi explained, the program that allows us to prove any Rust program. But then we have Pil2Proofman, which is a repository that allows us to generate the proofs. And then we also have Pil2Proofman.js, which allows us to generate the setup that Xavi was explaining before. Right now it's in JavaScript, but we are migrating it to Rust. And that's one of the pieces that's missing. So if we check the docs, the first thing that says there's an installation part in which it shows all the repos that you need to install, all the preliminaries that you need to do. This is already done on this laptop, so then we can jump directly to Quick Start. And the first thing it says, okay, so we're going to run cargo sys SDK new hello world. And now I'm going to do a cargo sys CDK new hello world. So now we've created a dummy program that's basically the SHAs that I was mentioning before. We can jump in. Yeah, well, and the next, I can hold it. And then we simply need to run cargo sys run release. Basically, what this does is it will process. It will convert the Rust, it will break down the Rust program in RISC-V instructions, and then we will convert those to CISC instructions. There's a one-on-one relation, and right now we are we're going through RISC-V, although we're not close to that. Maybe in the future we will explore different alternatives, such as Gradelift. Okay, so now I need to cargo sys build release. Great. So now I'm missing the input, so I'm gonna copy it from another file. So now it's building the crate. Okay, now it's built. Now we're going to run it, and we're going to generate the L file, which contains all the instructions. And also, I think that it prints the SHA and the SHA output, and now the next steps will be the setup, which I'm going to completely skip this part because we don't have time. So I already have this, and I'm going to directly jump to the proof, which is much more interesting.
What we have done now is to convert a Rust program into RISC-V 64 bits, and then to convert these instructions to CISC instructions.
So basically, I'm going to run the proof. And I'm going to explain, and while it's running, I'm going to explain you how everything organized. And so the first thing that's happening is that now it's loading the setup. And here there's 2 parts. There's the setup of all the different state machines that we are using, and then there's all the aggregation part that I'm going to explain while it's running. And then the next part is the program will execute. Basically, we're generating several instances. Here you can see that proof instances. So for this example, there's like 21 mains. There's a lot of binaries, binary extensions that are not the basic operations. There's also we're performing range checks. And at this point, the prover starts working. Basically, the idea is that we have instead of one huge monolithic proof, we break down in small instances, and then we prove each instance separately. And since this will result in like many proofs, right? Because we will have one proof for each instance, but we just need one single proof of the program that we are executing. So what we do is we first generate all these instances, and then we aggregate them together, and we generate one single proof. So the idea is that all the instances run at the same time and share the same challenges. So at each stage, all the instances synchronize because they are connected with each other, right? So they synchronize, and we get one single challenge that is distributed across all the different instances. And also one very important part that was just showing before, it was here, it was saying competing with STD-SAM. Basically, we rely a lot on the lookup protocol. So the way that there's different instances that either assume or prove. So we have in PIL what we call air group values, so that we have different instances that they are proved independently, but then so if 2 instances are related, one instance will prove one thing and the other one will assume the same thing. So at the end, what we're doing is we will check at the end of the proof that what one instance assumed and what the other proved matches. Basically, like to simplify it a lot, we just need to check that the sum of those values is 0. So if we check what's going on, we compute fry. Right now, you can see right now we are doing a fry for each of the instances. But in a future, the idea is that we will have either multi-fry or some of the newer protocols that were explained in last ZK Summit, like Weir. And here what's happening is we're already on the aggregation part. So we will aggregate all those proofs together and in a tree fashion. So each instance has its own air group values that I was mentioning before. They bring some part of the assume or some part of the proof, because you can have multiple instances of the binary, for example. So what we are doing here is, firstly, we are compressing the proof to shrink the size, because we are based a lot in what we did in the ZKVM, that we want our system to be able to aggregate an infinite number of instances. So to do that, what we need to get to get that all the proofs have the same size. So then we have our recursive circuits that can be merged together, and we can add continuously new proofs. So first, it's compressing. I'm going to show you the circuits because I think it's interesting. I think I'm going to jump directly to the final. Basically, there's two main circuits. The first one is the recursive two, like this one. Basically, what this circuit does is it takes two proofs, proof A and proof B, and it generates a new proof that is proof AB, which is it has exactly the same shape and size as proof A and proof B. So you cannot distinguish between them, but it allows us to. So then we will be able to aggregate proof AB with proof C, for example. And the important part of this circuit is that I was saying, so we said that all instances share the same challenge, right? But we need to ensure that. We need to make sure that our proof checks that this is right. So the way we build the global challenges is that we build a tree of all the, for example, for the first stage, we got all the roots of all the instances and we build a tree. And then when we aggregate, here there's this aggregate values null. We basically reconstruct the tree as while we are generating this recursive proof. So we are not only generating a new proof that verifies A and B, but this proof also has as an input, as an output, a new accumulated part of the global challenge. So then the recursive, then we keep doing that, and not only for the global challenges, but for the different air group values. And let me check. So it's finishing with the recursive one. I'm gonna let it run. Yeah. So yeah. In the meantime, I can also show the peel and other stuff, or I can show the final. Because at the end, I think it's interesting that, so we aggregate proofs and then we need, in the final one, the important part is that we need to verify that the global challenges were valid and that the global constraints, which basically are the assumes I was talking before, that there's like different machines that are how to say this, they are assuming or proving some stuff, and we need to make sure that the sum matches, right? Because there were two independent proofs that were supposed to be connected, but we need to check that that connection is done properly. And this is done here at the end, and this is very important because what happens is that we will be able to generate one single proof that verifies all the instances and also make sure that all the instances are properly connected. And so I think that's pretty much it. Yeah, I can show you a peel a bit. Do you want to? Yeah. No, so here, for example, this is the peel we're using CISC, and then we have different state machines that Xavi was was showing at the beginning of the talk, like the ROM, binary table, and all this can be found in here. State machines, there's different state machines, arith, binary. I'm not gonna jump into the pills because they are a bit.
Yeah, this part is basically the arithmetization part that we are using the language, the PIL language. PIL language is a polynomial entities language, where we are defining, in this language, we are defining how the airs are, the airs, the constraints, and the constants. So PIL, we are using right now, currently where you are using PIL2 it's very different than PIL1. You can find the repo in PIL2 compiler is the repo. You can find it. You can find a link inside the THES repository. And from the PIL files, we are defining all this stuff, and then we generate a PIL out file where that is a binary file to store that arithmetization part that we will use to generate the proving key and the verification key to generate the proof. Basically, it's that. If you need something more info, we will be around here because we have only 1 minute. So
now the final proof is being generated, so we can verify it. So at least show that the final proof verifies. And now we run it. And basically, it says that verification. Okay, so basically, we have a proof that could go to Ethereum that program was executed properly. And well, this could and now it's been run on sequential mode, but this could be also run in distributed mode, which would be much faster. Or also there's GPUs that's...
Yeah, we are working on that. Specifically on the distribution part, we have very good results, very good results. I think there is a branch in the ZISC, I can't remember the name of the branch, but we have very good results on the distribution part, and in the next weeks or months, we will merge it on develop. And I think that's it.
Yeah.
Okay, thank you very much.
Okay, thank you so much for that wonderful presentation. Please, a round of applause again for them. Thank you. Thank you, thank you. So I think we're almost on a roll right now, and we'll be getting right into the next one. We have Anonym in the building. A round of applause for Anonym, please. Era? Yeah? A round of applause. All right, let's go.
Hey. Oh, cool. Okay. Hi, I'm Nanak Nahal. I am a co-founder of Holonym. So at Holonym, we make human digital rights real using what we call the human keys. And so let me talk about the human key problem, how it relates to ZK identity and key creation. The issue is that human-friendly data is low entropy. There seems to be an inherent trade-off between how memorable some data is and how secure, like how random it is, right? Because obviously more memorable things are less random. More random things are less memorable. And in ZK identity, this poses a big issue. It poses a big issue in a number of places, but for this we'll focus mostly on ZK identity because nullifiers are still an unsolved problem. How to securely generate a nullifier to fully preserve privacy. Right now there's no fully privacy preserving way of creating nullifiers, and that's one thing we change with Mishi Network. So if you are a ZK identity protocol, you want to generate a nullifier from, say, a name, birthday, address, you have like a few options. You can store the name, birthday, and address in plain text, but that's not like the most privacy preserving. You could store a hash of these, which is okay, but you can easily reverse that hash because like these have low entropy. You can just try a few different, well, more than a few different tries and eventually get it. And then there's another option that's become more popular recently with stuff like ZK Passport, which is to store the last 128 bits of the government signature. This keeps it private towards everybody except for the government, which is great for most use cases, but not not everyone. So, yeah. Okay, cool. Okay, so one solution to this entropy issue that we built to solve some of these problems is the pseudorandom, well, oblivious pseudorandom function. So in a regular pseudorandom function, if you're not familiar, you are taking some input with some key. The input is not necessarily very random, very high entropy, but the key is, and then you're using this to output a high entropy pseudorandom value that can be used as a key. But for this to be useful in privacy preserving use cases, we want oblivious property. So the oblivious pseudorandom function, pardon this kind of weird diagram, is similar. This is the 2-hash Diffie-Hellman oblivious pseudorandom function, where the user will hash their private input, whether it's like password or like name, date of birth, whatever, something that's low entropy. They'll hash it to a point in the elliptic curve. They'll multiply it by a random mask R. And then the server will multiply that by their key. Then the client can unmask that, hash it again to get a final result, and now you have a pseudorandom function where every input to the server is completely masked. The server can never learn any information. There's information theoretic security against the server learning what the client's low entropy input is. And the server can be decentralized with standard threshold cryptography. So you can split the secret via Shamir secret sharing, where you do Lagrange interpolation. And the nice thing is that with this method, each node in the network can act as if they're a single node. Like it's completely asynchronous. They don't need to know there are other nodes in the network to do a single computation, because they're actually just doing like one multiplication. They're doing one elliptic curve point by scalar multiplication, where they're multiplying their secret scalar by the elliptic curve point. So like the client can then just query all these individually, reconstruct as if they, as if it got it from one node with one shared secret using Lagrange interpolation. This still leaves one problem, which is how to find faulty nodes. And then for this, you can use very special purpose, efficient zero-knowledge proofs, discrete log equality proofs, no need for snarks. And this can prove that nodes are, without this, one node might be able to get away with changing the result, and you can't track which node actually changed the result. This gives accountability to the nodes so you can see if somebody changed the result. And it has like super nice properties. So communication with any individual node is O of 1 because it doesn't care how many other nodes there are. And this can be easily parallelized. The more nodes there are, you just send parallel queries to them. So it scales super well. Very quick computation. You just have to do a discrete log equality proof. And there are some cool anti-collusion properties as well. Where, with any threshold network, there's an issue of collusion. But since the math is so like clean and linearly homomorphic, you can actually have this concept of what we're calling a semi-trusted node. This is, it could be a node or even a network itself, operates completely independently of this network. By the way, I don't know if I mentioned this. This is called MISTI network. We've implemented this as an AVS on EigenLayer. I probably should have showed that earlier, but you can run like an independent node where if machine network were to collude, this node can make sure that if you're splitting the node the key between that node and the network, then the network colludes, it's still fine, as long as the node is also not corrupt. And this node can itself be a new network. Because everything is asynchronous, it does not need any communication with the network. So there's some cool emergent collusion resistance properties. Oops, that is these slides were stolen from Louis, who is a cryptographer on our team, who helped implement this. I guess that's the last slide. The actual last slide somehow didn't make it in here. But please do check us out on Mishi.network if you're interested in this oblivious pseudorandom function. Its use cases for ZK identity. It also has use cases for wallets, such as Silk, which is our wallet that's a new paradigm for onboarding to improve security and self-custody. And making sure that once people are onboarded, they can actually have real use cases and more aligned with Web3 cypherpunk values instead of just giving away your stuff to a Google account. And then we also use it for zero-knowledge identity, of course, which is what this talk was about, with our zero-nym protocol. And you can find out about all of our work, all of our protocols on holonym.id. That's HOLONYM.id, or follow us on Twitter, holonym. All right, so any questions? Cool. Thank you.
Okay. Please a round of applause again for him. Thank you. Impressive. Thank you so much for that presentation. Really appreciate it. Okay, so I think we are down to the last, but not the least, presentation for today. We have Jerome. I hope I'm Jerome. Okay, okay. Van der Graaf. That's a beautiful name. Where are you from, sir? Where are you from, sir?
Where I'm from? Yeah. I'm
okay, your microphone.
Well, I live in Brazil, but I'm from Holland, from Amsterdam.
Amazing, amazing. I love your name. It's such an impressive name.
Thank you.
You're welcome. Okay, so, sir, the floor is yours, to do your presentation. Thank you so much. All right.
Do my best. This is working. Well, it's not showing. Ah, okay. Now I'm okay. Good afternoon. I'm a little bit lost. I just came in from the plane. Anyway, I want to talk to you this afternoon about extensions and refinements of ZK rollups. So I give a short outline of this talk. I'm going to leverage the ZK VM to implement cross-chain asset transfer. And leverage is in italics because it's a very popular word in the ecosystems. Anyway, I want to explain to you about entangled rollup. I'm going to talk a lot about what it is. And also explain about the extension that we recently developed. And the second part, it's going to be shorter. I'm going to show some sophistication, some sophisticated applications of ZK proofs. I'm not going to list the improvements here because it's going to distract you, but at the very end of the presentation, you will see. So we all know that each main chain is an island. It's like a separate entity, unaware of the outside world or the existence of other chains. And often we would like to be able to communicate between these chains, and in particular, we would like to do asset transfer. So here you see like these two isolated chains. And what do? The current solution is, well, we build a bridge. A bridge is a separate intermediate entity trusted with holding assets during some period of the transaction. And this is not desirable because it provides an opportunity for attack. It could be that maybe the bridge goes bankrupt while your assets are there, or maybe it gets hacked while your assets are there. So this is the solution showing the bridge. Now I'm going to explain to you the main idea of an entangled rollup. And the basic idea is the following, that using existing primitives and using existing underlying trust assumptions of a ZK rollup, we can implement cross-chain asset transfer. So it's like bridging, but without the need of a bridge. And again, without adding additional trust assumption or additional entities. So just to remind you, this is an outline of a ZK rollup. We have the user, which is represented by a wallet. We have the node, the sequencer, and in particular, we have on the right, we have the ZK VM. And this is essentially what we're going to take advantage of. The fact that we have a ZK rollup implies, of course, that we have a ZK VM. And the idea is that we are going to use the ZK VM for more powerful objectives. I'm skipping a bit here. I gave a more detailed presentation on this part, but I'm not going to go into much of the details, also given the limited amount of time. But the idea is the following, that in this case, you can see how a ZK proof is being used as a proof of transaction. On the slide, it's called a validity proof, not a ZK proof, but these two terms are equivalent. So what happens is that we have the transaction, we have the client sends 10,000 units to some rollup account. You have to wait for settlement, but once it's settled, you have a proof of transaction. And this proof of transaction has to go in the form of a ZK proof, because layer 1 doesn't blindly trust what happens on L2. So there has to be a ZK proof. This is exactly what the ZK rollup is used for. And then with this proof, you go to L1, and we can see that the rollup account on L1 will now authorize transferring 10,000 units to the client account on L1. So this is what we have, what we gain from the ZK rollup. And what we are going to do, we're going to use the same trick, but instead of between L2 and L1, we're going to do it from chain A to chain B. So this is the way, it's very similar. So step 4 is the proof of transaction. And intuitively, you must realize this is like a certified check. This is the whole idea of the ZK proof. The ZK proof will act as a certified check. So a certified check, it's like you show it and you can cash the money right away. So this is the idea of our scheme, and this is what we call the entangled rollup. How do you prove that the settlement on chain A actually happens? There are two different approaches. One is that you go back in time. You go back to the Genesis block, and you show that the current transaction, the transaction in which to validate goes way back all the way to the Genesis block. So this is by itself has some strong guarantee. Nevertheless, it doesn't show that no rollback has taken place. So this is why we actually are in favor of the next approach, which is you go forward and you wait. So what's the idea here? The transaction is included in block M, but now we're going to wait N blocks where N is sufficiently large to guarantee that no rollback has taken place. And then when there's N, when you have weighted N blocks, then you create a zero knowledge proof that shows that the transaction has been included in block M, that the hash of M was computed correctly, and also that the hash of M plus N was computed correctly. And so this altogether constitutes a proof. Well, this requires some thinking, and this is sort of specific to the blockchain, to the Bitcoin blockchain. But the idea is that if it were possible to create this proof but a fraudulent proof, this would be equivalent to forking in Bitcoin, which is supposed to be impossible. So this is the security guarantee. So instead of having two separate ecosystems, what we engage now is we are getting two entangled ecosystems. So this is part of the reason for calling this the entangled rollup. Now there is this thing which is called liquidity fragmentation, which is the following: if you have if you want to do asset transfer from chain A to chain B on layer 1, then when the transaction is okay and you are at chain B, then it's necessary that this rollup account does have these reserves. It's like when you go to the airport and you want to buy currency, I don't know, British pound, then the exchange where you buy it must have the amount available, otherwise it simply won't be able to work. So we have this problem, which is called liquidity fragmentation. And there are some instances in which we can solve this using the entangled rollup. Suppose we have, there's this case I read about DAI. DAI is represented on several L2s. And what happens is that the smart contract on layer 2 of blockchain A just needs to destroy 10,000, or this should be DAI, and this also should be DAI, while the smart contract on B2 needs to create 10,000 DAI. And why is this possible now? Well, because the coinage the currency is virtual. The entity that controls the currency can simply perform this transaction. It's just a bookkeeping trick. There is no real need to keep to have backing of the DAI. So this is a very powerful concept, which we call liquidity optimization. And this is one of the main use cases that we are trying to exploit. Also in a separate project, the Code project, we are trying to combine the Ethereum L2 and the other L2s together with Bitcoin. Okay, so this is the liquidity optimization. Yeah, so this is kind of conceptual image of this. Now, there is an extension of the entangled rollup that we only thought of like 1 or 2 months ago, which is the following. You can have this rollup, but instead of copying all the data only to one L1, you could copy this data to several L1s. Now, this does have a problem in the sense that you are stuck with the time it takes to settle transactions on all these different layers. So this is something that needs to be taken into account. Even worse, imagine that on one of the layers a rollback takes place. What exactly are you going to do? So we are still studying this topic. But you can even take this idea further. Instead of having one roll-up, you could have parallel roll-ups. I don't know, I call them here A2, B2, and C2 as if they are strictly related to the L1s. That's not even necessary. I mean, if you have a roll-up already, it's very easy to add an additional field to say which coin it is that you are representing. So the same roll-up technology could include various coins, various currencies in parallel. So this is a new idea, the extension of the entangled roll-up. So I think what I like about it is that the overhead is very small. You have one ZK verifier. You need a ZK verifier on all the different L1s. It's a very simple model. We do have a problem though with a ZK VM on Bitcoin, right? Because the Bitcoin scripting language is not sufficiently powerful. So this is why we have this separate project based on the BitVM ideas to have a more optimistic way to deal with transaction sending to Bitcoin. Now I'm going to briefly, I have a couple of minutes left, talk about the improvements. So one first improvement on rollups that we envision is to process simple transactions separately. So what's the idea? Well, the idea is that many transactions are asset transfers from account A to account B. There is no smart contract call. We built a ZKVM to be able to deal with complicated smart contracts. But it turns out that in many cases there is no complicated smart contract. It's a very simple transaction from account A to account B. So that means that maybe, well, not maybe, the correctness verification is very easy. We could use maybe a very small set of the ZKVM instructions. We could build a specific snark. Maybe we can build a very specific protocol for it. We are still looking into this. But the upshot is that we have two queues. We get a fast queue and a slow queue. So the fast queue only takes simple transactions. And so they don't get held up by complicated transactions which are in the slow queue. Right? We know that prover time at the moment takes a couple of hours, maybe 3, 4, 5 hours. And maybe by doing the separation, we can get the simple transaction processing time down to, I don't know, 20 minutes or maybe 3 minutes. So that was certainly worth looking into. There is some hopeful statistics that we have. This is very preliminary, but a student of mine did some investigation both on Bitcoin transaction and on the Metis transactions. And this set is 38.5%, so that's 40%, I would say. Seems like a good guess. They don't call a smart contract. And this is just based on simple fields that are included in a transaction. It doesn't even include ERC20 transactions, which I believe many of them are also very simple. There's a lot of USDC, USDT, Uniswap transactions that are simple. So I do expect this percentage to go up significantly. So the second improvement would be to do zero. You know, the roll-up has a proof on the whole transaction. Instead of doing it for the whole transaction, we could do it for one specific transaction only. This may be interesting. Of course, the transaction that must be independent of others, and maybe the solution is to put them in the beginning of the batch. And then you have to show that these transactions are correct and the batch has been finalized. I believe this can be interesting. We could do this, I don't know, for a high value transactions, or clients may want this specific treatment. And the third improvement we're looking into is to show that asset invariance is maintained in a transaction or in a roll-up. What does that mean? Well, it means that assets do not appear from nowhere, they don't disappear. But it's like you can see in the background, there's this bookkeeping sheet. It's like you want to have solid bookkeeping. But of course you don't have to do that for all the accounts. That's unnecessary, because all the accounts that are not involved in the transaction or transaction batch, they will remain the same. So we only need to sum over all the accounts that are involved in a transaction. And so the hope is that this will be much simpler than proving that the whole smart contract is correct. But of course, that's also the drawback. It doesn't prove that the smart contract has been executed correctly. So there's two sides. Why do I think this can be interesting? Well, all these improvements, they give us a way to refine, to get a range of services or products that we can offer to our clients. We already have the hybrid roll-up, which is the optimistic roll-up and the ZK roll-up. We now can have a fast queue and a slow queue for simple and difficult transactions. You could imagine that you have an optimistic roll-up, but that some clients or for high values, we do a zero knowledge proof in this specific case. Or we can also imagine that we have an optimistic roll-up, but we do the zero knowledge proof for asset invariance. That at least gives a better trust of what has been going on. So this is it. Just wrapping up, I think there's been a panel on the discussion between optimistic roll-ups and ZK roll-ups. I believe that we will always need alternatives to zero knowledge. So I don't think, I know that Vitalik has said that eventually all roll-ups will be zero knowledge. Frankly, I don't believe that. I think we will always stick with alternatives with optimistic solutions. The reason is very simple. Because the optimization of arithmetization, which are sort of sketched here below, is too big. So even at the moment we have the overhead factor is about 100,000 or so. I think that Justin Taylor defined a million like 6 months or a year ago. I think by now maybe it's 100,000. Let's say we have dramatic improvements and we can make this overhead drop to a factor of 10. Then this still can be too high in some situations, right? If you have a computation that takes 6 hours and then you need to have a zero knowledge proof for it, and the creation of the proofs takes 60 hours, then that's 2.5 days. So that's, in some instances, this is just not acceptable. So this is why I think we will always have alternatives to zero knowledge proofs. I think that the optimistic verifiable computation will expand beyond roll-ups, and we see we see this in BitVM. Well, this is, in some sense, is a rollup. We have the naysayer proofs. And we have the rise now of markets for verifiable computing. Again, you can maybe have a choice whether you do the verification optimistically or you do a ZK proof creation and verification. So the idea is that this is going to be completely outsourced. This is in combination with proof recursion technique. This is powerful. So this is where I want to stop. So this is the summary of the talk. You have now the improvements have been filled in at the bottom of the slide. And some of this has been publication. I have further information I should have said there. There's a blog of my explaining the entangled rollup, and there's also a technical paper on the entangled rollup. You can have the tiny URLs here, or you can have the QR codes. Okay, so this is it. Thank you very much for your attention.
Okay, thank you so much, sir. A round of applause. Thank you, thank you. That was a beautiful presentation, sir.
What's that?
I said that was a beautiful presentation. Thank you so much.
Yep.
All right, sir. I think with that, we definitely. Are there any questions? No questions for now. I think we're good.
Okay, thank
All
you.
right, thank you, sir.
Pleasure.
All right. Let me have that. Let me have. All right. Thank you. Okay, so with that, they say the 2024 season comes to an end, right? So with that, we would especially love to thank our team, the LEO team. We would love to thank all our partners, SciSig, Rig Zero, ZK AIM, O1 Labs, every single person that has made this possible. And we would like to thank the media team for broadcasting this. You guys are doing an amazing job. We'd love to thank Jimmy. We'd love to thank Annie. We'd like to thank the team, Viv, every single person. We'd love to thank the staffs of this FYI. I would love to thank everybody. The food was amazing. Everything here was amazing, super, super amazing. We had fun. And with that, we would say this was the last content for today. I was looking for the right word to end this with. And with that, I would say it was a beautiful session. I had a lot of fun. I hope you had a lot of fun too. And we would say, let's do this again some other time. But with this comes to an end now. Thank you so much. And stay enjoying ZK roll-ups. Thank you.